Everything is number, or at least it is for a computer scientist like you. In this module, we will work through numerical tools that will support your journey as a computer scientist. I want to invite you to think of what I mean with everything is number. Write down from a scale from 1 to 10 how much you agree with that statement. 10 is total agreement. It is a number. And jot down your thoughts on it and write the date. As you progress along this module, revisit this question and add any new thoughts. And do join the discussion forum on this topic and see what your module colleagues came up with. Now, my name is Sara Santos. I was born in Portugal and I live in London in the UK. I'm a mathematician with a love for arts and passion for computing. I love knitting socks, wrapping up presents, mathematically respecting the wrapping paper pattern, and I love dancing. Tell us more about you in the discussion forum. Now, back to you and computing. On a day-to-day basis, you will abstract from how a computer works at the very basic machine level. Still, a basic understanding of the numerical foundation of how computers work will help you be an effective problem solver and a creative professional. That's a pretty cool computer scientist. Computers compute. All information is computed as numbers. Whether you are manipulating pixels of images, creating websites, transforming sound, creating music, analyzing business data, designing VR or video games, you will always use tools with a mathematical base. I love mathematics and I particularly enjoy witnessing people connecting with their inner mathematician. A common ground we have as humans is a want for patterns. And the number sense and a need to express thoughts numerically is part of this knack for patterns. We humans are pattern searchers, and mathematics is the ultimate expression of our conquest of patterns. The word mathematics comes from mathema, that relates to gaining knowledge, to really knowing something. Patterns, rhythm, beauty, and the pleasure that comes from those are a very human thing. People specialize on how they deal with patterns. Some paint it, dance it, sing it, drum it, feel them, cause patterns in others via words, code, laughter, medicine, others even without a physical context. Being a mathematician, observing patterns, seeking the rule behind them, being able to know things for sure, proving that a rule works. Also, being baffled by the mysteries of patterns is all part of being human. It is the process of studying patterns that we nowadays call mathematics. But deep down, we are all mathematicians. Some of the mathematics we cover here may be familiar to you. Other parts may seem outlandish, but we keep it all linked to computing situations, and we invite you to always place the maths we learn in the context of a theme or a problem in computing. We will support you on that journey too. But what have I got in store for you? This module is designed as a walking and climbing journey. We are in it together, and I have prepared the way. You are going along the same path with enough room for you to do your own footsteps, but you are to do the walking, and you all can talk along the way. I'll point out some beautiful bits on the landscape. You will have options to go off the track sometimes, but within sight of the journey. You can stop and have a breather and then race back in. You can also talk along the way, and I hope you also point out to all of us when you find a new flower, tree or special rock along the way. The videos that contain examples were made thinking about you stopping the video and working through the example yourself with good old-fashioned pen and paper before you check against my result. Don't be tricked by the need to be right all the time. The surprise of being wrong and learning from it is a very valuable experience, so enjoy it and learn. Sometimes you'll be asked to read something in advance or think of a problem or revise a topic before a lecture. Do it and bring your own notes and thoughts, questions with you. You need a scientific calculator that is not your computer or your phone. After each video, do attempt the formative quizzes as soon as possible to understand if you need to revisit the videos or if you can progress to the next. The point of the formative quizzes is for you to get feedback on your learning, so do attempt it early on and as often as you need. Embrace the difficulties as learning moments and share your questions and thoughts in the discussion forum. We want you to succeed. There will be tasks with problem-solving elements and some peer reviews. You are encouraged to discuss some elements of these tasks in the forum to make sure you understand the assignment. There will be at least one summative quiz per topic that may contain questions that require you having completed previous tasks in order to be able to answer. We will look at numbers, functions, geometry, linear algebra, and simple probability. Numbers will include binary and other bases, as well as sequences and series. In functions, we will look at graphs, but also at calculus. In geometry and linear algebra, we will go through triangles, vectors, and matrices. Come along with us in this journey and enjoy the module. Have you ever wondered how computers work at the very lowest level? Or how is the input of information that you enter by either touching a screen or typing on a keyboard used inside a machine to be computed into an action, such as opening a website, playing music, or even just adding up numbers? In computing, everything is number. Everything is treated as a number, and it all boils down to comparing and operating with zeros and ones. But how? And do you need to know all about this low-level process all the time? Fortunately, the answer to that question is no. You can abstract from it, but it will save you a lot of bother if you have a sense of how it works. And here's an idea. A light switch is either on or off. And at the very basic level, there are many switches inside a computer. And operations that involve the on and off state of switches make the whole magic of computing work. Here's how many switches are inside each type of computer. There's 1 billion switches inside a laptop. I used a long scale for naming numbers with large numbers of zeros. And there's 1,000 million switches inside a smartphone. 2 million switches inside a scientific calculator. By the way, you are going to need one for this course. Now, I've got a job for you. Go and find out what I mean by switches. I wanted to go and find out what is, at the hardware level, that makes the computations inside a computer. Go to the lowest, simplest level you can and discuss with your peers in the discussion forum on the following lessons. What other devices have switches? You go and find out which everyday gadgets and devices have it and how many. Bring back your findings to the discussion forum. Basically, on equals 1, off equals 0. And here's one example of these switches in action. I do nothing, 0, and nothing happens. So input 0 gives output 0. I push it, so it is an input of 1. And at the end, I have an output of 1. We can do operations with these switches, and in a full computing degree, you study them as logic gates and create a computer. If you fancy it, you can buy kits of connectable logic gates and build your own devices. Or if you're like me, and like doing things from scratch, you can build a simple computer using rods and spindles, or Lego parts, or even dominoes. And here's a simple calculator. It performs the addition of two numbers. It adds 0 plus 0 0 plus 1, 1 plus 0, 1 plus 1. I know, you are really impressed with this level of calculation. But bear with me. We add up 1 plus 1 here. Well, 1 plus 1 is 2. But we've got one output with nothing and one output with 1. How is this 2? In other words, what is the meaning of each of these outputs? They are like symbols to represent numbers, just like you and I use 35, 3, 5, to mean 3 tens plus 5 ones. So the outputs have a value of 1s and 2s. Let's have you deciphering this. Study this image carefully, and when you think you've got it, give your answer in the in-video quiz. Okay, some of you got it. The inputs are units, either 0 or 1. The output on the left is worth 1 if it's on, or 0 if it's off, so either 0 or 1. The output on the right is worth 2 if on, 0 if off. So the left is for 1s and the right is for 2s. Together, the two outputs can make the numbers 0, 1, 2 and 3, although in this calculation we never get an output of 3 as a result. The clever thing is to code numbers using 0s and 1s in positions that are worth 1 or 2. It takes about 148 dominoes for this operation. Adding up two two-digit numbers in this fashion, made of 0s and 1s only, takes about 10,000 dominoes. So you can imagine the trillions of dominoes needed to mimic a smartphone. And imagine how long computations like the ones performed by a smartphone would take if mimicked in dominoes. I invite you to go and visit your nearest science museum and learn about the initial computers and then predecessor mechanical calculators. The key element in a computer is the ability to have a device that makes decisions under logical rules. And the first person to come up with such a device was Ada Lovelace, who made the jump from mechanical calculating devices to digital computation. And how does this relate to light switches and to how computers really work? And why am I talking to you about this in a mathematics module? Back to the code I mentioned earlier, as you may have realized, it's called binary. 0 in binary is 0, 1 in binary is 1. 1 0 in binary is 2, 1 1 in binary is 3, and so on. Well, how to make the next numbers? We will study this in this section. We will look at steps to make the conversion of everyday numbers to binary and to other number systems. We will use it in the context of hiding secret messages inside images and using encryption to guarantee secure exchange of messages. Online banking and other secure websites use encryption to protect sensitive information. Throughout this topic, bear in mind these two problems: concealing a message in an image and encryption of secret messages. Think of them from the point of view of computer science and how we implement it computationally to send messages using the internet. If you are brand new to computing, panic not. We will prepare you with the tools you need. Let me tell you more about these two problems. Everything is number, and so are pictures. The quality of a picture is usually rated on its resolution, that is, the number of pixels, the number of little squares made of one single shade of color that make up the whole picture. A small image, like this one, already needs 16 pixels, and that means at least 48 numbers to convey the pixel information. Let's look at the numbers that describe the color of a pixel. When making a web page, we write HTML instructions to give color information to parts of the page. Let's look at the W3 School's website. I'll show you the tools for color coding, and one of them is this one here, the RGB calculator. So I've got black at the moment, color black, and I'm gonna go for red. It's not probably the best choice for a whole web page, but anyway, I mean, why not? Why not? So full red, 255 of red, and if I want to make the page, say, yellow, surprisingly, I'll just keep adding. Green, you see it's turning a little bit orange. That's quite a nice shade. More and more green and yellower, almost the color of my dress. Let's see, and then top yellow. Wow. Okay, so lots of red, lots of green, got yellow. But we could instead, let's play with blue. We've got red full on. Let's add a bit of blue. What's happening? Oh, shade of pink. And as we increase that blue, we get closer and closer to magenta. We get magenta color. Right. And there's other combinations we can have. So here's different shades. And as I put more and more of these colors, I've got nice pale pink. And all in, increasing. Guess what's happening? Guess what we're gonna get? With 0 in all colors, we had black. With 255 on each color, we have blue, the full spectrum of light. So we will tap into these numbers to hide secret messages inside images. We're going to tap into the color of red, the color of green, the color of blue to hide the color of another image. So we're going to use these numbers for the color values and some of their properties to hide a message. As we go through the lessons, I want you to get thinking on how we will use these numbers to hide the message that could even be another image. This is called steganography, hiding secret information within a public, non-secret image or text or data. I invite you to play with images and pixel color values. You can use the W3 School's website as a starting point. You can discuss in the forum how you think the color codes can be used for steganography. A great step up from concealing is encryption, where the secret message is scrambled so it cannot be read without the key that unscrambles the message. I have a secret message I received, which is here in this box, and I have my private key, this really large one over here, and the output, so the real message has been decrypted, I pressed there, is actually welcome to Numerical Mathematics. So it doesn't look anything like the message I received. Okay? To encrypt a message, I only need a public key, so I don't need that private key at all. My public key is this. So I've got my public key. I'm going to encrypt a message, and the message is my telephone number is 009 007 006, and on that box there, the output, I've got the encrypted message. So I use the public key to encrypt. Here's the output, and if I were to give this to you and you had the private key, you would then read my telephone number. Without the private key, it's not possible to extract the real meaning of the message, and we're going to look at a simplified version of this method later on. So the point is, you can send me safe messages if you have my public key, and usually that is a huge number that is not easy to factorize, as in finding numbers that divide into it. And my private key is a number that factorizes in that. Well, sort of. You will see later all the details. This method uses as a public key 2 prime numbers multiplied, 2 huge prime numbers, and that gives a huge number. And as a reminder, here on the website it does tell you we're looking at numbers that have around 100 to 200 digits. The private key will have a connection to one of the primes, and with that number I can decipher the message. But it's computationally too hard for someone else to work it out, and it may take forever. I mean, the forever of everyone's life on this planet. A process like this happens every time we have a secure transaction online, such as with online banking, and the padlock symbol appears. Encryption is different from steganography. In steganography, people see an image or a text that it's normal, and there's no reason to suspect there is a secret message in it. In encryption, a message may look unreadable, such as Sherlock Holmes was famous for using both, usually some sort of anagram of an encoded message that read like a real word. But let's leave Sherlock in the books, shall we? The information is converted into a code. The most secure system in classic computing relies on properties of prime numbers, specifically on how hard it is to find prime numbers that divide into a given number, if this number is very large. This means that finding the correct key to unscramble the encryption system in a timely fashion is extremely unlikely. Doing it in a systematic manner is impossible using classic computers. We will use your knowledge of working with integers, in particular prime numbers. These will be key for modular arithmetic and encryption, as well as decimals and fractions. Every technique you learn can be systematized, and you will be invited to write informal algorithms for all of them. If you want to take it further, always bear in mind implementing such algorithms in a programming language you are learning, or use it as an opportunity to learn one. Programming is outside the scope of this module, but the purpose of this topic is to prepare you for when you use number bases and modular arithmetic in computing. In these first 2 weeks, topic 1, you will aim to build the mathematical skills to tackle the following problems: steganography, using images; encryption, using prime numbers. You will implement a simple instance of these problems using the tools in our platform. Don't worry if you are absolutely brand new to computing. We have design tools to support you. Good morning, good morning, good morning.
Morning.
Oh, lovely to meet you. You are?
Nancy.
Jack.
Peter. And I'm Sarah. I am a mind reader. I'm going to read your mind, but I will ask for your permission. I got a nod of consent. Good. I tried to be polite. I try very hard. So I needed to think very hard of the day of your birthday. Just the date. Forget the year and the month, which is a day between 1 and 31, right? Now, beam it to me. You too good. I'm seeing too many numbers. Let's narrow it down. You've got a magic card in your hand. And that magic card has boxes that says card 4, card 3, all to card 0. Scan those cards and tell me all the cards that have your date. Okay? If there's more than one, I need to know all of them. And I will ask you in order. And try very hard not to tell me the date of your birthday, just the card numbers. Okay? You ready? Mm-hmm. Lovely. Peter?
1 and 0.
Only 1 and 0, Peter?
Yes.
I feel some vibration in my hat. No? Okay, that's a lovely, lovely number, a prime number. Let me hang on to that thought. Jack?
0, 2 and 4.
0, 2 and 4. So you're missing card 1 and 3 on purpose? Yeah. Yeah. And yours, Nancy?
0, 1 and 3.
0, 1
And 3.
and 3.
Yeah.
0, 1 and 3. So we've got prime numbers. We got number 3, Peter. It's on the third.
Correct.
Yes. Jack, tell me again what were the card numbers.
The card numbers are 0, 2 and 4.
0, 2 and 4.
Yeah.
We got a multiple of 3, but a multiple of 7. It's 21.
Yeah.
Is that right?
Yeah.
Yes. And yours is prime number 11. Is that right? 11? Oh. Yes. But thank you very much. Now, how did I read your mind? Did I really do it? As in, did you actually beam your number into my mind and my hat did his trick? Or, we're at university here and I'm a maths lecturer, or did I use some mathematics or science to do this? What do you think? How did I read their minds? Actually, I made the audience give me their birthday in code, a code made of card numbers, and I used maths to decode it. Take a moment to examine the magic mind-reading cards closely. Make note of all the patterns you find. Some may help, some may not, but they are all worth noting down to try to make sense of it later. You can use the discussion forum at any stage to discuss your thoughts or even investigate some patterns together. Note that all the cards have exactly the same number of dates on them, 16. But why 16? And why did I number the cards from 0 to 4 instead of 1 to 5? Notice that some cards have consecutive numbers in them. But what is the pattern? And does this matter at all? It doesn't give you the method I used to uncover Alva and T's birthdays, but if you study these characteristics, you will gain further knowledge and understanding of the system behind it. But try this. Read my mind. I'm thinking of the date that is on card 4, on card 3, and on card 0 only. Of course, you can look at all possible combinations, but again, that will not give you any insight to the system behind it. It will just get you an answer. If you try to understand what is going on, you'll crack the code. Now, I'll guide you through the mind-reading process. Note down the first number that appears on each of the selected cards. The first number listed in card 4 is 16, the first on card 3 is 8, and on card 0 it's 1. But how can we use the numbers 16, 8 and 1 to make my date? Let's leave this question for a bit and we'll come back to it later. Let's try this approach with a number you select. Write your selected number, it's a number between 1 and 31, and note down all the cards where it features. I mean all of them. Write down the first number featuring on each of those cards. Compare the date and those special numbers. Any thoughts? Any ideas? Feel free to pause the video now and work through some examples until you crack it. I don't want to rob you of the delight of discovery. In fact, anything you discover becomes a memory with an emotion and with many more dimensions and connections than something you read or are told. So throughout this course, any investment you put into understanding and discovering will pay off. especially if you experience a bit of healthy struggle. Okay then, so back to my example. 16 plus 8 plus 1 makes 25. And let's check that 25 is in exactly those cards and no other. Could it be just coincidence? Adding up the first number in the cards, resulting in the secret number? Well, we have a theory now, we can test it. Or better still, you can test it. Do it again with other numbers. Once you get data that confirms the theory, you need a proof that it will always work. In mathematics, such a proof is an explanation, and here it comes. The way the mind-reading cards code the date of the birthday is the same we used in our domino computer. Binary. The first numbers of the cards are 1, 2, 4, 8 and 16. They're all doubling numbers. They are powers of 2. 2 to the 0, 2 to the 1, 2 squared, 2 cubed, 2 to the power of 4. To write 25 in binary, we write 11001, where each 1 stands for 25 being on a card and 0 stands for not being on that card. So from left to right, we have card 4, card 3, card 2, card 1, card 0, and we write 1 for being on card 4, 1 for being on card 3, 0 for not being on card 2, 0 for not being on card 1, and 1 for being on card 0. The worth of these positions are 16, 8, 4, 2, and 1. So if there is a 1 in a position, we add the corresponding worth. In everyday life, we use the decimal system using digits 0 to 9. 10 digits in total. The number 25 uses 5 in the position that is worth 1 and uses 2 in the position that is worth 10. It is very likely that the reason behind using 10 digits is that it is the number of fingers humans usually have in their hands. The decimal system is also called base 10. The worth of each position is called the place value. The place values in decimal go up by a factor of 10. It's always the base number, starting from 1. We read place value from right to left, with the rightmost place value being 1, then 10, then 100, and so on. The digits, a word that comes from the Latin word for fingers, are multiplied by the place value in order to know the total value. We use this recipe for any number base. The key idea in number bases is that the base number is how many digits are used, and the place values start in 1 on the right hand side and the next place value on the left goes up by a factor of the base. So base 2, called binary, has 2 digits, 0 to 1. The place values are powers of 2. Base 60, called sexagesimal, has 60 digits from 0 to 59, and the place values are powers of 60, and so on. But base numbers aren't a modern thing. They have been along with us as humans since the time we started organizing counting for larger numbers. Number bases allow us to use only a small number of symbols to write an unlimited quantity of numbers in a systematic fashion. It is a huge leap from carving notches on a bone to keep track of how many sheep you keep. A number sense is not exclusive to humans. Many mammals and birds have a number sense, and there is evidence to show such animals being able to distinguish quantities of 1, 2, and 3, some also 4, and an ability to compare larger quantities or even fractional quantities such as a half, a quarter, and 3/4. But we, humans, are a species that took that number sense further and have mental and physical representations of counting numbers, including the concept of nothing and infinity. Our species has cultural needs that require precision And so we developed a system for noting down numbers, making sense of them, and doing sophisticated operations with them. We developed routines, algorithms, to add up, subtract, multiply, divide, to keep track of money and goods when trading. Today, we still employ mathematicians and computer scientists to work in trading. Babylonians used the sexagesimal system combined with decimal. Base 10 to make numbers up to 59, the digits. These digits were then used in place values that are worth powers of 60. In sexagesimal, 20, 4, 59 means, from the right to the left, 59 units, 4 times 60, and 20 times 360, all added up. So the expanded form of this number is 20 times 360 plus 4 times 60 plus 69. And note, we write from left to right, from the largest place value to the smallest, and this equals to 7,200 plus 240 plus 59, which equals 7,499 in decimal. Now, are you wondering if the Babylonians had 60 different symbols for the digits 0 to 59? Yes and no. The genius of it is that they used 2 symbols only to make all the digits. They used clay tablets and a stylus, really, just a stick, and pressed the stylus on the fresh clay to make marks like this for 10 and like this for 1. And using base 10, they organized the marks like in this picture. And this allowed them to make astronomical calculations. I mean, both as in large numbers and also as in tracking the movements of the bodies observed in the sky. The motivation for this system may be that to observe the sky, it is handy to divide a circle into many small equal parts. 60 is a number with many factors. It can be divided by 1, 2, 3, 4, 5, 6, 10, 12, 15, 20, 30, 60, which is handy when we work out fractions of the denominator 60. This was a very sophisticated system, and Babylonians calculated with fractions, not just whole numbers. Looking around cultures across the world, there is evidence of even other number systems. The Mayans used the vigesimal system, that is base 20. Although Europe primarily uses decimal systems, in France there is evidence of using vigesimal, as the French word for 80 is 420s, 80. The Chinese number system is decimal, but with the added feature that a symbol for the place value is written after the digit, as a reminder for the expanded form. For example, 193 is written as the equivalent of 1, 100, 9, 10, 3, with 110 being a symbol for the place value, 1, 9 and 3 being digits. If that sounds really long, join me in appreciating a language fit for computation. The sounds for number words are shorter than the corresponding English words. In Britain and the US, the imperial system of measures uses bases 8, 12, 14 and 16, as they are 12 inches in a foot, 16 ounces in a pound, 14 pounds in a stone, 8 pints in a gallon, all side by side with decimal. Now, the digits we use today in the decimal system come from the Hindu-Arabic numerals. The trading in the Mediterranean gave Europe access to a much more sophisticated number system, positional and fit for efficient arithmetic. In the 1200s, Leonardo di Pisa, also known as Fibonacci, and himself the son of a trader, popularized these numbers. Until then, in Europe, the Roman numerals were used, and these were not suitable for speedy calculations, as the system is not positional. What I mean is that to add 16 and 43, we add the units, 6 plus 3 to give 9, and the tens, 1 plus 4 to give 5, and get 59. With Roman numerals, it takes longer, as the numbers in each place value are not so clear. We still measure time using other bases. What bases are these? I invite you to investigate grey codes, as these are variations of straight binary system but have additional properties. We will not cover it in this topic, but it is of interest for any computer scientists wanting to use number systems and error correcting codes in making physical devices. It surprisingly comes up in the disentanglement puzzle called Bagnodier. In the next lessons, we will look at number systems of base 2, 8, 16, and will perform arithmetic operations in these bases. To warm up, refresh your memory of how you learned to perform addition, subtraction, multiplication and division by hand back when you were a child. We'll also look at fractional numbers, that is between 0 and 1, and how we work with their digital expansion and their fraction representation. So go ahead and revise how to operate with fractions and turn digital expansions such as 0.25 into the fraction a quarter. You will then extend these techniques to any number base. Count with me in binary. 0, 1, 1, 0, 1, 1, 1, 0, 0. Continue the list until you have 16 numbers. And the last one, 1, 0, 0, 0, 0. Note down the patterns you see. And let's number these in decimal, side by side. What numbers are 1 followed by zeros? 2, 4, 8, 16. How many zeros for 2? And for 4? Or for 8? For 16? What is the pattern? Pause and think. That's it. 2 has 1 0 in binary. 4 has 2 zeros. 8, 3. 16, 4. And 2 equals 2 to the power of 1. 4 is 2 squared. 8 is 2 cubed. 16, 2 to the power of 4. So the number of zeros is the index of the power of 2. When we talk about place value, the most important thing to take into account is what symbols and how many are available to use, and what is the value of each position used. Recapping what we said in the last video, in binary we use digits 0 and 1. The place values run from right to left in increasing powers of 2 starting from 1. An example of binary number is 10011. To translate it into decimal, we note the value of each place value. We said the rightmost digit is the units, next the 2s, then the 4s, then the 8s, and finally the 16s. The expanded form is 1 times 16 plus 0 times 8 plus 0 times 4 plus 1 times 2 plus 1 times 1, which equals 16 plus 2 plus 1, which is 19. The place values run from right to left, start at 1, always, and are followed by 2, 4, and so on. I quite like the fact that plugging in an extra 0 at the right of a decimal number multiplies the number by 10. Can I use this idea for binary? Let's look at a couple more examples. Let's have number 110110 in binary. We want to write this number in decimal. The first thing we do is look at the place values of each of the digits. And I'm going to write those place values on top of the digits. The rightmost digit is worth 1, then 2, then 4, 8, 16 and 32. And we calculated these by starting in 1 and doubling every time. Every time we multiply by 2 to get the next place value. Now, looking at that number, every place value that has a 1, we will add the value. The place values with a 0, we'll ignore them. And that's how we're going to compute the number. So join me. 32, got a 1 there. We have a 1 on the 16, add it. We have a 1 on the 4, add it up. A 1 on the 2, add it all. And this comes up to 54 altogether. The way of presenting the answer is to write the number in binary with a little 2 and the answer in decimal with a little 10. 110, 110 in binary equals 54 in decimal. I'm going to look at another example just to make sure we got it. We change this number. Let's write a whole bunch of 1s. Let's put 6 1s on in a sequence. That's our number in binary. Now, we can do the same. We write the value of each place value. And in this case, we're going to add all these numbers up. Place values. We start on the right again is 1, 2, 4, 8, 16, 32. We add up all these numbers, 32, add up 16, add up 8, add up 4, add up 2, add up 1, and that gives us 63 altogether. 1, 1, 1, 1, 1, 1. In binary is the same as 63 in decimal. Now then, is there a better way of doing that? Is there a shortcut? Could we do this in a quicker way? Instead of adding up all the place values from 32 to 1, we could look that the number 111, 111 is just 1 less than the next number. And the next number is a 1 followed by 6 zeros. 111, 111 in binary is 1 less than 1 followed by 6 zeros. Yeah. And how does that help? Well, we'd only have 1 1, which means that we have one place value to consider, and that place value is a power of 2, is the next power of 2. It is 64. We could count them all up, or we could just say, hey, there's 6 zeros, that means that that place value is 2 to the power of 6, and that is 64. So this guy here, it's a 64 in decimal, and therefore we know that the original number is 1 less than that 64, 63, as we calculated before. This gives you 2 options of how to translate from binary to decimal. You can look at all the place values, or you can think about place values in a different way and create your own shortcuts. You have already looked into how the mind-reading cards that we looked at earlier relate to the place values in binary and allow us to work out numbers up to 31. Now, I want you to think about how you could make a set of cards to read numbers larger than 31. Use the discussion forum. Hello, let's look at how to translate from decimal to binary. We're going to look at the number 193 in decimal. There are several ways we can do this. We can look at place values in binary and compare them to how big our number is, and then make up the binary number in this way. What I mean is 193, let's compare it to the powers of 2 that are the place values of binary numbers. So I start writing the binary place values 1, 2, 4, 8, 16, 32, 64, 128, 256. And from all these numbers, the 256 is too large, so we won't use 256 to make 193. The largest we could use is 128. So I'm going to put a 1 there. That's because 128 is less than 193. Now what have we got? 193 minus 128. We've got 65 more to make. 65 we can make with 164, and now we've got 1 left to make. That means we'd want to use the 32, nor the 16, nor the 8, 4, 2, but we will use that one. So in summary, this way of translating from decimal to binary is just comparing the number in decimal to the consecutive powers of 2. And when you find the largest power of 2 that fits into that number, you stop and say, I'm going to take this power of 2. This is going to be my first 1 in binary. There is a more, let's say, computational or algorithmic way of doing it as a routine. We're going to start with 193 and we're going to divide by 2 over and over again and make a note of the remainders. 193 divided by 2 is 96 remainder 1. It's not a surprise the remainder is 1 because 193 is an odd number. So when you divide by 2 it has remainder 1. 96 divided by 2, 48. Remainder 0. 48 divided by 2, 24. Remainder 0. All these numbers are even, therefore the remainder is going to be 0. Divide by 2 is 12. Remainder 0. By 2 is 6. Remainder 0. It's 3. Remainder 0. And this is 1. Remainder 1. And we can't stop just yet because the result of the division is still 1. We need to go all the way to 0. So divide that 1 by 2. It's remainder 1. Now with these digits, we're going to write our binary number. The question is, which end do you start? What is the beginning? What is the end? What is the leftmost and what's the rightmost digit? Let's go back to 193 being an odd number. It's an odd number, therefore, when you divide by 2, the remainder is 1. That means that the rightmost digit in binary is going to be a 1. The rightmost digit is the first remainder you get. So the rightmost digit is going to be this guy here because it's the first division, and the leftmost digit is going to be this one. So that's the left, and that's the rightmost. I'm going to write the answer properly now. 193 in decimal number is written as that 1, that 1, that 0 and 0, 0 and so on. 0, 0, 0, 0, 0. How many zeros? 1, 2, 3, 4, 5 zeros, and the final one in binary. Done. You've worked with integers in binary and decimal, to and fro. We're going to look at numbers that aren't integers, numbers with a fractional part. Say we've got 1101.101. That's what I mean by fractional part. There is a point which we usually call a decimal point, but it's not a decimal point because we're working in binary, the fractional point. And these guys over here are the non-integer part. Now, what's their place value? What are they worth? Similarly to what we did with the integer part, we're going to write the place values above the digits. So we've got 1, 2, 4, and 8. And the way we work those out, we start in 1, we doubled. To go into the fractional part, we're going to divide by 2 every time. So 1 divided by 2, we've got a half. which is 0.5, and then we've got 0.25, and we've got 0.125. We can write these as fractions, which I'm going to write above it, and I encourage you to do so. That's a half, that's a quarter, and that's an eighth. We can write it as well as powers of 2. Let's do it. 2 to the 0 there, 2 to the 1, 2 to the 2, 2 to the 3, and 2 to the minus 1, 2 to the minus 2, 2 to the minus 3. Now, how do we now calculate this number into decimal? As before, where you've got a 1, you add the place value. Where you've got a 0, just ignore it. Let's do it. I'm going to add up the place values that have a 1. So 8 plus 4 plus 1 plus the half and plus the 1/8. Because we want this written in decimal and we want a decimal expansion with a fractional part, let's add up as digital expansion of the numbers. So we've got 8 plus 4 plus 1, we got 13, and then we've got a 1/2, which is 0.5, and 1/8, which was 0.125, and that adds up to 13.625, and that is 1101.101 in binary. Now, just reminding you again that in place value, the fractional part, so this number in decimal, 13.625, I will never say 13.625, never, unless I want to refer to 625 thousandths. But let's simply call it 13.625. Now, that was binary to decimal for fractional numbers. Let's do the other way around. Let's do from decimal to binary. Say my number is 271.25. That's my decimal number. How to write this in binary? Here's the algorithm. For the integer part, you've seen that we divide by 2 and keep note of the remainders. That's how we transform an integer number from decimal to binary. You divide by 2 over and over again. When you have a fractional part of the number, we're not going to divide by 2. We're going to multiply by 2, and instead of taking the remainder, we're going to take the integer part of that result. I'll show you. So this number, 271.25, the 271, you know how to do that one in binary, so I'm going to ignore it for now. I'm going to focus on writing the 0.25, writing that in binary. So in other words, we always separate the number into integer plus fractional. Okay, and we have 2 separate algorithms for that. So for 0.25, I will consecutively multiply by 2. Now, 0.25 times 2 is 0.5. The integer part is 0. So that integer part 0 is my first fractional digit. So that is going to be 0.0. That's the first digit I did just now. Now I look at what's left. So 0.5 times by 2 again, I get 1. And 1, the integer part is 1, so that is going to be my next digit that appears there. And the next thing to do is to take away that integer part and see what's left. Well, in this case, there's nothing left because 1 is the same as 1.0, 0, 0, 0, 0, 0. So when you take away the 1, all you have is 0. So you would finish the algorithm there. So we stop as the result is an integer. That means that 0.25 is 0.01 in binary, which is not very surprising if you think about the place value. The place value for that 0 is 1/2. The place value for that one is 1/4, and 1/4 is 0.25. So bang on, it's correct. We've calculated the fractional part of this number in binary. Let's now put it together with the binary translation of the integer part. So 271 is 100001111, which I haven't calculated here, but you now know how to calculate. So that is 271 into binary, and then dot the 01 that we calculated here for the fractional part. So that in binary is 271.25. Just to recap, we separate the integer part and the fractional part of the number, use the division algorithm to calculate the integer part into binary. For the fractional part, which is the new bit we've done here, you keep multiplying by 2, take the integer part of that result as your binary digit, and keep doubling what's left over and over again. Let's just do one more example. Say our number is now 0.75. That's a number, a decimal number, fractional. How do we do this into binary? Once again, we take the number, we double it, and 0.75 times 2 is 1.5. The integer part of this result is 1, so that's the first fractional digit, that's 1. Now I'm going to take away that integer part, so that 1.5, I'm going to take away the integer part, which is just the fractional part, is 0.5, and I will double that 0.5. That gives me 1. So that's the other digit, and again, we don't have any more fractional part left, so this is an integer, stop. So we stop. And therefore, 0.75 is written as 0.11 in binary, and looking at the place value, each of these ones corresponds to the fractional place values of 1/2 and 1/4, and 1/2 plus 1/4 is 0.5 plus 0.25, which is 0.75. So it all adds up. So 0.5 add with 0.25 is 0.75. Just to double check that we make sense of the calculations and the results we obtained. We looked at fractional numbers and how we translate between binary and decimal for those types of numbers. You may have asked yourself, are there more types of numbers than the fractional numbers we saw just before? There are mainly two types. You have the numbers that are rational and numbers that are irrational. I'll show you what I mean. A rational number is a number that can be written as a ratio. So something like a fraction, like 2/3, it is a rational number because the two numbers I'm using in this fraction are integers. The 2 is an integer, the 3 is an integer. Minus 1/5 is also a rational number, and traditionally we write, if the number is negative, the top number, the numerator, will be negative, and we keep the denominator, the bottom number, positive. They are written as fractions, but of course every fraction can be written in a digital expansion. So 2/3 is 0.666 and so on. It's a recurring decimal, we call it. The digital expansion of this number has a pattern that is repeated. It's a 6 that repeats over and over again. So we write this as 0.6 with that dot on top that says, I repeat the 6 to infinity. The minus 1/5 is minus 0.2. They're both rational numbers. They both have a digital expansion. One of them has a repeating digital expansion, the other a finite expansion. So this is finite and this is repeating. The cool thing is every fraction, every rational number, when you write it down as a digital expansion, you either have a finite expansion or a repeating expansion. That's it. If the number you're working with goes on forever without a repeating pattern, then it is an irrational number. And that means it cannot be written as a nice fraction with integer numbers. It cannot. And examples of that number you are familiar with, numbers like root 2, the square root of 2, and any number with a root, even numbers that you probably came across as pi, e, and so on, lots of constants, numbers that cannot be written as a fraction. Now, the point of this is, in binary, you will also meet digital expansions that are finite or recurring. And I'm just going to look at one example here so that you are familiar with what happens when you meet such a number. So going back to the number 2/3, I want to write this in binary. Okay, so we already know that the number is 0.6 recurring in decimal. In binary, we can approach it in several ways. Remember the algorithm we just looked? You keep doubling the number and gather the integer part as the digit. That's what we're going to do. So 2/3 times by 2, that is 4/3. 4/3 is more than 1. That is 1 plus 1/3. The integer part is that one. So that is going to be the first binary digit. And now the 1/3 is the fractional part. So we take the 1/3, we times it by 2. And now I have 2/3, which is less than 1. So this is a number like 0 point something. We know it's 0.6 recurring. So the integer part is the digit. We're going to put there. Now we would carry on doubling the number, 0.6 recurring, which is our 2/3, and double. And hang on, we have seen this before because that's the first line of our calculation. So we are repeating, we're back there. We're on a loop. That means that if we carry on doing this calculation over and over and over again, we're going to have that 1 0 repeated over and over again forever. In other words, 2/3 is written as a recurring digital expansion in decimal. That's the 0.66666. Or in binary is 0.101010, repeating over and over again. So I'm going to write this as 0.10 with a dot at the beginning of the period and a dot at the end of the period. So if you are working with a recurring digital expansion in binary, at some point your calculations will look the same, will follow the same pattern. You'll have a recurring set of calculations that creates that repeating pattern. This is how you know that you have such an example. We are using fractions and digital expansions to represent a number. I'm going to go through the process of transforming a digital expansion in decimal into a fraction, so we know how to handle it. Say the number in decimal is 0.117. This number can be written as a fraction. We know it has a finite digital expansion, therefore it can be written as a fraction with two numbers, a numerator and a denominator. How do we work them out? Here's what we do. I'm going to call this number x just for convenience, and I'm going to multiply this number by 10 over and over again until I have no no fractional part. So if I do 10x, I get 1.17. If I do 100x, I get 1.7. If I do 1000x, I get 117. That's the number I want. In fact, you could have worked out that it was enough to multiply by 1,000 straight away. And now what do? From here, to get the fraction for x, I divide both sides of the equation by 1,000. So I got 117 divided by 1,000, and that's the fraction that represents that digital expansion. Is this in lowest terms? Is this fraction in the simplest way, as in, are there common factors between 117 and 1,000? Not in this case, because 117 is a multiple of 3 and a multiple of 13, and the denominator doesn't have those factors, so it is in their lowest terms. But I'm going to do another example, a little bit similar, but this time is going to be a number with a repeating digital expansion. And I'm going to keep it very similar to that one. Say the pattern that repeats is the 117. Okay, so in other words, what I mean by this is 0.117, 117, 117, and so on. Okay, that's what I mean. That's my number. I'm going to call it x again for convenience, and what I want to do now is to multiply x by a power of 10 until the fractional part is exactly the same as the fractional part I have here on x. So if I multiply this number by 1,000, I'm going to shift 117 to the integer part of the number. But because it has a repeating digital expansion, the 117 will keep repeating on the fractional parts. So I still have that, and I will avoid writing forever by putting the dots on top. Okay, and now here's a trick. Because the two numbers, the x and the 1,000x, have the same fractional part, I can subtract them to obtain an integer number. So if I subtract, as in I do 1,000x, take away the x, that means I'm doing 117.117 recurring, and I'm going to take away 0.117 recurring, and that means these guys subtract, and I've got 117 left. Okay, so the result is 117, which is just the integer part. Okay, and now on this side, how many multiples of x do I have? Well, I had 1,000 of x, take away 1 of x, I've got 999 of x, and that's 117. And now to get the fraction for my number, I divide everything by 999, and there I am. And 117 divides by 9. 117 divided by 9 gives us 13, divide by 111. So that is the fraction that represents my recurring decimal, or my recurring digital expansion, 0.117. So in other words, 0.117 equals 13 over. Now I wanted to note that there is a way of knowing whether a fraction is going to have a finite expansion or is going to have a repeating expansion. It's to do with the denominator of that fraction. So in the examples we saw, we've got the two numbers here side by side, and in that first example, I have a finite digital expansion, and look what the denominator is. The denominator of this fraction is 1,000, which is divisible by 2 and by 5. On the second example, where I have the repeating fractional expansion, the denominator of the fraction is 111, which is not divisible by 2 and is not divisible by 5. So when I'm working in base 10 in decimal, the fractions that will give me a finite expansion have a denominator that is a multiple of 2 or a multiple of 5 or a multiple of both. any other fraction where the denominator doesn't have, is not divisible by 2 or not divisible by 5, it will give rise to a recurring decimal. We saw the algorithm to write fractional numbers in binary. Now we multiplied the number by 2 and took the integer part to get the digit for the digital expansion. Why do we do that? Why do we multiply by 2 when for the integer part of the number we do division by 2 and take remainders? We're going to look at why that is. It is to do with the place values. Say we have the binary number 0.1011. That's a number in binary. Although the number is in binary, I'm going to run the algorithm so first to observe what is happening. So the algorithm says multiply this number by 2. Now if I multiply this number by 2, because this is in binary, multiplying by 2 means I'm going to shift the place values. Let's look at the place values of the number to start with. This is for place value 1/2, 1/4, 1/8, 1/16. And so multiplying by 2 is going to shift the place values. It's going to double all of them. The first one that appears there for place value 1/2 is going to become the digit for place value 1. The 0 for place value 1/4 is going to become the digit from place value 1/2, and so on. So what I mean is that this number multiplied by 2 is going to be 1.011 in binary. And the algorithm said, let's take the integer part, and that's going to become the first digit of the expansion. So that should be the first digit, and that is true, and that is the first digit because that was the digit for place value 1/2, and now we double the number, it became the integer part. Now the algorithm says take the integer part away and keep just the fractional, so we would then have 0.011 in binary, and we would double it again. Again, doubling it is going to shift all the place values, so we have 0.11 in binary. The integer part is 0, and that 0 came from the place value of 1/4 from the initial number, because by now we multiplied by 2 twice, so we shifted the digit 2 places. And we keep going. We double it again. There's going to be 1.1 in binary. That integer part is the third digit of the expansion. Take away the integer part, we get 0.1 in binary. Multiply by 2, that means 1.0 in binary. The integer part is 1, which is the last digit, and we know to stop because as you remove the integer part, you're left with 0. So we stop. I hope this example gives you a better idea of why the algorithm works. In decimal, we know that looking at the digital expansion of a number, you can tell whether the number is rational or irrational. Rational numbers are numbers that can be written as a fraction with whole numbers as numerator and denominator. If instead of using a fraction we want to use the digital expansion of the number, can we tell if the number is rational or irrational? Yes, we can, because all rational numbers have either a finite digital expansion, like 0.5 or 0.62, or they have a recurring digital expansion. Like when you do 1/3 in your calculator, you see 0.33333 recurring. You can just write a 0.3 with a dot on top to say that that is a 3 that is going to repeat over and over again. Now, those are the two types of rational numbers, and they all are written as fractions, as we saw the method earlier on. What about binary? What happens with rational numbers when you write them in binary, or irrational numbers and you write them in binary? Surprisingly, or not, maybe you're already guessing, the same is true. If the number is rational, if the number can be written as a fraction with integer, numerator and denominator, then the digital expansion, no matter which base you write it on, it will be either finite or recurring. It might happen that a number can have a finite expansion in one base, but a recurring expansion on the different, or have recurring expansions on both, but with different periods, with different patterns of repetition. The key to deciding whether it's going to be finite or recurring is to do with the denominator of that fraction. I'm not going to go into too much detail, but I want to lift the veil of this to you so you know what to expect when you're working with these numbers. Let's look at 1 over 6. 1 over 6 is less than 1, therefore the first binary digit, the integer part, is going to be 0. And now I'm going to double this number. So 1/6 times 2, which is 2 over 6, which is 1/3. Now 1/3 is still less than 1, so the first fractional binary, it will be 0. So digit 0 there, digit 0 there. And now take 1/3 and double it. And that's 2/3. That is still less than 1, so I got another 0. And then 2/3, double it. I got 4/3, which is 1 plus 1/3. And that, the integer part is 1, so that's the digit I'm going to put there. Okay, and I'm going to take the fractional part and double it again. Now, at this stage, you realize that that 1/3 times 2 is what I've got there. So we're going to have this part repeating. So that is 1 over 6 as a fraction that it's written in decimal. It has a binary fractional expansion of 0.001 with 0.1 repeating. Now, there's two things I want to draw your attention for. First, there is a period, there is a repeating pattern. And second, there is an initial part before the repetition starts. Now, this initial 0 comes from the fact that the 6 being the denominator, 6 is 2 times 3. The fact that we have a 2, which is a factor of the base 2, means that I've got that initial 0, meaning I've got that initial non-repeating part. Then the fact that I've got a 3 as a factor of 6 means that I will have a repeating pattern. Now, why does 3 give us a repeating pattern? Because 3 has no common factors with the base. 3 has no common factors with 2, so I will have a periodic expansion. I've got that 2 that is a factor of the base, so I will have, say, a delay until the period begins. And these considerations I made here about the denominator of the fraction and the relationship to the factors of the base are essentially the bits that decide what the fractional expansion of a number looks like in a given base. Have a play with more fractions and gain an idea of how it works. If you have powers of 2 in the denominator, you will have a finite digital expansion in binary. If the number you have there isn't a power of 2, if it's a power of 2 times something else, or just no 2's at all, it will be a recurring decimal. In this lesson, we looked at number systems and we focused on a binary, both converting decimal to binary and binary to decimal. We looked as well at rational and irrational numbers and how they are represented both in decimal and in binary. Now, I would like you to get ready for operations in binary. That only requires you to recap how you've learned to do addition, subtraction and multiplication back in primary school. So go and revise that, those really handwritten algorithms, and get ready for the next lesson. And now we're going to compute with numbers in binary. It's all going to add up, I promise. We start with addition of binary numbers. Say we have big numbers like 1, 1, 0, 1, 1, and we want to add it up with the number 1, 0, 1, 1. We're going to do it old school style, okay? We're going to write the numbers one on top of the other and do the algorithm column by column like you learn how to add up numbers back in primary school. 1, 1, 0, 1, 1. Now we're going to write the numbers lined up with the place values correctly aligned. So 1, 0, 1, 1 underneath. Our long line, adding it up. And we have to keep in mind going in between binary and decimal for some of the minor calculations going on. So what I mean is first column, 1 plus 1, that is 2. 2 in binary is 1, 0. Hang on, how do we do this? Where do we write the numbers? No problem. So 1 plus 1 is 2. That is 1, 0 in binary. We need to put a 0 here, and the 1 would kind of go there, but we can't really write it there because that is going to be for the result of the column. So what we do, we're going to carry that digit, and we're going to put it at the top of the column. So I'm going to rub that one off, and I'm going to write it over there, because really that 1 is from the next place value. So we put it on the column for the next place value. And now we proceed. So we're now on the second column. We're going to add up the 1 with the 1 with the 1. So 1 plus 1 plus 1 is 3. And 3 is 1, 1 in binary. Again, we need the 1 over here. And the other one that is for the next place value, we put it on top. And now we add up the numbers in that column. 1 plus 0, that's just 1. No numbers to carry. And then 1 plus 1 again is 2. 2 is 1, 0, so 0 here, and the 1 for the next place value goes on top of the next column. And now 1, 1 is 2, so is 1, 0 again. And we'll put the 0 there, and we're going to put the 1 on the next column, but there's no next column, so we just put it on the next place value. Done. Okay, so what do we write? We write the result of our sum is that 1, 1, 0, 1, 1 in binary added with 1, 0, 1, 1 in binary equals 1, 0, 0, 1, 1, 0 in binary. And when you get used to doing this, you'll be a lot faster than converting binary to decimal of the both numbers, add them up, and then convert it back to binary. That is a long way. It's much better to learn how to manipulate the numbers in binary and get confident with it. Let's do another example of addition in binary. Let's do 1, 0, 1, 1, 0 added with a string of 1s, those there. You can anticipate that there might be loads of carries. Let's see. So first column for the place value 1, 0 plus 1 is 1, no problem. Now here 1 plus 1 is 2, 2 is 1, 0. So we're going to write a 0 here and 1 carried over there. Now 1 plus 1 plus 1 is 3. That's 1, 1. So 1 here and the next one there. 1 plus 1 is 2. 2 is 1, 0. So 0 there and 1 over there. 1 and 1 adds to 2, which is 1, 0. And there we go. So 1, 0, 1, 1, 0 in binary added with 1, 1, 1, 1 in binary is 1, 0, 0, 1, 0, 1 in binary. So that's how you perform addition purely in binary. We're now going to look at subtraction in binary. Let's do the following. Let's do 1, 0, 1, 0, 0, 0, take away 1, 0, 0, 0, 1. I'm just going to write it down. So we do 1, 0, 1, 0, 0, 0, take away 1, 0, 0, 0, 1. It's very important to line up the numbers in the correct columns of place value. We're going to subtract. Looking at it column by column, there's immediately a little problem, isn't it? Look at the first column there. 0 take away 1. How do we do that? Do you remember how we did that? How you did that in primary school for decimal numbers? You had to borrow, because 0 is too small to take away 1. You had to borrow. Where are we going to borrow from? Well, we're going to borrow from the bigger place values next to it. The thing is, we've got a 0 just there, which you can't borrow anything from there, and another one. So we're going to have to borrow from a lot of place values. What I mean is, we're going to look at this part of the number here. 100. 100 can be written as 1 add 1. That means we're going to replace the 100 by just 1, and when we're going to borrow that extra 1 to the first column this way, we're going to cross that 100 out, and we're going to replace it with 1, like I did here on the side. And this one here is going to be borrowed to the smaller place value. So this 0 becomes 10. That's 2. Now we do 10 take away 1. 10 take away 1. That's 2 minus 1. So that is 1. That means that 10 take away 1, just put a 1. And now I look at the next column. I got 1 take away 0. That's fine. 1 take away 0 is just 1. Next column, 1 take away 0, also just 1. Next column, actually, I haven't got anything there because I should have put a 0 there. I got 0 take away 0. That's just 0. Next column, I've got 0 take away 1. Same problem as before, but not an issue because we can borrow. And in fact, we just look, we've got 10 take away 1. That is 1. That's it. That means that 10, 1, 0, 0, 0 take away 1, 0, 0, 0, 1 is 1, 0, 1, 1, 1 in binary. Now, we can check if this is right or not. Let's just do the addition in binary backwards to see if we got the right sum. So, if we add these up, we should get the big guy. So let's do it here on the side. 1, 0, 0, 0, 1. 1, 0, 1, 1, 1. Let's add it up. 1 and 1 is 2, which is 0, 1. 1 and 1 is 2, which is 0, 1. 1 and 1 is 2, which is 0, 1. 1 plus 0 is just 1. 1 plus 1 is 2, which is 1, 0. And that is the number we started with, so correct. Now, next, let's do 1, 0, 0, 0, 1. Take away 1, 1, 1. So 1 take away 1 is just 0. Then next place value, we got 0 take away 1, which we can't do straight away. We've got to borrow. And again, we're going to borrow from that number of greater place value. So again, we observe the 1, 0, 0 is 1, 1 add 1. So we're going to replace that 1, 0, 0 by 1, 1. And we're going to replace this 0 here that was too small by 1, 0. That's where the borrowing is taking place. And now we do 1, 0, which is 2. Take away 1, that's 1. And now 1 take away 1 is just 0. 1, this one here, take away 0 is just 1. And over here we had nothing, so we're done. 1, 0, 0, 0, 1. Take away 1, 1, 1 is 1, 0, 1, 0. And let's check that we did the right sums. Just add up the 1, 0, 1, 0 with 1, 1, 1. And 1, 1, 0, 1, 0, 1, 0, which is the number we started with. So it is correct. Let's put the little 2's here. And there we are, subtraction in binary. We're now going to multiply numbers in binary. Let's look at simple multiplication first. Say we're doing 1, 1, 0, 1, and I just want to multiply that by 1, 0. It's not 10, it's 1, 0. And that is all in binary. I talked about 10 just as a reminder of how would we do this in decimal. I'm going to do it on the side. If you have 157 and you were going to multiply by 10, this is a proper 10, by 10, you would just increase all the place values by a factor of 10. So you just do 1570, as in the 7 is now, goes from being in the place values for the units to the place value of the tens. The 5 goes from being the place values for the tens to being the place values for the hundreds, and that 1 goes from being the place value for the hundreds to the place value for the thousands. And you stick a 0 in the units place value. So that's what you do in decimal. Now back to binary, this 1 0 means 2. But it has the same idea as multiplying by 10 in decimal, is that you shift the number 1 place value to the left. So that means it is 11010 in binary. This one is a place value for 1s. It becomes a digit on the place value for 2s. This 0 is a place value for 2s. It goes to the place values for 4s. This one, place value for 4s, becomes place value for 8s. And the 1 on the place values for 8s becomes the 1 on the place values for 16s. So that's what happens. And I put a 0 on the empty space for the place values for 1. So this is what happens when you multiply by 1 0 in binary, when you multiply by 2 in binary, when you double numbers in binary. If you double it again, you're going to shift the digits again 1 place value. So multiplying by powers of 2 in binary just shifts the number place values to the left. So this is the main idea to understand how multiplication works in binary. It's a lot easier to multiply in binary than it is to multiply in decimal, actually. I'll show you how. So let's look at doing a little bit more complicated multiplication. Say we're doing 1101, put another 1, multiply by 101. We can do the algorithm in this way. But let's see what we should expect. The multiply here, 101. 101 just means 100 add 1. And multiply a number by 1 changes nothing, just repeats the same number. Multiplying the number by 100 is going to shift all the digits 2 places to the left. So basically what we're going to do is we're going to add a copy of the number with a copy of the number shifted 2 places to the left. That's all is going to happen. Multiplying by 101 is going to be multiply 11011 by this guy, and multiply 11011 by 1, and then add the results. So 11011 with 2 zeros at the end, and this is just a copy of its own. Now, I haven't lined up the place values correctly there. I'm going to try and do it now. So 1, 1, 0, 1, and 1. And then adding these guys up will be... Okay. That's what we should expect. But I'm going to do that again on the main calculation here. So, let's do it here. So I multiply this top number by this first one. And that means just repeating the top number. So 1, 1, 0, 1, 1. Now, this 0 here means just leave another place value blank. So I'm going to leave that place value blank. And then multiply by this one here is going to be copy the number again, but starting from here. Okay? So I'm going to do 1, 1, 0, 1, and 1. And now add up everything. That's 1, that's 1, that's 1. 1 plus 1 is 2, which is 1, 0. So 0 with another 1 there. 1 plus 1 is 1, 0. Another 1 there. 1 plus 1 is 1, 0. So I put another 1 there. And 1 plus 1, 1, 0. And I've got it, which is what we had predicted over there. Now I'm just going to do one more example to see if we nail it. Okay, so I've got 1, 0, 1, 1, 1 multiply by 1, 1. So copy the top number. And now for the second one here, copy the number again, but one place value shifted to the left. So 1, 1, 1, 0, 1. Add them all up. 1 plus 1 is 2, which is 1, 0. 1 plus 1 plus 1 is 3, which is 1, 1. So carry. 1 plus 1 is 2, which is 1, 0. So 0 there and a 1 there. 1 plus 1 is 2, which is 1, 0. And I put that one there. 1 plus 1 is 2, which is 1, 0. So the result 1, 0, 1, 1, 1 in binary times 1, 1 in binary equals 1, 0, 0, 0, 1, 0, 1 in binary. And that's done. Hello there. We're looking at some examples of your work in writing the algorithms. Let's look at converting between decimal and binary. We're going to write the algorithm alongside looking at an example. We have the binary number 10111 and we're going to convert it to decimal. 10111. We're going to convert this number to decimal. We look through the place values, which I'll write here. So place values 1, 2, 4, 8, 16. We're going to do that in general for our algorithm, but let's focus on that example. For the conversion, all we have to do is to add up a place value when we have a 1. That's all we do. So we have that decision there to do. So let's bear that in mind, so we write that step, that decision in the algorithm. So in this example, we're going to add up the 16, the 4, the 2 and the 1. So we're going to need a container to hold that sum, and we're going to do it on a loop. Now, it might help if you picture that we have these values on a bit of paper. So we're going to have a mental bit of paper to hold the value of a number that it's like a variable. So let's bear that in mind as we go along. So to start with, we need to know which place value we begin. I want to start with the largest place value. I want to start on the left of the number. I want to start on the place value 16 here. So how do I know where to start? If I want to start on that place value 16, I need to know how many digits I've got. So the first thing is work out how many digits we have. Count the digits of the number. So our first step is going to be as simple as count the number of digits. Okay? Count the number of digits. Now we count, but it's not enough to count. We need to hold that value in the variable, which is like a bit of paper if you want, or a little box where we're going to keep that. We're going to call n this value. Okay, so make big N equals to this number. I am using a rather informal language here, and it's fine. We are precise about the things we need to be precise, and the other parts we can be quite informal in our algorithm. This is not a formal algorithm class. Right, so we do that. In our case, we count how many digits. We have 1, 2, 3, 4, 5 digits. Our N is 5. Okay, and how does that help with what we're going to do next? We're going to start with the large place value. In our example, the large place value is the 1 on place value 16. How does 16 relate to that n equals 5? 16 is 2 to the power of 4. It's 1 less than the 5. That means the first place value we're going to add is the 2 to the power, not n, but n minus 1. So I'll say on step 2, for now, we're going to add up the value of 2 to the power of n minus 1. But you are screaming over there, adding where? We need a container, don't we? We need another variable to hold the sum. So step 2 is actually going to be make a variable sum. Make a variable sum. And it's going to be an integer variable. Sum. And we're going to restart it. We're going to start it with value equals 0. Okay? That's 0. And now we've got a container. We're going to put in there the first digit. Well, not quite the digit. What we want to put in there is the place value of that leftmost digit. So the place value is, in that case, is 2 to the 4. We want 2 to the n minus 1. So step 3 is going to be make sum equals to the sum you had there, which was 0, but doesn't matter. Add 2 to the power n minus 1. 2 to the n minus 1. Great. We got our first little bit in our routine. Now, some of you might be thinking, shouldn't I multiply that place value by the value of the digit? Yes, you are right. We would do digit times the place value. But remember, this is the first time we're doing it. The first digit is the first one, you find. We're not going to run through all the possible zeros into infinity. We are going to start with 1. So in this first step, we can skip that. But you might be saying, shouldn't we future-proof this step and have a multiplication by the digit? Let's come back to this thought. So step 3 so far is this way, and now we want to move to the next digit, move to the next digit. How do I do that? We can say move to the next digit. Let's try and write that down. Move to the next digit to the right. Okay? Can do that. That means we now would be, on our example, we would be on place value 8, which we have a 0. And then what we would do, because I've got a 0, I've got nothing to add to my sum. If I had a 1, I would add again the place value. Okay, we could do that. So we need to decide. We need to check what that digit is. So on next step, which I'm going to write, say step 5, we would say, let's have a look there. What do we say? If the digit is 0, do nothing. If the digit is 1, add the place value, okay? Now, do we know what the place value is? The place value needs to be the other power of 2, a smaller power. So it looks like we have to update our place value holder, which I think it's enough to use n, the number of digits, and now say, I was on the last digit, I want to now go to the next one. So I'm going to say, I'm going to make n be 1 less. And now, let's see, could we use the steps we had before? Could we go back to step 3 and say the sum is going to be the previous sum plus the next power of 2? We could do that. But we did say that we only do that if the digit is a 1. If the digit is a 0, we don't go there. So it looks like we need to redo that step 3 and have an if. If the digit is a 1, do this. If the digit is 0, just carry on to the next digit. But you are probably thinking, have we got a way of keeping hold of digits? Not yet. We're going to need a container for the current digit. So I'm going to have to go back and let's see, on step 1 we count the number of digits. We made n to be the number of digits. Okay. On step 2, we said make a variable sum equals 0. That's fine. But we also need to make a digit variable. So I'm going to change, feels like we need to make a digit variable here. Digit equals 1 on that first step. So we say make variables sum equals 0 and digit equal 1. Okay, maybe that works. So let's see. On step 5, n equals n minus 1, so we moved a digit. We now need to go where? We need to go to the step 3, but we need to read the next digit. So on step 4, we say move to the next digit to the right. So we have, okay, into value, into variable digit. Okay, we're kind of reading that. And then we can go back to step 3. Okay, so on step 5, we could say step 6 is go to step 3. And now what happens on step 3? On step 3 says do the sum, but we only do that if d equals 1. So we need to do an if there. We have several options. We could say, at this stage, we could say if digit equals 1, where do we go? If it's 1, we're going to do the sum. So we go to step 3. Go to step 3. Okay. What happens if the digit is 0? If the digit is 0, we want to move to the next digit. Okay. It might be easier for us to do the if on step 3. So that's what I'm going to do. Instead of going this way, I'm going to say we do a nice neat loop. We're going to go here, go to step 3, and on step 3 we're going to make a change. On that change there we're going to do the new step 3 is going to be if the digit is 1, do the sum. If it's 0, move on. Okay? So we're going to say if digit equals 1, we're going to do sum equals sum plus the power of 2. Else, what else? Else move on. Else do nothing. Move on to the next digit. Okay? That's great. So that's new step 3 there. Step 3. Okay, so replace that step 3. Now, does that make sense? Let's have a look. Let's write this down to make sure that the whole algorithm makes sense. So we're going to do step 1. Make a new variable n and make n equal number of digits of the number. And then what do we say? On step 2, we make 2 variables, the sum and the digit. Okay, we can make that into 2 steps. Step 2, make a variable sum and set sum equal to 0. On step 3, we can do, that's the digit, make variable digit, and we set digit to 1, and that's because the first digit we read is always a 1. And now our new step 4 is going to be our old step 3. If the digit is 1, do the sum. If not, move on. So that's going to be step 4. If digit equals 1, sum equals the previous sum, and top it up with the correct power of 2. Else, we don't need to say else because else just move on. And what happens moving on? Moving on means go to the next digit. So we're going to write that step, which is now going to be step 5. And move to the next digit to the right. Okay. move to the next digit to the right, store it in digit, that's the variable digit, and now it says we now should decrease n and then go to step 3. So step 6 will be decrease n, so n equals n minus 1, and then the next step will be go to the loop, which now is step 4. Go to step 4. Step 4 here. Okay, if it's 1, add it. If otherwise, then move on, decrease the n. Okay, and that looks pretty cool. Does this work? Is this a good algorithm? Does it stop? Not so far. When do we stop? We stop when we run out of digits. We run out of digits when n is 1. Okay, so we need to stop. We need to put an if statement somewhere saying let's stop when n is 1 when we do the final round. Okay, so what do we do? Here when we say go to step 4, we should say if n is 1, we still want to run the cycle. So if n is 0, we want to stop. So we're going to change this statement here, and we're going to say, instead of go to step 4, we're going to say if n equals 0, we want to stop. So I'm going to leave some space for what we're going to say we stop. Because if we stop, we need to print out the value of the number, and the value is sum, and then stop. Okay? So if n is 0, output the message value in binary equals, print out the value of the variable, so equals sum. Okay, and then stop. Else, if n is not 0, else that means n is 1 or more, we still go to step 4. Okay, so let's run this by hand now. Right, so step 1, make a new variable n, and its number of digits. Our number was 10111, so the number of digits n is 5. Okay, make my variable sum equals 0, that's fine, and my variable digit equal 1, that's great. And that's because I'm the beginning of the number 10111. Now, step 4, if the digit is 1, which it is, do the sum. So sum is now the value I had there, which was 0, add 2 to the power of 4, because it's 5 minus 1, so 2 to the 4. Great. And then step 5, move to the next digit to the right. So that's now the digit equals 0. So now my digit equals 0. And step 6, decrease the n. So n is now 4. Great. And if n is 0, which is not, else go to step 4. Step 4, digit is 1. No, it's not. So move on. Step 5, move to the next digit to the right. And next digit is a 1. Store it on the variable. Digit is now 1. Great. Decrease the n. N is 3. If n is 0, no, n is not 0, so go to step 4. Digit is 1, yes it is. Update the sum. The sum is now what I had before, 2 to the 4, add 2 to the square, because it's 2 to the n minus 1 and n is 3. Great. And then step 5, move to the next digit, so there's another 1 that is coming. And step 6, decrease the n is 2. And then step 7, if n is 0, no it's not, so go to step 4. Step 4, if digit is 1, which it is, do the sum. So sum is what I had there before, add 2 to the n minus 1. N is 2, so it's 2 to the 1. And then step 5, move to the next digit. Next digit is a 1. And step 6, decrease the n. N is now 1. And if n is 0, no, it's not. Step 4, digit is 1, add the sum. So sum now is what I had there before, and now add 2 to the 1 less than the n, so 2 to the 0. And step 5, move to the next digit to the right. There is no digit to the right. Yes, so it feels that we should fix the algorithm and say there, if there's nowhere else to move, we should stop. So the instructions I put on step 7 should be on step 5. And I'm showing you how we improve our algorithm as we run it. I'm not expecting you to write the algorithm neat first time round. It's a trial and improvement process. So we need to go back and fix what we've written, and we're going to do it here as well. So it feels that the right place to have a stopping instruction is on step 5. Move to the next digit to the right and store it in digits. So we need to have there an instruction. If n is 0, we would output. So we're going to change that instruction there. And we're going to say if n is 1, we now need to output the result. Output value in binary, value in decimal. Equals sum, and we stop. Else we need to move to the next digit. Okay, else move to the next digit. And then store it in digit. Okay, and that we're going to tidy up. That means that on step and we need to make the n equals n minus 1 on the same step. Okay, and then on step 6, which we only run if we still got a digit to go, we do go to step 4. Okay. Okay. Now, does that make sense with our example? Yes, so where were we? We were at the point where we had n equals 1. If n equals 1, output, and we had done the sum. We had a total sum. If n is 1, we output the value. So at this point, we print the value in decimal is, and then we do the sum. We had 16 plus 4 plus 2, which was 22. That's what we accumulated on variable sum. And we stop. Okay, great. Did I change what we've done before? No, because every time we got to this stage in the other steps, n was bigger than 1, and so we could carry on doing the sum. Okay, so here's one example of an algorithm you could run for to do the conversion from binary to decimal. What things could be different? There are many ways of writing the same algorithm, but one thing we could change is that in this algorithm, when we do the sum equals sum plus a power of 2, we could have done a weighted sum. Instead of having if digit equals 1, we do the sum, and if digit equals 0, go somewhere else. Instead of that, we could have done sum equals sum plus the digit times the power of 2. And if the digit is 0, then that means you're not adding anything. If the digit is 1, you're adding the power of 2. So that is an alternative, which means you don't need to have ifs. There's different ways of solving the same problem. Another approach could be starting from the rightmost digit. You could start from the 1 on the right and then go up in your powers of 2. You could. So you could invert the cycle, and you could still say, now, instead of decreasing the n as we did, you could increase the n. So pretty much a similar structure as we had written just now, but instead of having n equals n minus 1 in your increment, in your decrement, we would increase n. We would start from n equals 1 and then n equals n plus 1 and so on. But then how do you know you stop? Well, same way, you stop because you count the digits to start with and you run this cycle that many times. So that's another way. There is still another way, which I'm not going to write in algorithm form, but I want to write the algebraic reason for. So instead of adding a power of 2 in every cycle, you could add the digit and then times it by 2. And so you add a digit and double the result. And that is a lot more efficient because you're not calculating powers of 2. You are doubling every time, which, if you remember, a machine level doubling is just putting a 0 at the end of a binary number. It's a very easy operation compared to multiplication. So back to this idea. We can do a new algorithm where the variable sum is going to store the new digit, then you double the sum, and then you add a new digit, and then you double the sum, and you carry on going like this. So I'm going to write the algebra of that, and that's a very elegant way of doing it. So for our example, where we have 5 digits, our number is this one, I'm going to call the digits digit 4, digit 3, digit 2, digit 1, and digit 0 in that order. But the expanded form of this number is going to be digit 4, 2 to the power of 4, plus digit 3, 2 cubed, plus digit 2, 2 squared, plus digit 1, 2 to the 1, plus digit 0, 2 to the 0. So this is the expanded form of that number. And I can have a 2 multiplying for most of it and decreasing the power. So this is what happens. This first part here, it's a multiple of 2. I've got a 2 on each on each term. So I do 2 times, and then instead of having d4 2 to the power 4, I'm going to have d4 2 cubed. Because the 2 outside the bracket and the 2 cubed multiply out to 2 to the 4. Then I have d3 2 squared plus d2 2 to the 1 plus d1. And then outside the bracket, I've got d0 2 to the 0. 2 to the 0 is just 1. Okay, and now inside the bracket, I can do the same idea. I put everything from d4 to d2 in a bracket with a factor of 2 out. So it's 2, 2, d4, 2 squared, plus d3, 2 to the 1, plus d2, 2 to the... I'm just going to write d2, could have write 2 to the 0, but I don't need to, plus d1 there. And I'm going to get rid of that 2 to the 0 because it's just 1. And I keep doing this. So the bracket there is going to be 2, and now bracket d4, 2 to the 1, plus d3, and then plus the d2, close the bracket, plus the d1, close the bracket, plus the d0. We can check if the brackets are right. Let's do some coloring. I've got, these are red brackets, that's great. These here are yellow brackets, that's cool. And the other ones are white brackets. That works. Okay, so let's do one more. One more level means 2, 2 bracket, 2 bracket. And now I've got 2 d4 plus d3 plus d2 plus d1 plus d0. I didn't add any brackets, but I just rewrote that d4 2 as a 2 times a thing. That means this nested sequence of brackets it's how I can build this sum in the way I said earlier. So if I start with a sum that it's D4, so the digit is kept in sum, and then the next round you double it, you're doing this, double sum, and then the next time you run the loop, you do add the digit, which gives you this set of brackets, and then you double it, which means that 2 multiplying for the bracket, and so on. So that is the most, in my view, it's the most elegant way of do this conversion from binary to decimal. So now let's look at the other aspect. Let's write the algorithm for converting from decimal to binary. We're going to use the division algorithm. So to convert 38, which is a decimal number, into binary, we divide 38 by 2. Okay, so we start 38 divided by 2, that's 19, remainder 0. Then we do 19 divided by 2, that's 9, remainder 1. 9 divided by 2, that's 4, remainder 1. 4 divided by 2 is 2, remainder 0. 2 divided by 2 is 1, remainder 0, and then 1 divided by 2 is 0, remainder 1. I just done that example so that we tap into that to write the generic algorithm. So, what's important? First, we need the number, which is n, and we need the digits. The digits, they're going to be our binary digits. I'm going to start with the empty word there. So this is going to be the empty word. Empty word. Okay. We have the number saved in the variable n. We have the digits containing just an empty word. And then every time we do a division and capture a remainder, we're going to save the new remainder in that word. Let's call Q the integer part of the division of the number. So it's going to be the integer division of n by 2, okay? So the integer part. And now we need to extract the remainder. To extract the remainder, we do the number minus twice the q, okay? The number minus twice what we've got, that's our remainder, I call it r. So the remainder is our digit, okay? And now we're going to carry on doing the division. So let's make n equal to our q. N is our q now, and we just loop. We should just now loop up there. But you've noticed we're not keeping track of the digits. We need to save the digits, so we need somewhere to say, let's write the digit r to the left of the word digits. Okay? That's how we keep track of the digits. Now, did we do it the right way around? Is it left or right? So let's look at our example. The first remainder, it's going to be the rightmost digits, and the last one is the leftmost. So the number in binary is going to be like this, and we went that way. So every new digit is written to the left of the digits we had so far. Okay, so those are the steps, and we can write that into step 1, step 2, step 3, step 4, step 5. How do we stop? We stop, let's look at our sums. We stop when we had quotient 0. If the quotient is 0, we stop, and we have to print out the value. So that means that here I would say if q is 0, we print digits and stop, else we have to go back there, okay? How do we do that? You can name all these steps into step 1, step 2, step 3, step 4, step 5, and redirect here on the else to step 2, okay? We have an algorithm that stops. I'll just give you a very brief overview of task 2. On task 2, you are to write algorithms of adding up 2 two-digit numbers in binary. You are to do subtraction as well, and multiplication. I'll put in boxes for all the digits we need to account for. And the main thing to consider is that if you're adding these two numbers, it's all very good if it's 1 with 0 or 0 with 1. You get one answer there, but you need to account that if you have 1 plus 1, you're going to have 1 0 as an answer, which means you need to have a 0 here and a 1 that it's carried. So you need to take into account that you need to have a variable for carries, okay? So that's a pointer there. On subtraction, you need to take into account the borrowing that goes on if this digit here is too small for this one, meaning if you've got a 0 here on top and a 1 below, then you will need to borrow from over there. So you will need to change the digits of the numbers as you go along. With multiplication, we need to take into account that the results are going to be here, possibly like this, and then when you multiply this guy here by the top number, you'll move place value. So you need to take into account that, okay? So you're not going to write anything there, but you're going to move place value. So that's a few pointers of what your algorithms need to take into account. We've now looked at operations in binary, and you know how to add, subtract and multiply numbers in binary. You are now to write down the algorithms for these operations using two-digit numbers, and I would like you to write it the best you can, in as much detail as you can, as close as to a computer scientist as you can. As to how this fits in computing, keep an eye out for logic, as these tools together will allow you to build your own simple computer. You now do binary back to front, and some of you may be dreaming of making a binary clock. We will work through the details of two more bases, base 8 and 16. I would like you to focus on generalizing these examples onto working with any other base. I mean, I want you to think about how you use base 3, base 4, base 67, any base. So follow these examples and make your own notes and form your own theory of how to write numbers and perform arithmetic in any other base. Base 8 is also called octal, from the Greek word for 8. There are 8 digits, and these are 0, 1, 2, 3, 4, 5, 6, and 7. But what are the place values? I mean, say the first 3 place values. You can answer that in the in-video quiz. The octal number 123, which I will write 123 with a little 8 for avoidance of doubt. This is the subscript, which means that it's written in base 8. This number uses 3 place values worth 1, 8, and 64. As we start with the place value 1 on the right and multiply by 8 to get to the next place value to the left. The place values are consecutive powers of 8, starting from 1. The digit 3 is for units, the digit 2 is for 8s, and the digit 1 is for 64s. We use this to write the expanded form 1 times 64 plus 2 times 8 plus 3 times 1, which gives 64 plus 16 plus 3, and totals 83. And that means that 123 in octal is written as 83 in decimal. The number 7701 in octal uses 4 place values worth 1, 8, 64 and 512. The first 4 powers of 8. The leftmost 7 is on the position for 8 cubed, so 512. The next 7 on the 64s, the 0 on the 8s, and the 1 on the 1s, giving the expanded form 7 times 8 cubed plus 7 times 8 squared plus 0 times 8 plus 1 times 1, which equals 7 times 512 plus 7 times 64 plus 0 times 8 plus 1 times 1, which equals 3,584 plus 448 plus 0 plus 1, totaling 4,033. And so we write 7701 in octal is 4,033 in decimal. Let's get going with another base 16 or hexadecimal. Let's work out the place values. The place values go up by a factor of 16 every time. So we write numbers with place values running from right to left, starting at 1, then 16, then 256, which is 16 squared, then 4096, which is 16 cubed, then 65,536, which is 16 to the power of 4, but also 256 squared, and so on. In the in-video quiz, I asked you to relate powers of 2, powers of 8, and powers of 16. Later, we will see why this is important. With base 16, we need 16 digits. That's great. We can go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, but we can't go 10, 11, 12, 13, 14, 15. Well, we can, like the Babylonians did, but that would be very confusing. You know, what does 1115 mean? Does it mean 115 really? Or 111.5? Or 1115? Or something else? To remove this ambiguity, we use symbols A, B, C, D, E, and F to stand for the numbers 10, 11, 12, 13, 14, 15, respectively. So 1115 is BF in hexadecimal, and 1115 is 11F. Let's look at the value of these numbers. You know how it goes. We have to note down the place values. Follow me on this one. We write the place values and write the number in the expanded form. So BF equals 11 for B times 16 plus 15 for F times 1. And that gives 176 plus 15, which totals 191. As to 11F, that is 1 times 16 squared plus 1 times 16 plus 15 times 1, which equals 256 plus 16 plus 15 and totals 287. Very different numbers. Let's see all of this in action with 2 examples. Let's write the number 179, that's a decimal number. Let's write this into octal. We're going to use the division algorithm. We're going to divide by 8 over and over again and taking note of the remainders, and those will be the digits of the number in octal. So on our calculator, 179 divided by 8, that is 22. 179 divided by 8, that is 22, integer part. Let's work out the remainder. So we take the 22 times by the base, which is 8. We got 176. That, taken away from 179, leaves remainder 3. And now we divide the 22 by 8. 22 divided by 8. We got 2, and the remainder will be 2 times 8, which is 16. 16 to 22 is 6. And now we divide 2 by 8, which is 0, remainder 2. The first remainder is the rightmost digit, so the number is 263 in octal. We could, instead of using the division algorithm, match the powers of 8, which is really essentially what we've done here, but let's look how that seems. You would write the powers of 8, 1, 8, 8 times 8, 64, and the next one, 64 times 8, 512. 512 is too large for 179, so we don't need it. And now we would write 179 as multiples of these powers and then add them all up. So how many 64s go into 179? Well, 179 divided by 64. That is 2 64s. And let's see how much is left now. So 64 times 2 is 128. We do 179, take away that 128. We've got 1, we've got 5. So we've got 51 left. We need to make 51 out of 8. How many 8s? Well, we got now 51 divided by 8. That's integer part 6. 6 times 8, 48. So we got 51, take away the 48. And we are left with 3, and so 3 1s make the rest of the number. Of course, we get the same result as we got using the other method, and we're essentially doing divisions by 8, but in this case we're doing divisions by 64, and then by 8, and then by 1. Let's now look at an example in hexadecimal. We're going to write the same number, 179, in hexadecimal. Hexadecimal is base 16, so we're going to divide by 16 over and over again. So we're going to do 179 divided by 16, and it does speed up stuff if we use the calculator. Divide by 16, and that is 11, and let's work out the remainder. We do 16 times 11, which is actually 176, we should know that, 176. So 179 minus 176 is remainder 3. And now we do 11 divided by 16, which is 0 remainder 11. So the remainders have to be up to 16, but never 16. Right, so here's our digits. So if we don't remember what is A, B, and C, 9 is the last numerical digit, A is 10, B is 11, C is 12, and so on. Well, this is going to be a B, and this is a 3. So our number, remember, the first remainder is the rightmost digit, so we have B3 in hexadecimal. Let's also look at how we could do this with approximating by powers of 16. In this case, it's very, very close to what we did. We start with 1, 16. 16 squared is 256. And we make 179 using these numbers. 256 is too large, we're not going to need. So the question is, how many 16s fit into 179? Well, we would do 179 divided by 16, which we've done for the previous calculation. So it's going to be 11 16s. And then we have remainder 3. So 11 16s, 16 times 11, 176, so we got remainder 3, and that 3 is made of 3 1s. So like we did before, this is a B, that's a 3, so 179 is B3 in hexadecimal. You have now all the tools to work in any number base. We just looked at the place values for octal and hexadecimal, and we can translate between these bases and decimal. Octal uses 8 digits from 0 to 7, and hexadecimal requires 16 digits, so we use all the digits 0 to 9, followed by letters A to F to mean the values from 10 to 15. Next, we will look at fractional numbers. Have a think of what the place values should be for fractional numbers written in octal and hexadecimal. To fully appreciate the upcoming videos, start extending the algorithms for operations in binary into these new bases. and I asked you to think about steganography. I haven't forgotten that. We're now looking at how to work with fractional numbers in hexadecimal and octal. Let's remind ourselves of the place values in octal. The integer place values start with 1 and then multiply by 8, multiply by 8 again. So 1, 8, 64 and so on. For the fractional part, like we did in binary, we start dividing by the base. So we're going to divide 1 by 8 and then divide by 8 and divide by 8 and so on to get all the fractional place values. I'll write this down. So the integer place values, we wrote 1 and then 8 and then 64, and if you carry on you would get to 512, just reminding ourselves that these are powers of 8, so 8 to the 0, 8 to the 1, 8 squared, 8 cubed. It gets really big with powers of 8, doesn't it? For the fractional part we're going to divide by 8, so we're looking at 1/8, then 1 over 64, and 1 over 512. The powers 8 to the minus 1, 8 to the minus 2, 8 to the minus 3, and so on. I'm just going to write what these guys are in decimal. So 1/8 is 0.125. 1 over 64, we're looking at 0.015625. And the 1 over 512, 0.001953125. I'm somehow feeling a little bit discouraged of adding these numbers by hand, but hey, that's what calculators are for. So we're going to look at an example of how to translate a number that is in octal into decimal. So there we go. Say our number is 0.72. This is a fractional number in octal. That's our reminder there with a little 8. This means that the 7 is in the place value for the 1 over 8 and the 2 is in the place value for the 1 over 8 squared. Okay, so all I'm going to do is to say I've got 7 of that lot of 1/8. And I've got 2 of that lot of 1 over 8 squared. So I've got 7/8 plus 2 over 64. And adding it all up, that's 29 over 32, which is 0.90625 in decimal. So that is fractional octal to decimal. Let's do the reverse now. Let's look at a fractional decimal number and write it in as a fractional in octal. Say we've got the number 0.515625. That's our decimal, nice and long. I feel discouraged to compare this number to the powers of 8, the negative powers of 8. So we're just going to do the algorithm of just multiplying by 8 over and over again and taking the integer part as the digit. Let's do that. So 0.515625 times 8, and we're doing times 8 because that is octal. Okay, in binary we multiply by 2, in octal we multiply by 8. Calculator says 4.125. Now, the integer part of this result is 4. That's going to be our first fractional digit in octal. So 0.4, and that 4 comes from that integer part. Now remember what we did in binary, we took away that integer part and worked with what was left, the fractional part. So from here we take away the 4, which means 0.125, that's what we're left with. And now multiply by 8. Multiply by 8 and surprise, surprise, we get 1. So that is the next octal digit. And we stop because this one has no fractional part. So actually it's an integer number. So integer. And we stop. Yeah, I'm relieved I don't have to do more multiplications of 8 here. So I'll stop, and so this is my number in octals. Just a reminder where that one came from. That one there became that one there. Okay. Let's look at hexadecimal next. Just a reminder, hexadecimal place values are powers of 16. We'll write them. So we have 1, 16, and then 16 squared, which you remind yourself, 16 squared is 256. 16 cubed, 4096. Those are the integer ones, so that's 16 to the power of 0, 16 to the 1, 16 squared, 16 to the cube. We're going to need the fractional parts with the negative powers of 16 for this bit. So we're going to divide by 16. So 16 to the minus 1, which is 1 over 16 that writes down as a decimal as 0.625. Next, 16 to the minus 2, which is 1 over 256. Calculator says we get 0.003906250, and just carry on like that, 16 to the minus 3 and so on. You get the picture. So these are the place values. So for fractional numbers in hexadecimal, we're going to work with these place values here. Let's look at an example. Right, let's transform this number here, 0.9b, which is a hexadecimal number. Let's remind ourselves what these b's and a's and so on mean. The digits in hexadecimal, we have 16 digits to work with, and those are 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then A for 10, B for 11, so 10, 11, 12, D for 13, E for 14, F for 15. That's it. Now, I recommend that when you do your working, right at the top of the page, the digits, so you don't confuse what A, B, C, and D, and so on are worth. So there we are on the top line. So we're going to write what the place values are, and we're going to work out what this number is in decimal that way. So we just did this. The 9 stands for the 1 over 16, and that B is on the position for the 1 over 256. That means that this number is 9 times 1 over 16 plus 11 times 1 over 256. And just a reminder again, this 11 here is because of the B, and this 9 here is the other digit on the original number. So calculator to the rescue, adding up these numbers, it comes out to 155 over 256, which is no more, no less than 0.60546875, and that is in decimal. Now, if your number had an integer part and a fractional part, you work out what the integer part is in hexadecimal doing the division by 16 and take the remainders algorithm. Work out the fractional part using the algorithm I'm going to show you now, which is the other way around, multiply by 16 and take the integer part as the digits. So the example I've got for us is 0.96875. That's a decimal number. We want to write this in hexadecimal. We're going to start by multiplying by 16 because that's the base 16. Multiply that and we get 15.5 precisely. And this is the integer part. This is going to be our first hexadecimal digit. Now remember, 15 in hexadecimal is f. So we're going to write it here, 0.f, that f from that 15. From 15.5 here, we're going to take away the 15 and just work with the fractional part. So 0.5, and then we multiply by 16. And that is 8. 8 is going to be the next digit. We're going to be there, and we stop because 8 is an integer. There's no fractional part to continue. Yeah, we're still happy. Cool. So that means that that fractional number in decimal is written as 0.f8 in hexadecimal. Earlier, when you played with powers of 2, 8 and 16, you probably noticed that there is a pattern between powers of 2 and powers of 8, and a pattern between powers of 2 and powers of 16. We will use that pattern to move between binary and octal. We will use it too to move between binary and hexadecimal, and between hexadecimal and octal via binary, without going through decimal. The key thing to note is that 2 cubed is 8, and that means that one octal digit can be expressed as a binary number using up to 3 digits. Note that 7 in decimal is 111 in binary. Take this moment to write the octal digits 0 to 7 as 3-digit binary numbers. Answer in the in-video quiz with your results. Let's write the number 1, 111, 011, 001, the binary number, in octal. We count the number of digits. There's 10 binary digits. And starting from the smallest place value, the right-hand side, we group the digits in 3s. So we start with a 1, a 111, a 011, and a 001. And now take each group of 3 binary digits as a number of its own right. So 1, then 111, then 011, then 001, and write these individual numbers in decimal, which is exactly 1 octal digit. It is possible because they have at most 3 digits. And that gives 1, then 7, then 3, and then 1. And these numbers are the digits in octal, giving 1, 111, 011, 001 binary, written as 1731 in octal. In short, we group the binary digits in 3s and replace each group of 3 digits as 1 octal digit, which is the decimal conversion of the 3-digit binary number, using the same conversion you used in the in-video quiz earlier on. Remember that the whole point of this section is to do a direct conversion without converting to decimal. But we use decimal only at the level of groups of 3 digits to do immediate octal, rather than converting the whole binary number to decimal and then the whole decimal number to octal. You can try the 2 methods and appreciate how much quicker and elegant the direct binary to octal method is. Let's start now with the octal number, 4036. And let's transform it into binary using the idea of 1 octal digit being a 3 4-digit binary number. So 4 is 100, 0 is 0, but we need to write it as 000 because we need to have 3 digits. 3 is 11, so we do 011. 6 is 110. And now we write the binary strings in the same order: 100, 000, 011, 110, and we have that 4036 in octal is written in binary as 100, 000, 011, 110, and we're done. The key thing to note is that 2 to the power of 4 is 16, and that means that one hexadecimal digit can be expressed using up to 4-digit binary number. Note that 15 in decimal writes as 1111 in binary. Take this moment to write the hexadecimal digits 0 to 9, 8 to F as 4-digit binary numbers. Let's write the number 1, 111, 011, 001. That means we have 11, 1101, 1001. And now we take each group of 4 binary digits as a number of its own right. We have 11, then 1101, then 1001, and write these individual numbers in decimal, and then as one hexadecimal digit. And it is possible because they have at most 4 digits. So we get 3, then D for 13, then 9. And these numbers are the digits in hexadecimal, giving that 1, 111, 011, 001 in binary is written in hexadecimal as 3D9. In short, we group the binary digits in 4s and replace each group of 4 digits as one hexadecimal digit, which is the decimal conversion of the 4-digit binary number, using the same conversion you used in the in-video quiz earlier. Again, remember that the whole point of this section is to do a direct conversion without converting to decimal. But we use decimal only at the level of groups of 4 digits to do immediate hexadecimal, rather than converting the whole binary number to decimal and then the whole decimal number to hexadecimal. Like I said earlier, you can try the 2 methods and appreciate how much quicker and elegant it is to do the direct binary to hexadecimal conversion. Let's start now with a hexadecimal number, 9F0C, and let's transform it into binary using the idea of one hexadecimal digit being a 4-digit binary number. So let's write each hexadecimal digit as a 4-digit binary number. So 9 is 1001, F, which is 15, is 1111, 0 is 0, but we write 0000, and C, which is 12, is 1100. And now we write the binary strings in the same order. And so 1001, 1111, 0000, 1101. And we have the 9F0C, the hexadecimal number, is written in binary as 1001, 1111, 0000, 1101. And we're done. To translate between octal and hexadecimal, we go via binary at digit level. It is really only a regrouping of digits. We use the methods we have just covered. So 745 in octal is 111, 100, 101 in binary, because 7 is 111, 4 is 100, and 5 is 101. So 111, 100, 101. And now we regroup all these binary digits as 4s, giving 1, 1110, 0101 in binary. Remember, we start with the smallest place value for the grouping. And get writing these groups of digits into a hex each. Now we know the 1 in hex is 1, 1, 1, 1, 0 in hex is E, 0, 1, 0, 1 in hex is 5, and we write them one after the other and get 1, E, 5 in hexadecimal, which equals 1, 1, 1, 1, 0, 0, 1, 0, 1 in binary. Easy peasy. AB3C is 1, 0, 1, 0, 1, 0, 1, 1, 0, 0, 1, 1, 1, 1, 0, 0 in binary. Because A is 1, 0, 1, 0, B is 1, 0, 1, 1, 3 is 0, 0, 1, 1, and C is 1, 1, 0, 0. And yes, we need the leading zeros, making 3 as 0, 0, 1, 1, and not just 1, 1, because we need to stick to the length of 4. So now we regroup these digits in trios, when we have 1, 0, 1, 0, 1, 0, 1, 1, 0, 0, 1, 1, 1, and 1, 0, 0. And we write these guys in decimal, which is octal, and we get 1, 2, 5, 4, 7, 4 in octal. And we're done. The whole idea is 1 octal, 3 bits. 1 hexadecimal, 4 bits. And I'm using bits as binary places. The same algorithm applies to fractional numbers, but we have to think carefully of how to group the digits. Let's look at some examples. A.4c in hexadecimal, let's convert it to binary. 1010 dot 0100 1100. We're going to tidy up the zeros at the end. 1010 dot 010011. Let's do another one. 9.f. Let's convert this hexadecimal into octal. It's 1001 dot 1111. Then 1001 dot 111100, and notice how the grouping was done here, giving 11.74 in octal. Let's do the binary 1.01 into hexadecimal. We write 0001 dot 0100, and that is 1.4 in hexadecimal. Let's do 10.1101, a binary number, into octal. We're going to add zeros, 010.110.100, and that is 2.64 in octal. This image has a hidden message inside. Can you see? Probably not. I'm not talking about a deeper artistic meaning or a metaphor. I'm talking about concealing a message within the information that makes this picture render on your screen. Everything is number, and this image is made of numbers that describe each pixel. The process consists of using the pixel information to conceal a message. This is the image before the message was concealed. And now let's look at both of them side by side. Can you now tell what the message is? No. Do you suspect something is hidden in it? I don't. The main idea is to use the color codes to hide the message. And these are the RGB codes of the original image. On each row, we got a red, green, and blue color value, and we go along all the columns and we complete a row, then we go to the next row and so on. So we've got, on the first row, we've got 255, 0, 0, that's 1 pixel. 255, 192, 0, that's another pixel on that row, and so on and so on and so on. Here is the secret message. I haven't told you how the message was created. I'll go into that later. The idea is to fit the numbers of the message in each pixel. So we group the numbers in the message in rows with 7 numbers on each row, as we have 7 pixels on each row, like this. And here is the clever bit. Each pixel has 3 numbers for red, green and blue colors, for RGB colors. The numbers in the secret message go up to 6. So we can write each number in binary using 3 digits. And then we hide each binary digit in one color code, red, green, blue. I'll show you how. We write the first message number into a 3-digit binary number. So 4 is 100. And we hide the digit 1 in the red value of the pixel, the second digit 0 in the green value of the pixel, the third digit 0 in the blue of the pixel. 255 is an 8-digit binary. It's 1111, 1111, and we replace the rightmost digit by the 1, giving the same number, 111, 11111. It's the same number in this instance. 0 is an 8-digit binary, 0000, 0000, and we replace the rightmost digit by the 0 of the message, giving 00000000. So far they all look the same. With the other 0, still an 8-digit binary with 8 zeros, and we replace the rightmost digit by the 0, giving another array of 8 zeros. That means that the first pixel has codes for red 1111, 1111, which is 255. Green will be 00000000, which is value of 0, and blue 00000000, which is 0. For the second number from the message, 1, we write it as 001 in binary. We use the first digit 0 for the red value of the pixel, the second digit, which is 0, in the green value of the pixel, the third digit 1 in the blue value of the pixel. So 255 is the 8-digit binary 11111111. We replace the rightmost digit by the 0, giving 11111110. 192 in binary is 11000000, 8 digits, and we replace the rightmost digit by the 0, giving 11000000. 0 in binary will be 8 zeros, and we replace the rightmost digit by the 1, giving 00000001. So the second pixel becomes a pixel with color codes red 11111110, which is 254, green 1100 0000, which is 192, and blue 00000001, which is 1. The third number from the message is 4, which is 100, and we're going to use the first digit 1 in the red value of the pixel, the second digit 0 in the green value of the pixel, and the third digit 0 in the blue value of the pixel. And again, 255 is the 8-digit binary 11111111, and we replace the rightmost digit by the 1, giving 11111111. For green, 255 is 11111111, and we replace the rightmost digit by the 0, giving 11111110. For blue, 0 is the 8-digit binary 000000, 0, 0, 0, 0, and we replace the rightmost digit by the 0, giving 0, 0, 0, 0, 0, 0, 0, 0. So the third pixel becomes red 1, 1, 1, 1, 1, 1, 1, 1, which is 255, green 1, 1, 1, 1, 1, 1, 1, 0, which is 254, and blue 0, 0, 0, 0, 0, 0, 0, 0, which is 0, and so on. The final image with a message hiding in it has the pixel information as follows. And it looks pretty much like the original. Now, to recover the message, we undo the process. We write the color codes in binary, extract the rightmost digit, and use 3 consecutive digits to write a number in binary. Then translate this number in binary to decimal. We would have recovered the message intact, and it will be this one, just like we started. You can try it yourself. The secret message was created by mapping the characters and the numbers. I used this table. And then we group the numbers in the message in pairs so we can recover the characters and read the message below. The same concept can be used to hide an image inside an image. We're not going to use a table of letters. This time we're going to hide a pixel color code inside a pixel color code. In the example we just saw, we used the unit digits of the binary number for each color to hide one binary digit of the hidden message. Now, in this new process, we will use the least significant binary digits of the color to hide the color code for the hidden image. Let's see how many we need to use. This will be the process you will follow for the next task. To make the most of this video, I suggest you pause it during the calculations and try it for yourself before seeing my solution. Here is the process, both in binary and in hexadecimal. Let's do binary first. Say I wanted to hide the pixel information RGB 162, 200, 140 on the pixel with codes 255, 150, 20. This is the code for the original image. We do it in this way. The red of the original image is 255, which is 1111, 1111 in binary. The least significant digits are 1111, which we will ignore. The red of the hidden image is 162, which is 1010, 0010 in binary. The most significant digits, the leading digits, are 1010. The new red value will be 1111, 1010. So we took the most significant digits of both colors, but made the digits of the hidden color of less significance. That means we put them at the end of the number. So red will have the value 1111, 1010, which is 250. Let's do it for green. The green of the original image is 150, which is 1001, 0110 in binary. The least significant digits are 0110, which we will ignore. The green of the hidden image is 200, which is 1100, 1000 in binary. The most significant digits are 1100. So the new green value will be 1001, 1100. So we took the most significant digits of both colors, but made the digits of the hidden color of least significance. So the green color code will be 1001 1100, which is 156. The blue of the original message is 20, which is 0001 0100 in binary. The least significant digits are 0100, which we will ignore. And the blue of the hidden image is 140, which is 1000 1100 in binary. The most significant digits are 1000. So the new blue value will be 0001 1000. We took the most significant digits of both colors, but made the digits of the hidden color of least significance. So the blue color value will be 0001 1000, which is 24. So the pixel of the image that contains the hidden image has RGB codes 250, 156, 24. These two shades are very similar. Can you tell the difference between the shade of the original image and the shade of the image with a hidden pixel? The difference is very subtle, and we would do this process for every pixel of the image. How well can the secret image be retrieved? Let's see. Let's do the inverse process. For a pixel with RGB values of 250, 156 and 24, this is from the image that has an image hiding inside, the red code is 250, which is 1111, 1010 in binary. The least significant digits are 1010. This is where the hidden image is. We use these to be the leading digits of the hidden color value. So we write 1010, 0000. We then convert this number, 1010, 0000, to decimal, which gives us 160. And so the hidden value for red is 160. For the green code, which is 156, written as 1001, 1100 in binary, the least significant digits are 1100. That's where the hidden image is. The hidden color value is 1100, and we put 4 zeros at the end. So 1100, 0000. We convert this number to decimal, and so 1100, 0000 is 192, and that is the hidden value for green. For blue, we have 24, and this is 0001, 1000 in binary. The least significant digits are 1000, so the hidden color value is going to be 1000 with 4 zeros at the end, so 1000, 0000. We convert this number to decimal and we get 128. The hidden color value for blue is 128. So the RGB color values for the hidden pixel are 160, 192, 128. Now let's do this process in hexadecimal. Say I wanted to hide the pixel information, the RGB code 162, 200, 140 on the pixel with RGB code 255, 150 and 20. So this is the one from the original image. We do it in this way. It is the same process, but we're doing it in hex. The red of the original image is 255, which in hexadecimal is FF. The least significant digit is F, which we will ignore. The red of the hidden image is 162, which in hexadecimal is A2. The most significant digit is A. So the new red value will be FA. So we took the most significant digits of both colors, but made the digits of the hidden color of less significance. So the red value will be FA, which is 250. For the green of the original message is 150, which is 9, 6 in hex. The least significant digit is 6, which we will ignore. And the green of the hidden image is 200, written as C8 in hex. The most significant digit is C. So the new green value will be 9C. We took the most significant digits of both colors, but made the digits of the hidden color of less significance. So the green color code will be 9C, which is 156. The blue of the original message is 20, which is 14 in hex. The least significant digit is 4, which once again we will ignore. And the blue of the hidden image is 140, which is 8C in hex. The most significant digit is 8. The new blue value will be 18, and we took the most significant digits of both colors, but made the digits of the hidden color of less significance. So the blue value is 18 in hexadecimal, which is 24. That means that the pixel of the image that contains the hidden image has RGB codes 250, 156, 24. The two shades are very similar. Can you tell the difference? And we would do this process for every pixel of the image. To retrieve the hidden image, we go pixel by pixel once again. Let's take the pixel with RGB values 250, 156, 24, which was the end result of the process we've just followed. The red is 250, which is FA in hex. The least significant digit is A. We use this as the leading digit of the hidden color value, which in this case is A0. Converting A0 to decimal gives us the hidden value of 160 for red. Let's look at green. The code is 156, which is 9C in hex. The least significant digit is C, so the hidden color value becomes C0. Converting C0 to decimal gives us the hidden value of 192 for green. As to blue, the value 24 is 18 in hex. The least significant digit is 8, and so the hidden color value is 80. We convert 80 to decimal, giving us a hidden color value of 128 for blue. So the hidden color value we just recovered is RGB 160, 192, 128. Compare these RGB color values to the color values of the original image. There is a slight difference, but it's not that much. Here's an example of an image and the secret image. After hiding the secret image, the original image changes to this. It's not that different. When we follow the extraction process, the secret image comes out like this. It's not exactly the same as we started, but it's close enough to tell what it is. Great news! We can perform arithmetic in octal and hexadecimal too. I'll show you. Say we're adding up the octal numbers 7, 1 with 6, 5. We're going to put them in columns like we did with binary. So 7, 1, 6, 5, all lined up. We're adding up these numbers column by column. So over here, 1 plus 5 is 6. 6 is still less than 8, which is our base 8. So it is a valid digit, so 6. Then 7 plus 6, that's more than 8. So 7 plus 6, it's a 13. And 13 in octal, it's written as, okay, let's work it out. It's 8 plus 5, so that means it's going to be a 1 and a 5 in octal. So we write a 5 here, and we take 1. That 1 is going to carry to the next place value, which just happens to be empty, and therefore we just write it there. Okay? So the result is 156 in octal. That's what it adds up to. Let's do a subtraction. In a similar fashion, 7, 1 in octal, take away 2, 4 in octal. We line them up. We leave some space at the top for borrowing digits if needed and replacing some of the place values. So we start with 1 take away 4. We can't do it straight away, 1 take away 4, because 1 is too small. So we're going to look at here, we got 7. We're going to borrow 1 from that place value, because 7 is 6 plus 1. So we're going to leave a 6 there. We're going to borrow 1 over here, meaning we're going to replace that with a 6, and we're going to put a 1 here. So we got 1, 1, take away 1, 4. I'll just rewrite that more neatly. So that 1 there becomes a 1, 1. And now we do 1, 1 in octal, take away 4. 1, 1 in octal, take away 4 in octal. Let's remind ourselves what 1, 1 means. It's 8 plus 1, and now take away 4. And so we've got 9 take away 4, which is 5. Therefore, we got a 5 there. Okay? And now we move on to the next place value. We've got 6 take away 2. So here 6 take away 2, and that is 4 in octal. So the result is 4, 5 in octal. Multiplication next. We're multiplying 1, 7 in octal by 1, 2 in octal. Line them up. Okay, so we're going to do like before. We multiply this 2 by the 1, 7, write the result over here, and then we multiply this one by the 1, 7, write the result here, shifted 1 place value. That's what I'm going to do. But we're going to have to go back and forth with decimal to interpret the multiplication digit by digit in decimal and octal. I'll show you. Okay, right, so 2 times 7. 2 times 7 is 14. Now, 14 is not a number we can use in octal straight away. We need to convert to octal. It's greater than 7. So this is 8 add 6, which makes 1, 6 in octal. So we put the 6 here, and we have a 1 that is going to hang around there. Now we do 2 times the 1, this 2 times that 1, which is just 2. And we do that 2 added with this 1, it's going to be 3. 3. Now, we're going to multiply, we're going to shift things 1 place value, and we're going to do 1 times 7, which is 7, and 1 times 1, which is 1, and add them up. So we got 6, 3 plus 7 is 10, 10 in octal is 8 plus, so 8 plus 2 means is 1, 2 in octal. So we put a 2 here and carry the 1 over there, and now 1 plus 1 is 2, which is valid in octal. So that means 2, 2, 6 in octal. And now let's look at the similar operations in hexadecimal. We're going to add up two numbers in hexadecimal. We're going to have the number AB in hexadecimal added with 25 in hexadecimal. Let's just remind ourselves what the letters mean. So after 9 comes 10 is A, 11 is B, C is 12, D 13, E 14, F is 15. And we're going to line up the numbers as before. A, B, 2, 5, add them up. We're going to do column by column. We've got B plus 5. B plus 5, we're looking at 11 add 5. That is 16, and 16 in hexadecimal is going to be 1, 0. So I'm going to write 0 here and 1 on that column. And now I need to add up the 1 with the A with the 2, and that is 1 plus 10, because A is 10 plus 2. That makes it 13, and 13 is the digit D in hexadecimal. So I'll write D there. So that means that AB in hexadecimal add 25 in hexadecimal equals D0 in hexadecimal. And in a similar fashion, we're going to do a subtraction. We have for AB in hexadecimal, take away 1F in hexadecimal. So AB and 1F all lined up, take away. So column by column, we're going to B take away F. Now, let's remind ourselves again, B stands for 11, B is 11, and F is 15. We can't really do 11 take away 15, we're going to have to borrow from the next column. So A is worth 10, so we're going to say A, which is 10, is the same as 9 plus 1. So we're going to replace that A by a 9, and we're going to put 1B in this column. And now 1B in hexadecimal means 16 add 11 from the B, that's 27. And then 1B take away F means 27 take away 15, because F is 15. And that gives us 12 as a result. 12 is letter C in hexadecimal. That means I've got C there. And now all I'm left to do is 9 take away 1, which is 8. That means that AB in hexadecimal take away 1F in hexadecimal equals 8C in hexadecimal. One more, we've got a multiplication. All right, so AB in hexadecimal times 1, 1 in hexadecimal. AB 1, 1, let's multiply. So we're going to do 1 times B, which is B, 1 times A, which is A, and then we're going to write 1 times B, which is B here, and A, and add them up. So B, A plus B is 10 plus 11, which is 21, and 21 is 16 plus 5, which makes it 1, 5 in hexadecimal. And put a little 1 there, and now we do A plus 1, which is B. So A plus 1 is just B, and the result of this sum is B, 5B in hexadecimal. So we can use the same ideas of adding, subtracting, and multiplying from decimal and binary into octal and hexadecimal. You can even extend it to other number bases. We have worked in great detail on binary, octal, and hexadecimal. I just want to show you a few examples of how we extend the same techniques into working in any base. The main thing to bear in mind is that in, say, base 3, we're using digits from 0, 1 and 2, so digits up to 3. If it's base 5, 0, 1, 2, 4, base 60, up to 59 and so on. That means that when we are converting from decimal to any base, say base 3, we keep dividing over and over again by 3 and taking note of the remainders. For the fractional part, we will multiply by 3 over and over again and take note of the integer part. And that's how we extend that algorithm to any base. With operations, you'll see that it's very similar. I'll stop talking and I'll show you some examples. Say we have 1201 in base 3. What is this number in decimal? Well, base 3 is going to use place values that are powers of 3, starting from 1. So we'll write those up as a reminder. I have 1, 3, 3 squared, which is 9, and 3 cubed, which is 27. That means we go straight to the expanded form, which is 1, the digit, times the 27, plus 2, the digit, times the place value 9, plus 0 times the place value 3, plus 1 times the place value 1. And that was a number in ternary, base 3, because the digits were 1, 2, 0, 1. There were no digits 3 or greater. Now we have the expanded form, we just do the calculation and get on with it. So we've got 27 plus 18 plus 1, that makes 30, 40, 46. And so 1201 in ternary is 46 in decimal. Let's look at changing from decimal to base 5. Let's do 45.2. 45.2. I'm allowed to say 45 because it's decimal. And we want to write this into base 5. This is the division algorithm. Well, kind of. It is the division algorithm for the integer part, for the 45, and it's going to be the multiplication by 5 algorithm for the 0.2. So let's do it separately. 45, we're going to divide by 5, because it's base 5, and that is 9 remainder 0, and then 9 divided by 5, it's 1 remainder 4, and then 1 divided by 5 is 0 remainder 1. That gives me that the digits for 45 in decimal is written as, remember the first remainder is the left remainder is the rightmost digit. So the 1 is going to be the leftmost, so 140 in base 5. Now let's do the fractional part. So 0.2 in decimal. We're going to multiply that by 5. 0.2 times 5 is 1. 1 is the whole part, so that's going to be the first digit. We take away the 1, we have 0, and so we stop. So this is fractional part is 0, so we stop. And that means that 0.2 is going to be written as 0.1 in base 5, which is okay, because 0.2 is a fifth, and 1/5 is the first fractional place value for base 5. So putting it all together, 45.2 is 140.1 in base 5. So let's look at an example of addition. Let's do addition in base 11. 7.6 add 0.6 in base 11. What we're going to do, stack the numbers one on top of the other, do the addition. 6 plus 6 is 12. 12 is one more than our base, so 12 in base 11. So 12 in base 11 is going to be 111 plus 1. Okay, so it's going to be 1, 1. That means I put a 1 here, the units 1, and this other one for the 11 place value is going to go there on top. And I've got 1 plus 7 plus 0. That makes it 8. 8 is still less than 11, so it's a number we are allowed to use. And there we go. The result of this sum is 7.6 plus 0.6 in base 11 is 8.1 in base 11. I'm going to do subtraction now, base 5. 2.3 take away 1.4, and that's base 5. Stack the numbers, one on top of the other, place values aligned, we're going to subtract. And now we have, column by column, we got 3 take away 4. Too small, we're going to have to borrow. Now, what we're going to borrow? We have a 2, we're going to split that. That's a 1 plus a 1. We're going to lend it to the 3, so I've got a 1, 3 over there. And now I have that 1, 3, which is a 1, 3 in base 5. So it's a 1, 3 in base 5. What is that? 1, 3 in base 5 is 5 plus 3, which is 8. So really I'm doing 8 take away 4, which is 4. And now the next column, I've got 1 take away 1, which is 0. And so the result is 0.4 in base 5. Does that work? We can always check. Let's add them up. If we do 1.4 add 0.4, what do we get? 4 plus 4 is 8, but 8 in base 5 is going to have to be written using the help of 5 plus 3. So 8 is 5 plus 3 like we did earlier, and that means it's going to be a 1 on the place value of 5 and a 3 on the place value of 1. So I write the 3 here and the 1 on top, and now I add the 1 with the 1, which is a 2. And that's correct. Now let's look at one more example, multiplication in base 7. 1, 2, base 7 times 6, 0, base 7. Let's do it. 1, 2, 6, 0. 0 times 2 is 0. 0 times 1 is 0. And now 6 times 2 is 12. 12, but 12, what is that in base 7? Well, let's split the 12 as a 7 plus something. So it is 7 plus 5. That makes it 1, 5 in base 7. So we do 5 here and the other one over there. And now 6 times 1 is 6. Put it there. And let's add everything up. Column by column, 0, 5, and then 1 plus 6 is 7. But 7 in base 7 is 1, 0. So 1, 0. I'll just note it down here on the side. 7 is written as 1, 0 in base 7. So that's what we did over here. And therefore the result is 1050 in base 7. And with these examples, and with a little bit of revision of what we've done on all the other bases, you should be able to perform base translation and operations in any number base. You have all the tools to operate with numbers in any base. You know the algorithms to convert between decimal and any base. Although we did it explicit for binary, octal and hex, you wrote your own algorithms for any base. We looked at the special relationship binary has with octal and hexadecimal. One octal digit maps to 3 binary digits. One hexadecimal digit maps to 4 binary digits. Hexadecimal maps to the way we describe colors, with 24-bit fitting into 6 hexadecimal place values. Go and find out more about ways of describing color across the years and as technology advanced. You played with concepts of steganography and exercised the concept of manipulating pixels in an image. I hope you enjoyed the task and found in it an opportunity to deepening your understanding of numbers and number bases. Some of you have started implementing these ideas and algorithms of these lessons into a programming language, but remember, programming tasks are outside the scope of this module. Which sweet treat shall I have? Inna minna monna mite, bascalora bora bite, ooga booga bow, eggs, butter, cheese, bread, stick, stock, stone, dead, out. Not that one. You probably know your own version of this song. Most cultures have their own selection rhymes of songs. I'm using it to eliminate the sweets one by one, and I'll eat the last one. So I was here, so inna minna monna mite, bascalorum bora bite, hooga. Oh, I don't really need to do it this way. I can just count the sweets, count the words, and see how many times the sweets fit into that length. Let's look at that. There are 19 words in this rhyme, so it goes like this. I start on my cupcake, so I'm going to start here, and I count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. This one is out. So the fourth sweet is out. That's the one I eliminate. And then I'm going to start from the fifth sweet. So so this is 4 is out, I start from the fifth, and now I go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. So okay, this is out. So the 2 is out, and I would start again on the third suite. That's going to take a long time. We can do better than that, because really we're wrapping around the number 19 around the number of suites, around 5 suites. So that means the 19 covers the 5 suites 3 times, and then there's 4 more words to use, so the fourth chocolate is out. Yes, that's what we got. And then I start counting on the fifth, and I've got 4 chocolates to count over. 19 covers it 4 times, that's 16. And then there's 3 more words left, so the third chocolate after the fifth, which is a third, that is number 2, and that is out. Then I've got 3 chocolates left. I start on the third chocolate. 19 covers it 6 times. That makes 18. And then there's 1 word left, so the third chocolate is out. Then I'll do it again. I have 2 chocolates left. I start on the fifth. And then I'll just go even and odd, even and odd, alternating between the fifth and the first, and the fifth is out. So I will eat the first sweet first. I'll eat my cupcake first. You can do it yourself with your treats and check my maths. So we really didn't need to do the counting around every time. What we needed was the remainder of the division of 19 by how many sweets were left on the table. So 19 divided by 5 is 3, with the remainder 4. So the fourth chocolate is out, and I start on the fifth. So I've got the fifth, the first, the second, and the third available. Then, starting on the fifth, I do 19 divided by 4, which is 4, remainder 3. And from 5, 1, 2, the second is out. Then I start on the third chocolate, and I have the third, the fifth, and the first. So 19 divided by 3 is 6, with the remainder 1. So the third chocolate is out. Then I start on the fifth chocolate. I've got the fifth and the first. 19 divided by 2 is 9, with the remainder 1. So the fifth chocolate is out. And so I will eat the first. All we needed were the remainders. This wrapping around numbers and requiring only remainders of division is the core of what we do in modular arithmetic. You and I use it every day to work with hours and minutes and seconds. You see, 20 minutes after 1:56 p.m, it's 2:16 p.m. You add 56 minutes with 20 minutes, that makes 76 minutes, and then you take away the 60 minutes, giving you 16 minutes past the hour. And then that extra 60 minutes you convert into 1 more hour, so you add 1 to the 1 p.m, making it 2:16 p.m. Modular arithmetic is often referred to as clock arithmetic. But instead of working always with 60 minutes of 12-hour clock faces, we work with the size of the clock we need for each problem. With the chocolates, we did 19 divided by 5 equals 3, with remainder 4. So here we were working with a clock face with 5 hours. When we did 19 divided by 4 equals 4 with remainder 3, we actually want a clock face with 4 hours. 19 divided by 3, which was 16 with remainder 1, we were working on a clock face with 3 hours. And 19 divided by 2, which is 9 with remainder 1, we actually want a clock face with 2 hours. Well, the 2-hour clock just highlights if the number we were working is even or odd. Like in binary, odd numbers end with a 1 and even numbers end with a 0. What's cool about this concept of working with remainders of division is that the rules of arithmetic are very similar to the ones with common numbers. What I mean is that 45 divided by 4 leaves remainder 1. And that's because 4 times 11 is 44, and that's the highest multiple of 4 fitting into 45. So the remainder is 1. I'll write that. So 45 divided by 4 leaves remainder 1. And 18 divided by 4, I'm ignoring the integer part for now, leaves remainder 2, because 4 times 4 is 16, and then 16 to 18 is 2, so that's remainder 2. Now, the cool thing about the rules of arithmetic here is that if I add 45 with 18, the remainder of that sum, when divided by 4, is the same as adding the remainder 1 and the remainder 2, so it's going to be remainder 3. So I don't need to add the numbers up, do the division by 4 and work out the remainder. I can just say, well, it's going to be the remainder 1 from here plus 2 from there. I can add up the remainders, and that is one of the key properties we're going to tap into. Now, this also works for multiplication. So 45 times 18, the remainder of division by 4 is the multiplication of the two remainders. So 1 times 2. So the remainder is going to be 2. Check for yourself. That means that if we are only interested in remainders, then we can work out remainders of smaller numbers and then add, subtract and multiply remainders provided we are working in the same size of clock. We're going to call that the modulus. Sometimes I call it mod. Now, this property does not extend to division. It is only for addition, subtraction, and multiplication. From the first examples with suites, the pattern of numbers we keep eliminating looks random. One way of generating pseudo-random numbers for computing purposes employs modular arithmetic, working with remainders. And one incredible use of modular arithmetic is the strongest form of encryption using classical computing, the RSA encryption that relies both on large prime numbers and modular arithmetic. RSA stands for the name of the mathematicians that developed it, Revest, Shamir, and Adelman. In this lesson, you will learn how to work on encrypting and decrypting messages using the RSA algorithm, banking on modular arithmetic. Get ready for this adventure. Hi there. Let's look in more detail how to actually compute in modular arithmetic. The main thing to bear in mind is that we are working with the remainders of division by the number that is written after the mod, okay? So when we work in mod 5, we are working with the remainders of division by 5, which actually the remainders can only be 0, 1, 2, 3, or 4. There's only 5 options. So every time we're working in mod 5, we're really boiling down every number to either 0, 1, 2, 3, or 4. If I'm talking about 23, and I want to work out what is the smallest positive number that it's congruent with 23 modulo 5, I'm actually saying, what's the remainder of 23 when divided by 5? That's really what I'm asking. Okay. So we want to work out what that guy here is. The way to do that, we do the division of 23 by 5. And we know that 23, the largest multiple of 5 that fits in 23 is 20. So really we'll be doing 23 is 20 plus some extra bit that it's a 3. So 3 is that remainder. Now, how do we do that from the division itself? Well, 20 is 4 times 5. So I've got 4 is the integer part of my division, and then I've got my remainder, 3. So the answer to this is that 23 is congruent with 3 mod 5. It sounds like I'm kind of complicating it by writing down all these expressions, but this is the meat and bones of what you got to do every time you work with numbers in mod 5. I'll show you in the calculator. So I'll write 23 divide by 5, that gives you 4.6. None of those numbers is the remainder. 4 is the integer part of the division, as I had written on the board before. I'll show you again. Okay, that's a 4 there. And now on the calculator I would do 4 times 5, which is the mod, which is 20, and then I'll do 23 take away 20, which is 3. Okay? So done. Now on the back of this, I can get for free pretty much what 28 is congruent with mod 5. So 28 is just one more multiple of 5 away from 23. So he's got the same remainder when divided by 5. What I mean is that 28 is 23 add 5. So really is going to have the same remainder when divided. So 28 is congruent with 23, which is congruent with 3 mod 5. And you can check that out yourself by doing the calculation by writing 28 divided by 5. Well, really it's going to be 5 and some remainder, because 25 fits into 28. And then you do 28, take away the 25, which is 3, as we said, and job done. What about larger numbers? Can we bank on this idea for larger numbers? Of course we do. If I had instead, if I had 128, 128 is 100 on top of the 28, and 100 is itself a multiple of 5, so that's not going to change the remainder of the division. So 128 is still going to be congruent with 28 and congruent with 3 mod 5. Now, in other words, the smallest positive number that is congruent with 128 mod 5 is still 3. Let's look at another number, larger one. I just write here a number I fancy. I know, 1011024. I nearly tricked you to think we're doing binary, didn't I? Okay, anyway, so that's that one. What is that congruent with mod 5? What is the smallest positive number that is congruent with this one, mod 5? Again, don't get fooled by the large number. It all boils down to the remainder of division by 5. Fortunately, when we look at multiples of 5, the last digit, the units digit, tells you whether the number is a multiple of 5 or not. If it ends in 0 or in 5, it is a multiple of 5. This guy ends up in 4, but the closest number to it that is a multiple of 5 is going to be the guy that ends up with a 0. So 1011020 is the closest multiple of 5. So we can, this number plus 4 is the number we started with. Therefore, the remainder of the division by 5 is going to be that. This means you can spare doing the whole division. And in fact, if you were to do the division, you would be doing, divide that guy by 5. You have some integer part, which I don't care about, and you're going to have a remainder of 4. You will get it. Just check it out with your calculator, okay? Let's have a taste of what mod 9 looks like. Again, mod 9, how many remainders you're going to have? Yeah, I can hear you. 9 remainders from 0 to 8. That's all you're going to get. So if we're working with 179 mod 9, there's only 9 possibilities for that answer there. How do we get it? Now, mod 9 is one of my favorites because we got a little shortcut to work out the remainder. It is the thing you've learned in primary school of casting off 9s, yeah? So casting off 9s means you add up the digits of the number, and that brings us to 17. The result is still a 2-digit number. Let's add the digits again. That gives you 8. So 8 is going to be the remainder of the division by 9. That means that it's going to get you the mod straight away. It's a pretty cool property. This also works with a little variation for mod 3. And in mod 3, there's a special relationship between 9 and 3. It is a, 3 is a factor of 9. So we can still do casting off 9s, and then we do something else at the end. So let's do the casting off 9. So add up the digits of this guy, and we can shortcut this into 4 and 5 is 9, so I get rid of it, and then I get 6. 6 is a 1-digit number. 6 would be the congruence mod 9, but we're not doing mod 9, we're doing mod 3. We just know that 6 is also a multiple of 3. Therefore, the number we started with, 2, 1, 3, 4, 5, is going to be a multiple of 3 as well, and therefore it has remainder 0 when divided by 3. Do you want to check that? Let's look in the calculator then. 21,345 divide by 3, drum roll, bong. 7,115. That means the division is whole and you get 0 remainder. Okay, there we are. Now for free we get the numbers that come after and before this guy have the other remainders that are possible mod 3. So 21,346 has remainder 1 when divided by 3. 21,347 has remainder 2 when divided by 3. And the next number, 21,348, you say it is? Yeah, divisible by 3, and so remainder 0. If you were tempted to write 3 there on the mod, it would be correct, but it wouldn't be totally correct, because I want to boil it down to the smallest number that is congruent with 21,348 mod 3, and the smallest is going to be either 0, 1, or 2. So we've got another multiple of 3 here, and so on. Mod 11, say we've got 1,428, and again I'm asking you, what is the smallest positive number that's congruent with 1,428? Mod 11. Mod 11. 11 is pretty cool as well, because there is another shortcut for working out remainders of division by 11, and it goes this way. It's a trick with the digits. So we add up, so that's 8 plus 4, and that is 12. Then we add up the second and the fourth digit, 2 and the 1. So 2 plus 1 is 3. And now here's the clever bit. You do 12, take away the 3. So you do the sum of the odd order digits, take away the sum of the even order digits. So we do the 12 minus the 3, and that gets us 9. And 9 is going to be the remainder of a division by 11. So that's going to be the mod. We can prove all these shortcuts I've shown you. We can prove them, but I just wanted to appreciate using them and see how much this helps you with your mental arithmetic and speeding up these calculations. It could be long and tedious, but let's look in the calculator. Is this true? Am I really talking the truth? You check. We're going to key this in the calculator. So 1,428 divide by 11, you get 129, blah, 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 blah. So you would do 129 times 11, which, by the way, we could do in the calculator, but it would be so much more fun if we do it by hand here. So I'll show you a trick of how we do multiplication by 11. 129, 129, a bit off sync. So 9, 11, 4, 1. There we are. 1,419, and then you take the initial guy, 1,428, take away that product, and what do you get? What do you get? You get 9, as we said, and so that's the remainder, okay? You could do that on a calculator, but it's a lot more fun to multiply by 11 by hand. I know you understand that. Right, so one more, let's do mod 128, big number. So in mod 128, how many remainders can we have when we divide by 128? It's 128. All the remainders from 0 to 127. If our number is bigger than that, then we need to do some division. So let's look at 760. What is the smallest positive number that is congruent to 760 mod 128? Let's do it. Calculator time. Right, so we write 760 divided by 128, and there we are. So 760 divided by 128, the whole part of this division is 5. Let's work out the remainder. I'm going to back on my calculator just because 128 times 5, actually this one could do in our heads, couldn't we? 128 times 5, writing it down, is 640, and then you would do 760, take away 640, and blah, 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 you get 120, which is the remainder of this division. Okay, and therefore the number we're asking you on mod 128. Hi there. Let's look at how to add up numbers in modular arithmetic. The key thing to bear in mind is the meaning behind all those symbols we use in modular arithmetic. We are always using the remainders of division, and when we're adding numbers, say mod 5, we are adding the remainders of division by 5. So I'm just going to show a different example, an example that apparently doesn't have anything to do with modular arithmetic, so bear with me in this. Say I'm packing oranges in trays that take 12 oranges each. Okay, so I got my happy oranges here in a tray of 12. So 12 oranges, really good. I got one tray with 12 oranges. And I would give it the job that this week I'm going to be packing 140 oranges in trays of 12. Okay, so I got 140 oranges to pack in trays of 12. How many trays do I get and how many oranges are left unpacked? Well, 140 oranges fills up 11 trays of 12. So 140 can make 11 full trays of 12. And that brings me to 132 oranges. And then I've got 8 left that don't fill up the full tray. That 8 is the remainder of division of 140 by 12. 140 is 8 mod 12. Okay. Say that now on the second week, I've done such a great job packing oranges that I've got 150 to pack, same size of tray. So 150, that's going to be, I can make 12 trays of 12, and that gives me 144 oranges. And then I've got 6 left that don't make a full tray. That's because 150 is congruent with 6 mod 12. Now the question is, over the 2 weeks, how many oranges are not in a full tray? So you pack them all in trays of 12. How many are left in a half filled tray? So it all boils down to 140 plus 150. What's the remainder of division by 12? We could add 140 plus 150 and then divide by 12 and find the remainder, but we have the remainders of 140 and 150 already calculated because we had 140 had remainder, let's have a look, it was remainder 8 mod 12, and 150 has remainder, it was remainder 6 mod 12. Therefore, when you add it up, the 140 add 150 is going to be congruent with 8 add 6. Basically, you're going to try to pack the 8 oranges left and the 6 oranges left into another tray of 12. And that gives you 14 oranges, make one tray of 12, plus 2 leftovers, which means remainder 2 mod 12. Okay, so we don't really need to add up the 140 with 150 and then do the division if we had the partials already done. So the answer over there is that you get remainder 2 mod 12. Now that example, just to illustrate the general rule that it's true in modular arithmetic, if you add up, if you have a number, let's call it A, and we know that has remainder C when dividing by a number n, and you have another number B that has a remainder D when dividing by the same n, it is true that the addition of the two numbers A and B has the same remainder as the adding up the two remainders. Just like we did in the previous page, with A being 140 and B being 150. Now, of course, this number here may not be a small enough number, but you can then find the remainder of this new number that it's smaller, mod n. Let's have a look at how we use this. Just another example. We have 1,456, and we want to find the remainder of this mod 12, so what's left after packing your oranges in trays of 12. if you spot that this number can be written as a combination of a multiple of 12 plus something else, you can use that to shortcut the calculation. So I spot that this number is close to 1,440, which I know is 120 times 12, because 12 times 12 is 144. And then I've got 16 there. I can use this breakdown to speed up the calculation. 1,440 being a multiple of 12 is congruent with 0 mod 12. I'm now down to adding up these, and 16 is congruent with 4 mod 12. Okay, so you can knock off multiples of the mod and take them away to speed up your modular arithmetic calculations. One more example. If you're explicitly asked to calculate 256 add 18, still mod 12, we can do the partials again. 256, that is congruent with 4 mod 12. You can check that out. And then 18 is 12 plus 6, so 6 mod 12. The addition of these guys is going to be congruent with 10 mod 12. Okay, there you are. And we write there congruent with 10 mod 12. We looked at adding up numbers in modular arithmetic, for example, adding numbers mod 5. Now, what number added to another changes nothing? That's going to be the additive identity. And having that in mind, we will be able to understand what it means by having numbers that kind of cancel each other out or add up to that additive identity. Easier if I show you what I mean. In mod 5, I'm really interested in working with numbers between 0 and 4, so the remainders of division by 5. We'll look at the addition table, which I'll just write again here. The addition table, mod 5, I've got 0, 1, 2, 3, and 4, 0, 1, 2, 3, and 4, and I'm going to add up all those numbers mod 5. Okay, so 0, 1, 2, 3, and 4. 1, 2, 3, 4, and then 4 plus 1 is 5, which is 0, mod 5. And then 2, 3, 4. 2 plus 3 is 5, so that's 0 mod 5. And 4 plus 2 is 6, which is 1 mod 5. And then 3, 4, 0, 1, 2, for the same reason as before. And 4, 0, 1, 2, and 3. Right, that's our addition table. Now, we're looking for the additive identity. That is a number that added to any other doesn't change it. So it's a number that added to 1 still gives 1 mod 5. But instead of 1, I put 2. I want the result to be 2. And so on and so on and so on. So it's adding nothing, isn't it? It's 0. Now, does it still make sense in mod 5? 0 plus 2 is just 2, meaning 0 stands for any number that is a multiple of 5, and 2 stands for any number that leaves remainder 2 when divided by 5. If I add 2 of those numbers together, I still have remainder 2 mod 5. And 0 add any number is going to be the number itself, mod 5. So the same 0 I have here. So 0 is our additive identity. So 0 mod 5 is the additive identity. Mod 5. We could even write a special 0 for it, which sometimes we do, but let's go with 0. Now, what do I want to go with this? I want to look at pairs of numbers that add up to that 0. That's easy with the addition table. We just look at where is the 0. Look, I've got a 0 there, a 0 there, a 0 there, a 0 there, a 0 there. So for this 0, I've got the 4 and the 1. 4 plus 1 adds up to 0, mod 5. That's not surprising. 4 plus 1 is 5. 5 divided by 5 leaves remainder 0, mod 5. We've got the 3 and the 2, because 3 plus 2 leaves remainder 0 when divided by 5. So in fact, any pair of numbers that adds up to 5 in this table. So there we are. So 4 and 1, 3 and 2, 1 and 5, 5 and 0, 0 and 5. So those pairs are additive inverses, mod 5. So I'll just write it there. 0 plus 0, 1 plus 4, 2 plus 3, 3 plus 2, 4 plus 1. They're all 0 in modular arithmetic with modulo 5. Okay. That means each of these pairs are inverses of each other, additive inverses, modular 5. So that means 1 is the minus 4 mod 5, meaning 1 is the number that added to 4 gives 0 mod 5. And also 4 is the minus 1 mod 5. Okay, so that comes from there and also from there, okay? From the other two, when with 2 and 3 added to 0, that means 2 is the additive inverse of 3 and 3 is the additive inverse of 2. So I write the minus for it. So 2 is the additive inverse of 3, so I write minus 3. And 3 is the additive inverse of 2, so 3 is the minus 2 mod 5. So 3 is minus 2 mod 5. How do I write this in the middle of a calculation? I would simply write minus 4, and I use the symbol for congruence, minus 4 congruent with 1 mod 5. And I would say as well that minus 1 congruent with 4 mod 5. And similarly for the other numbers. So the minus 2 is a 3 mod 5. And minus 3 is the 2 mod 5. The key idea to bear in mind is which is numbers that added together give 0 mod 5. So let's look at this example. Say I've got number 23 and I want to find what is the additive inverse of 23 mod 5. So I would ask, what is the additive inverse of 23 modulo 5? The mathematical way of writing it would be, what is minus 23 mod 5? We say, what number added with 23 gives 0 mod 5? Now, to start with, I wouldn't work with 23, because 23 is bigger than 5. I would reduce 23 to the remainder of division by 5, so to the smallest number I can. So 23 divided by 5, well, 5 goes 4 times into 23, so 23 is 4 times 5 plus 3, so the remainder is 3. So to start with, 23 is congruent with 3 mod 5, so minus 23 is going to be minus 3, which we saw before, that the number that added with 3 that gives 0 is 2. So the minus 3 is 2 mod 5, and therefore minus 23 is 2 mod 5. And in this way, we work out the additive inverse of any number in any modulo. Hello, hello. Let's get ready for multiplication in modular arithmetic. We've got 11 times 13, and we want to calculate this in mod 9. Now, key thing to remember is if you can avoid getting to big numbers, please avoid it. Keep the numbers as low as you can. In this case, 11 and 13, the numbers we're trying to multiply, are a little bit bigger than the mod 9. So we're going to calculate 11 mod 9 and 13 mod 9 and then multiply the remainders together. That's what we're going to do. So 11 is congruent with 2 mod 9. 13 is congruent with 4 mod 9. And the product, 11 times 13, and note how I'm avoiding doing the multiplication, because I don't have to, will be 2 times 4, which is 8 mod 9. Okay? So this is what we're going to do every time we have multiplications to do in modular arithmetic. We will just try to keep the numbers low, and when possible, calculate the remainders individually and then just do the multiplications together. Right, I didn't quite tell you why we can do this. I'm not going to prove it, but I'll give an idea of why this works. The fact that 11 is congruent with 2 mod 9 means I can write 11 as 9 plus 2, and 13 is congruent with 4 mod 9, so it's 9 plus 4 in this case. And multiplying 11 by 13, I'm just going to do that carefully here, is the same as multiplying 9 plus 2 times 9 plus 4. And that means I would distribute 9 times that 9 and 9 times that 4, and then do the 2 times that 9 and the 2 times that 4. And that would give me, I'll just do all the terms bit by bit, 9 times 9. Again, I'm avoiding doing the multiplications. 9 times 9, I'll do plus 9 times 4, plus the 2 times the 9, plus the 2 times the 4. Now, I didn't do the multiplications because I'm looking into mod 9. That means I don't care about multiples of 9. Multiples of 9 are going to get out of my way, and all I'm going to concentrate is on the remainders. Now, I've got here 9 times 9 is a multiple of 9. 9 times 4 is a multiple of 9. 2 times 9 is another multiple of 9. And the remainder is going to be this guy here, 2 times 4. So what I'm saying is that 11 times 13, because it is a multiple of 9 plus 2 times 4. So when we're calculating 11 times 13 mod 9, we have the same remainder as 2 times 4, which is 8 mod 9, because we threw away this multiple of 9 here in the calculation. So this is a generic example that gives an idea of how we prove this result. And this result, I'm just going to summarize it with variables. So if we have A, that it's congruent with C mod some n, and we have another number B that it's congruent with D for the same n, and I want the multiplication of A times B, but I want the remainder of division by n. So all I have to do is multiply the remainders and then calculate that mod n. This is what I meant with the rule I applied in the last example. Let's look in more detail at mod 5, and we're going to write the multiplication table in mod 5. The remainders of division by 5 are just numbers from 0 to 4. That's all I need to write on my multiplication table. And we are doing mod 5. So we're going to multiply this out and write the remainders of the result. There we are. So 0 times all the other guys gives 0, because every time you multiply a multiple of 5 by another number, you still have a multiple of 5. So all these bits here will be 0. And this is mod 5. And then let's have a look. We're multiplying 1 by the other numbers. 1 times 1 is 1, 1 times 2, 1 times 3, 1 times 4. No surprises there. The same happens on the column of 1. 1 times 1, 1 times 2 is 2, 3, 4. There we are. Now for the row of 2, 2 times 2 is 4. 4 has a remainder 4 in mod 5. 2 times 3 is 6. 6 has remainder 1, mod 5. So we write 1 there. And 2 times 4 is 8. 8 has remainder 3, mod 5. Okay, so right there. And similarly, on the column of 2, I've got 2 times 3, which is 6, is 1 mod 5, and 2 times 4 is the same one as before, is 3 mod 5. On row 3, got 3 times 3, which is 9. 9 is congruent with 4 mod 5. And then 3 times 4 is 12. 12 is 10 plus 2, so it's 2 mod 5. And that means I got a 2 there. And in a similar fashion, I got a 2 on this 4 times 3. And 4 times 4 is 16. 16 is 15 plus 1. Therefore, I get 1 mod 5. And that's the complete multiplication table in mod 5. And you wonder, what if I've got bigger numbers than 4? How do those numbers fit in the multiplication table? Remember, we boil the number down to the remainder mod 5, and then there will be an answer in the multiplication table. One final example on mod 256. We're performing 238 times 144. What is the smallest positive number that is congruent with this mod 256? Let's have a little think. In this case, both numbers, 238 and 144, are smaller than 256. So these numbers are already remainders of division by 256. In this situation, it might be easier to perform the multiplication and then work out the remainder like we did before. So we're going to have a little help from our calculator now. We're going to do the multiplication there just to speed things up. And we multiply by 144. That's, we get 34,272. That number divided by 256, we have 133, and then let's work out the remainder. Once again, we take the integer part, 133, multiply by 256, which is the mod, and we're going to take that away from the original number. So we're going to take that away from 34272, and we have 224 as a remainder. Don't worry about that minus there. I did 133 times 258 minus the original number instead of the other way around. That's where the minus comes from. Okay, so the result is 224 mod 256. Hello, we're going to look at multiplication again. This time we're going to look at the multiplicative identity, and multiplicative inverses in modular arithmetic. In normal numbers, the number 1 has a special property. When you multiply 1 by any other number, it doesn't change that number. So 1 times 3 is 3, 1 times 10 is 10, and so on. So 1 is the multiplicative identity for normal numbers, because it's that number that when multiplied by others, it doesn't change them. In modular arithmetic, we want that property too. So we're looking at, say we're on mod 5, we're looking at a number that multiplied by 2 still is 2 mod 5. We're looking at a number that when multiplied by 3 is still 3 mod 5. Well, let's try 1. Does 1 work? 1 times 2 is 2. Yep. 1 times 3 is 3, and so on. 1 is the multiplicative identity in modular arithmetic for any mod we consider. So now that we know what the multiplicative identity is in modular arithmetic, let's look at inverses and what that means. Let's focus on mod 5 for now. In mod 5, we already looked at the multiplication table. I'll just copy it here again. Yes, I didn't copy the 0 row and the column row because that's not going to be of interest for now. So let's focus on these numbers. The multiplication table, here it is. 2 times 2 is 4, 2 times 3 is 6, which is 1. 4 times 2 is 8, which is 3. And now I've got, 3 times 3 is 9, which is 4. 12, which is 2, and 4 times 4 is 16, which is 1. Okay, so I've got the multiplication table for mod 5, and I have excluded the 0, because 0 times any of the other numbers gives 0, so that's not interesting for now. And we're focusing on multiplicative identity, which is number 1, and we're looking for multiplicative inverses. Let's just remember for a second what happens with linear numbers. In linear numbers, it makes sense to talk about inverses. That means if I've got 2, what number times 2 gives me 1? 1 being the identity. And that is number 1/2. So 1/2 is the inverse of 2, because when I multiply it together, I get the identity. Similarly, for 3, the inverse is the number that multiplied by 3 gives 1, which is 1/3. And at the same time, 3 is the inverse of 1/3, because 3 times 1/3 gives 1. So that means 3 and 1/3 are inverses, 2 and 1/2 are inverses, and so on. I'll just note that a half is sometimes written as a power. So a half can be written as 2 to the minus 1, and a third can be written as 3 to the minus 1. And that minus 1 in the power is an indication for inverse. You invert the fraction, but also in terms of multiplication, it means it's an inverse. We're going to grab that idea back to modular arithmetic. So on mod 5, we want to know what are the pairs of numbers that are inverse for multiplication. What are the pairs of numbers that multiplied out give 1? Well, look again at the table. What pairs of numbers multiply out to 1? There we are. Everywhere in the table you find a 1. That tells you what pairs multiply out to 1. It tells you what are the pairs of inverses. Well, I've got a 1 that comes from 1 times 1 being 1 mod 5. That's fine. We've got a 1 that comes from 2 times 3. So 2 times 3 are inverses mod 5. And same with 3 times 2. I'll just write it down. And 4 times 4, congruent to 1, mod 5. So 2 and 3 are inverses, mod 5, and 4 is inverse of itself, mod 5. I'll write that down. 2 inverse is 3. mod 5. That means the inverse of 2 is 3. 3 inverse is 2 mod 5. That means that the inverse of 3 is 2. And 4 is an inverse of itself, mod 5. Now, we're probably thinking it's all very well with the numbers in the multiplication table. In the multiplication table, it's easy to spot the pairs of inverses because we're looking for the 1 in the result. And you quite rightly may be thinking, what if I've got larger numbers, numbers that aren't in the multiplication table? For example, what if I'm asking you what's the inverse of 23 mod 5? What's that inverse? Not a problem, because as before, if the number we're working with is larger than the remainders you're allowed, then we calculate the remainder. So 23 is 3 mod 5. And therefore, when we're looking for the inverse of 23, we are looking for the inverse of 3. And we just saw that the inverse of 3 is 2 mod 5. Let's look at another example. Say I wanted to calculate this big power. I've got 163 to the power of 42 mod 49. So that's the first thing I'm asking you to calculate. 163 is a large number, and it's a large number in the sense that it's bigger than 49, the number in the mod. So the first step is to reduce that number to the smallest integer congruent with it, mod 49. So we do 163 is congruent with 16 mod 49, and I'll show you in the calculator. 163 divide by 49, the whole part is 3, so I do 3 times 49, it's 147, so I need to do 163, take away 147, 163, and that is 16. That's how I got the remainder. Now, the clever bit here is that instead of doing powers of 163, I'm going to do powers of 16. And I'm going to build them up until I get to our big power, the power of 42. So what I'm saying is that 163 to the power 42 is congruent with 16 to the power 42 mod 49. So I'm reducing the calculations to working with powers of 16. Let's do it on a new sheet. So 16 squared is 256. That is larger than 49. So let's do that on the calculator. 256 divide by 49. I could do divide by 49, but you're probably screaming that we know how much that is. Yeah, we could do 259. How many multiples of 49 fit into that? Look at that. 59 is almost 50. It's 50 minus 1. So we could do 5 49s is going to be 5 50s minus 5. So it's going to be 250 minus 5. So that's going to be 245. And so the remainder is going to be the same as taking away the 245 from it, which is 11. It's 11 mod 49. Now we're going to do the next power of 16. We're going to do squares of squares. So if I do 16 squared again, I get the power 4. I'm just right here as a reminder of what we did. And the beauty of this is that now I do 16 squared was 11, so this is 11 squared, which is 121, which if you take away twice 49, you get a remainder of 23. Okay. And then we keep going. We keep going. Let's do 16 to the power of 8. That is the square of the previous. Just as a reminder, here is the square of the previous one. And that means I can replace the 16 to the power of 4 by 23. So I do 23 squared. And that gives us 529, which is, if I take away multiples of 49, is remainder 39, mod 49. Now, 39 is quite close to 49. So instead of working with a positive remainder, I'm going to work with a negative remainder. Because although I've got a remainder of 39 over 49, it's 10 short from the next multiple of 49. So this is minus 10 mod 49. Why on earth do I want a minus 10? 10 is very easy to do powers, isn't it? And I've got minus, so if I do a square of minus 10, I'm going to have the square of 10 is going to be the same. It's going to be 100. So easy to work with, and it's good to work with small numbers when you're doing big powers. So let's go with it. Now, we could do 16 to the 8 squared again, or we could do a different operation. Let's keep in mind what's our goal. Our goal is to get to power 42. We've got power 8. If we could get to power 10, then we would just raise it to the power 4 again, and we'd be very close to 42. So I'm going to do 16 to the power of 10 by noting that that's 16 to the 8 times 16 to the square. And we had calculated these numbers before, so 16 to the 8 is congruent with minus 10, and 16 squared is congruent with 11. So that is going to be minus 110. But again, I want a remainder mod 49, which means we could just add twice 49 to it, so add 98, and that will give us minus 12 mod 49. If you add another 49 to it, you get a positive remainder, but minus 12 is quite nice because it's still a small number in magnitude. Now, here's the magic bit. Let's get to power 40 by doing 16 to the 10 to the power of 4. And that's great because a negative number to power 4 is going to be positive, and 12 is quite small, so we're going to be able to handle this. So this is the same as doing minus 12 to the power of 4, don't forget the brackets, and that is the same as just doing minus 12 squared times minus 12 squared, and that boils down to 46 on each side. So 46 squared, which is, 46 is minus 3 mod 49. So that's going to be under minus 3 squared, which is 9 mod 49. Now, just recapping, we want to get to 16 to the power of 42. We are on 16 to the power of 40. We just need to multiply this result, 9, by 16 to the power of 2. Let's do it on the next page. So we've got 16 to the power of 40 is 9 mod 49. We want to multiply by 16 squared. 16 to the 42 is 16. 40 times 16 squared, which is the 9, and then 16 squared, we saw that it was 11 mod 49, and that gives us 99, which is just 1 more than twice 49, so it's remainder 1 mod 49. Right, back to the question we started with. 163 to the power of 42 is 1 mod 49. I'm going to write this down. 163 to the power of 42. We said because 63 is congruent with 16 mod 49, this is the same as 16 to the power of 42 mod 49. That's what we said, and therefore this is all 1 in mod 49. the fact that this power is 1 means that we're very close to knowing what the inverse of the number is. So a good follow-up question from here is asking, calculate the inverse of 163 mod 49. So we are asked to calculate the inverse of 163 mod 49. That's a good follow-up question. And to do that, we observe the following. If you have a power that equals to 1, the power before that is the inverse of the number. So 163 to the power 42 can be split as 163 to the power 41 times 163. If this product is 1, which we have calculated that it is, that means that is the definition of multiplicative inverse, is what number times 163 gives 1? Well, the number is this guy, is 163 to the power of 41. So that is the inverse. So 163 to the power of 41 is the inverse mod 49. Do we have that number? Not yet, but we pretty much laid out all the foundation to do this computation really quickly, because we've done a lot of powers of 16 to come to this one. And I'm still talking about powers of 16 because the inverse of 163 is going to be the same as the inverse of 16. So to calculate the inverse, we just go back to this, and this is also 16 to the power of 41 for the same reason I explained above. And the power 41 is going to be made of lots of the other powers we calculated earlier. Let's have a look. The 41 I could make with the power 40 and then just multiply by 16. The power 40 was 9. So 16 to the power of 40 was 9. And so all I have to do is do 16 to the power of 40 is 9, and then multiply by another 16. Let's grab the calculator for that. 9 times 16, we've got 144, and that take away 98. 98 is 2 times 49 minus 98. That's our 46, so that is 46 mod 49. That means that the inverse of 163 is 46 mod 49. You could also say minus 3, because 46 plus 3 is 49. We're going to look at exponentiation in modular arithmetic. That just means doing powers of numbers and taking the remainder. Let's look at powers of 3 in mod 7. I'm going to do 3 squared. That's 9, which is 2 mod 7. 3 cubed is 3 squared times 3 again. So 3 squared times 3. And because 3 squared is 2 in mod 7, we just need to multiply these 2 with 3. And because 3 squared is 2, we only need to multiply 2 by 3. And that gives us 6 mod 7. 3 to the power of 4, we can do the square of the 3 squared. And that means we can square the 2. 2 squared, which is 4. And 3 to the power of 5, we can do 3 to the 4 times 3, so that will be 4 times 3. Or we could do 3 cubed times 3 squared, for example. 3 cubed times 3 squared, because the powers add up to 5. And 3 cubed, we saw there was 6, and 3 squared, we saw that it was 2. So that is 12, which is 5 mod 7. Whichever root you choose, you'll get the same number. And one more, 3 to the power of 6. It is, we can do 3 cubed squared, or we could do 3 squared cubed. Let's do that one, 3 squared cubed. 3 squared, we saw that it's 2, 2 cubed is 8, and 8 is 1 mod 7. Now, with that one, it's a good one. Because when you get 1 mod 7, you now can do powers and powers of it, and powers of 1 will always be 1 mod 7. So that means that from here onwards, any power of 3 to the 6 is going to be 1 mod 7. Why am I so excited about it? It's because we can do huge powers now with very little effort. I'll show you. Say we want to do 3 to the power of 203 mod 7. Pretty big. And if you give it a go with a calculator, 3 to the power of 203 isn't going to fit in the screen, which means you don't have a precise number, no point doing division by 7 and taking remainder because it's not going to help. So instead, we're going to take powers of 3, building from the previous results, and get as close as possible to 3 to the power of 203. We've got 3 to the 6 is 1. So 3 to the 6 is 1. We're going to take powers of 3 to the 6 until we get very close to 3 to the 203. So let's do 3 to the 6 to the power of 33. And you're wondering, why 33? Well, because 33 times 6 is 198, and that's the multiple of 6 closest to 203. So that is 3 to the 6, we know it's 1. So now we do the power of 33, which is still 1. So 3 to the power of 203 is going to be 3 to the power of 198 times 3 to the power of 5. And that 3 to the power of 198 comes from 3 to the power of 6 to the power of 33, because 6 times 33 is 198. And so we've got 1 times 3 to the 5. And 3 to the 5 we worked out in the previous calculation, so it's 5. So we've got 1 times 5, which is just 5 mod 7. Okay. So this is an example of how we can use powers of a number in modular arithmetic to build up to a large power, but without having to work with very large numbers. I thought it was interesting that in this initial calculation we work out all these powers of 3, and 3 to the 6 is 1 mod 7. Is that a coincidence? Or does it always happen? Do we always get a power of number that is going to be 1 mod 7? Does that always happen? And if so, can we work out that number? Is it always power 6? Good question. The answer to that is summarized in what is called Fermat's little theorem, and it tells you how you get 1 mod a prime number. 7 is a prime number, and in mod 7, power 6 is almost always going to give you 1. Fermat's little theorem says, let P be a prime number, and let's work on mod P. So we're working on mod P. And on mod P, the power P is very special. So any number to the power P is congruent with itself, mod P, provided P doesn't divide A. Okay? So P does not divide A. Let's make sense of that. In our previous example, we had powers of 3 mod 7. So our P is 7 and our A is 3. Yes, 7 doesn't divide 3, so we're good to go. 7 is prime, so Fermat's little theorem applies. So it says that 3 to the power of 7 is congruent with 3 mod 7. Now, probably wondering, we don't have a 1 there, and I was promising that there is a power that gives result 1. There is. Just let's look at this one again. It's 3 to the 7 is 3 again. That means that the previous power, 3 to the 6, has to be 1. I'll show you why. So 3 to the 7 is the same as 3 to the 6 times 3. And if this is 3 itself, then 3 to the 6 needs to be congruent with 1, mod 7. So we can update Fermat's little theorem to say not only that the power 7 returns the initial number, but that the power 6 is the identity 1. So a to the p minus 1 is the identity 1 mod p, provided p does not divide a. Okay. And that makes working in modular arithmetic with prime numbers a delight. And we will see later on an example of real-life application of prime numbers in modular arithmetic where we're going to capitalize on prime numbers. Earlier on in the course, you wrote algorithms to convert a decimal number to binary, and you thought of the algorithms for any base. In a programming language, you can use shortcuts to finding the remainders of integer division. Look out for the mod operator coming from modulus, as we use it in modular arithmetic. For example, 56 mod 16 gives you the remainder of the integer division, which is 8. So you can implement modular arithmetic in a programming language using this operator. 56 mod 16 will return 8, giving you that 56 is congruent with 8 mod 16. I've mentioned in earlier videos that we can use modular arithmetic to create mental arithmetic strategies to test for divisibility. And here's how we do it for casting off 9s. I'm going to write a generic number with digits from AN all the way to A0. And I'm going to write this number in the expanded form using powers of 10. And I want to check what is this number congruent with mod 9. So I'll write AN times 10 to the power of n plus AN minus 1 times 10 to the power of n minus 1 plus all these other terms all the way to A2 times 10 squared plus A1 times 10 plus A0. And we want to check what is this congruent with mod 9. Now, this is what we do for divisibility by 9, because if the remainder is 0, the number is divisible by 9. If the remainder is anything else, then it is not. Let's break this down into each power of 10. So 10 is congruent with 1 mod 9. 10 squared is congruent with 1 squared, which is congruent with 1 mod 9. And any power of 10 is congruent with 1 mod 9. That means that this initial expression is congruent with AN times 1 plus AN minus 1 times 1, and all of them in the same fashion, and so adding A2 times 1 and adding A1 times 1 and A0. Now this is congruent, we're just eliminating all these 1s because multiplying by 1 does nothing, AN plus AN minus 1 plus all the digits plus A2 plus A1 plus A0 mod 9. Now, let's just think about that. That means that the remainder of division by 9 only depends on the remainder of division by 9 of the sum of the digits. That's what we do with casting off 9s. We add the digits. And then we keep going, adding up the digits until the result is a 1-digit number. If you get 9, then the rem is 0. You can check for yourself how it works for mod 3. It's quite similar. Now for mod 5, so for checking divisibility by 5, what you get is that the remainder only depends on the units digit. If it's 0 or 5, then it is divisible by 5. For divisibility by 4, mod 4, you get that the remainder only depends on the tens and the units of the number, A1 and A0. For mod 11, this is a nice one, the one I mentioned in another video. Divisibility by 11, let's check each power of 10. So 1 is congruent with 1 mod 11, 10 is congruent with negative 1 mod 11. You would say 10 is congruent with 10 mod 11, but it is also negative 1. Now 10 squared, let's use the minus 1. 10 squared is congruent with minus 1 squared, which is congruent with 1 mod 11. And 10 cubed is congruent with minus 1 cubed, which is congruent with negative 1 mod 11. See the pattern? If the power is an odd power of 10, we have congruence with minus 1. And if it's an even power of 10, we have congruence with 1 mod 11. That means you can pair up the odd positions and the even positions, and so the sum of the odd position digits minus the sum of the even position digits is congruent with the initial number mod 11. That means that is the key to divisibility by 11. You can have the reassurance that your mental arithmetic shortcuts always work because you can prove them with modular arithmetic. Let's recap what we've done so far. One aspect that came up over and over again in number systems was working with remainders of division. In modular arithmetic, we looked at the powerful mathematics that can be done with such remainders to create an environment with arithmetic operations similar to day-to-day numbers. When iterated over and over again, multiplications in modular arithmetic seem to have a random pattern. That is tapped into in computing to generate pseudo-random numbers. The unpredictability also contributes to an encryption method, up to today the most powerful in classical computing. This method, RSA, taps into the fact that it is computationally hard to factorize numbers into primes, and so exploits large prime numbers and their product to create a public key encryption method. You can share that huge large number that is a product of two large primes, and anybody can send you secure messages with that key that only you can decrypt and read its true meaning. The tool we've learned to implement RSA encryption was calculating multiplicative inverses in modular arithmetic. We calculated powers in modular arithmetic, and we used a shortcut called Fermat's last theorem when the modulus was prime. Now, you can go ahead and program your mini implementation of RSA if you wish. You know it's outside the scope of the course. And you can go and read about digital signatures and other tools we can use to communicate and even exercise democracy in a secure way digitally. Next, we will get started with sequences and series. To get ready, start paying attention to streams of numbers around you and see which ones you can come up with a generating rule and make predictions on the behavior of those numbers. Mind you, we won't be cracking the secret rule behind the stock market or the lottery. There's no such thing, but we will open the door to what tools are out there to understand what can be understood from streams of numbers. As always, we want to see it from the point of view of a computer scientist, so get your focus on that. I will leave you a puzzle. It dates back to the 1st century before Christ, and it can be found in the literature, so as true as books can be. Josephus was a commander in Galilee, as the Roman army was invading. He had 40 soldiers under his watch. He decided that as their number was minute, they would not stand a chance against the Romans. So he looked for a randomized way of taking their lives that did not go against their moral and religious beliefs. Josephus and his army stood in a circle. One sword is used. The first person in the circle kills the person to their left. The sword is taken by the next person alive, and the person kills the next person to their left. The process went on like this until there were only 2 people alive. The instructions were so that the last 2 would stab each other at the same time. Only that Josephus was the last person holding the sword and convinced the other person that they could disguise themselves as Romans and survive. He lived to tell the tale. So where in the circle was he? And how did he work out the correct position to guarantee he was to live? The purpose of the next task is for you to see the mathematics of modular arithmetic in action, in a context that is real in computing. We're going to use a simplified version of a crypto system that is used every day by banks and probably by you too. A crypto system is a method of scrambling a message to hide its meaning, but that can be unscrambled using a key to recover its meaning. The method we're going to use is a public key crypto system, as a scrambling key can be given to anyone to encrypt a message, but only the holder of the private key can unscramble it. Think of it as a postbox with a special lock. The public key can only be used to put a message inside the postbox, like the opening of a slot to feed messages through, and the private key is a sort of master key that opens the compartment where all messages are. The postbox owner is the one that receives messages. They own all the keys and have given copies of the public key to anyone that wants to send the owner messages. If you want to learn more about encryption, read the further reading section. But please note that encryption itself isn't a learning outcome for this module, but understanding the mathematics for this particular method exposed here is. We said earlier in the module that everything is number. Letters and symbols in a written message can be converted into a number or several numbers. There are many ways of doing this. For example, we can use my table that we've seen earlier, and the message hello could be 22 for H, 15 for E, 26 for L twice, and 33 for O. And so we could have the number 2215262633 making up the message. There are standard ways of encoding a message into a number, but we won't be exploring such methods here. So in this next task, we will just assume that the messages are numbers. And here is the main idea. The secret message, remember a number, is encrypted by raising it to a certain power in modular arithmetic. Then there is another power you can raise the encrypted message to, returning the message you started with. Let's imagine Bob is going to send messages to Alice. He has the public key and Alice has both. The keys are the powers. Follow me. The whole process is like this. Say Bob raises the message to a power in modular arithmetic to encrypt the message, and he sends Alice the encrypted message. Alice then raises this message to another power in the same modulus, and that returns the message Bob wanted Alice to read. And here is the setup. We're going to use a prime number and we're going to call it P. The original message to be kept secret will be called M, and M has to be a number between 1 and P minus 1 so that it survives the encryption and decryption process. When we encrypt the message M, the resulting scrambled message will be called C for cryptic. Two special numbers, an encryption key E and a decryption key D. The public keys will be the number P and the number E. The private key will be D. And here's the procedure for encryption. We are going to operate in modulus P for the encryption and decryption process. We do C is congruent with M to the power of E modulus P. And here's the procedure for decryption. We operate in modulus P, so M will be recovered by doing C to the power of D modulus P. So M is congruent with C to the power of D mod P. This means that if Alice issues out public keys P equals 11, which is prime, and E equals 3, and it gives them to Bob, Bob wants to send the message M equals 5, so Bob does the following. C is congruent with M to the power of 3 mod 11. So he works out what M to the power of 3 mod 11 is, and he calls the result C. That's the encrypted message. Work this out yourself before you continue watching the video. Yes, the result is that C equals 4. So he sends C equals 4 to Alice, the encrypted message. Now Alice wants to decipher this message, so she's going to use the private key D equals 7. For now, don't worry about where the private key comes from. Just follow me. Alice calculates C to the power of 7 mod 11. The result will be the same as the original value of M. Work out C to the power of 7 mod 11 yourself before continuing watching the video. Continuing the calculation, it gives that M is 5 as Bob intended. Are you asking yourself why does it work? We will talk about it later, but you go ahead and discuss your thoughts in the discussion forum. In the discussion forum, you can follow the discussion prompt, post encrypted messages for others to decrypt. You need to post the message C and use the same keys as we used in this example. Then read the encrypted messages of other people and decrypt them. If you want to up the game, actually write a message and convert it into numbers using the two-way table I just showed you. You can discuss with your peers how to use the numbers. Now, to make the game playable, do make it explicit that you are sending an encrypted message by saying C equals the number. When you are decrypting, check with your peers if your result M equals your result is correct. Try this in-video quiz and replay the last part of the video and the modular arithmetic videos if you need. So why does it work? Why does encrypting M into C by doing C congruent with M to the power of E mod P and then doing C to the power of D mod P retrieve M? C to the power of D is congruent with M to the power of E, that's the C, and then to the power of D. And that is congruent with M to the power of the product of ED in mod P. So what is M to the power of ED mod P? To start with, what is ED? In the examples we saw in mod 11, so P equals 11, E was 3, and the private key was d equals 7. So E times d, 3 times 7, is 21. But you wonder, what is so special about 21? Well, in mod 11, the special power that turns any number into 1 is power 10. From Fermat's little theorem, we have that a to the power of 11 is congruent with a itself mod 11. And that means that a to the power of 10 is congruent with 1 mod 11. Now, what about 21? Let's see. A to the power of 21 is congruent with a to the 10 times a to the 10 times a. And that is congruent with a itself, because a to the 10 is 1 in mod 11. So 21 is special because it is a multiple of 10, 10 being 1 less than the modulus, 1 less than the 11. So 21 is a multiple of 10 plus 1, meaning that 21 is congruent with 1 mod 10, not mod 11, okay? Mod 10. What this means is that 3 and 7 are inverses modulus 10. So this is the clever thing that Rivest, Shamir and Adelman saw in inverses in modular arithmetic to create this system. Now back to Alice. She concocts the private and public keys D and E by finding inverses mod p minus 1. But she knows that the only numbers that can be used as keys are numbers E and D that have no factors in common with p minus 1. I'm not proving this result here, but you may have worked this out in one of the quizzes on multiplicative inverses mod n. Now, are there any other numbers we can use as keys in encryption mod 11? Meaning, are there other inverses mod 10? And how does one compute inverses mod 10? We saw earlier that in mod a prime we use Fermat's little theorem to help. The strategy is to calculate the special power of a number that is equivalent to 1. In mod a prime, prime p, that special power is power p minus 1, as a to the power p is congruent with a mod p, meaning that a to the power p minus 1 is congruent with 1 mod p. And so a to the power p minus 2 and a are inverses mod p. That means that the special power for mod p prime is power p minus 1. It may happen that there was a smaller power giving 1, but the theorem says that if you don't know otherwise, try this special power, p minus 1. That's all good for primes. How about for composite numbers? Number n, say n equals 10, meaning working in mod 10. It turns out that the special number here is given by how many numbers from 1 to n minus 1 that have no factors in common with n. That means co-prime with n. In our example, n equals 10, and we're looking at numbers between 1 and 9 that are not divisible by 2 and also not divisible by 5, which are the factors of 10. In mod 10, we will only work with numbers 1, 3, 7 and 9, as all other numbers, 2, 4, 5, 6, 8, are divisible by 2 or by 5 or by both. So 1, 3, 7 and 9 are 4 numbers, and that 4 is the special power in mod 10. For convenience, I'm including a table with the special power for several moduli. In this table, you can find the power for mod 18 by looking on the row with 12 and the column with 6. So 12 plus 6 is 18. And the special power is that number there, 6. Again, there may be a smaller power that achieves the result, but we guarantee that the power on this table works. I haven't totally explained why this works, but you can work through the algebra if you fancy. The proof is outside the scope of the module. You can read the references in the further reading section. So how does this work? The special power for mod 10 is 4. And that means that all inverses are given by the lower power, power 4 minus 1, which is 3. That means to calculate inverses, we're going to take powers 3. So a to the power 4 is congruent with 1 mod 10. That's using the number from the table. And that means that a cubed times a is congruent with 1 mod 10, and therefore a cubed is the inverse of a mod 10. This technique is an extension or Fermat's little theorem for when the modulus is not a prime number. Now, back to where we were. We're trying to calculate other inverses mod 10. We can only consider numbers 1, 3, 7, 9, as these are the only co-prime with 10. 3 and 7 are inverses, we saw earlier, because 3 times 7 is 21, and that's congruent with 1 mod 10. And so we now got 9 and 1 left. Now, 1 is the inverse of itself, so let's see what happens with 9. 9 squared is 81. 81 is congruent with 1 mod 10, so 9 is inverse of itself as well, mod 10. Now, those are no good as keys. The only good keys are the ones where you got two inverses that are not the same. Let's see what happens with p equals 17, still prime. The keys have to be inverses mod 16, one less than 17. Now, 16 has many factors. Let's see which numbers up to 16 have no factors in common with 16. We've got 1, 3, 5, 7, 9, 11, 13 and 15. That's altogether 8 numbers. Let's find the inverse of 3 mod 16. The special power for mod 16 is 8. You can use a table or you count the number of coprimes. So the power to give the inverse is going to be power 7. So 3 to the power 7 mod 16. That's what we want to calculate. We do 3 cubed, which is 27, and 27, take away 16, that's 11. So it's congruent with 11 mod 16. 3 to the power of 6 is going to be the square of 11. And so we've got 121, which is congruent with 9 mod 16. Check that out. And so 3 to the power 7 is congruent with that 9 times the 3, the 9 from 3 to the 6, and 3 to 1 more power, and that is congruent with 11 mod 16. Now that means that because power 7 gives the inverse, we have that 3 to the 7 is the inverse, so 11 is the inverse. So 11 is the inverse of 3 mod 16. That means that for encryption, mod 17, we can use keys 3 and 11 because they are inverses. 3 and 11 are inverses mod 16, one less than the prime. Now, you can compute for the other numbers. So, for example, for 5, what's the inverse of 5? You would do the same. It will be power 7 to find the inverse of 5. And working through the powers, you do 5 squared is 9 mod 16. 5 to the power of 4 is 9 squared, which is 1 mod 16. And that means we actually achieved a power that has result 1 earlier than the power 7. That can happen. And that means if 5 to the 4 is 1, that means that 5 cubed times 5 is 1, and that means that 5 cubed is the inverse of 5. So let's compute 5 to the 3. 5 to the 3 is the 5 squared times the 5, so 9 times 5, which is 45, and 45 is congruent with 13 mod 16. So 5 and 13 are inverses. We've got 3 and 11, we got 5 and 13, and you can carry on the calculations to find out all the other pairs of inverses in mod 16, so that you have all the other pairs of keys mod 17. That's the cool thing about modular arithmetic. In real-life RSA encryption, we don't use one prime number. We use a product of two prime numbers, making it difficult to calculate multiplicative inverses. I haven't explained it, but take my word for it for now. But in this module, I'm not asking you to work on the full RSA, only in the simplified version using a prime p as modulus and keys e and d that are inverses mod p minus 1. So just so we have it clear, we work in mod p for encryption and decryption, and we work on mod p minus 1 to find keys that are inverses. The next assessment task consists of you implementing by hand the methods I just explained. You are also asked to assess the security of the system by explaining the calculations you would need to perform with the public keys in order to decrypt the message. You will start by exchanging ideas in the discussion forum, and then you will complete your own task individually. I've got a great job offer for you. You can even choose the salary plan. You can get £100 on the first day, and each day you work, you get £50 more than the day before. Or a different plan, I double your salary every day, but you start on £1 on day 1. The question is, how long do you want to work for us? And what payment plan do you want? Is that too good to be true? Okay, it's just a story, I know, but we can still look at the figures. Have you made a decision? How do we actually decide? You could get your spreadsheet out and try it. I'll get mine. Let's put in all the data from these payment plans. So I've got a column here for the days of work, and the first payment plan and the second payment plan. So the first payment plan, we start with £100 on day 1, and on the second day is the payment we had on the previous day with extra £50 on top. So that means we get 150 on day 2, 200 on day 3, 250 on day 4, and so on. So we get all of that. Let's see how many days we need, but we'll put 28 for now. Now on the second option, you start on £1. So we start on £1, and on the second day, we go with doubling what we earned on the previous day. And we carry on in that fashion, so we're going to double. Now, is that a good table to help us make a decision? Let's see. We're earning really low amount on the second payment plan. We got £1, £2, £4. Day 8, we are on £128. Not bad. And it keeps doubling, so we're just making really serious money on day 10. And it looks like we're catching up with the £550 we get on the first payment plan. Now, so how many days should I work? On day 11, I'm already earning more on the second plan than on the first. Is that how I should make my decision? Yeah, I can hear you screaming there. It's not enough just to compare that. We need to say, how much money do you make in total? We will need to tally up all of this. So let's do that. We have that value, and then the new one, let's add up. And we're just adding up the money you've earned up to that day, all the payments you received up to that day. So there we are, and then let's do the same on this one. And let's copy that formula. Okay, big numbers. Oh, there at the bottom. There we are. We're having the accumulation of salaries. Let's highlight this column here. So we're actually comparing the sums of these. And looking at that in detail, the first day, the income of Plan B overtakes Plan A is when you earn 8,191 against 5,200 in total. So the day before, we're still making more money on the first payment plan, but we are ahead from the 13th day onwards. Why am I talking about that? We are going to pay attention to sequences of earnings and sums of earnings. But let's look at another example. I've got another story for you. The inventor of the game of chess, this was before the 7th century in India, presented the game to the emperor. Now, having enjoyed the new game, the emperor praised the inventor and offered a generous reward. Whatever you want. She asked for 1 grain of rice for the first square of the board, 2 for the second square, 4 grains of rice for the third square, 8 for the next, and so on. The emperor approved the payment, probably dismissing it as a humble request from this inventor and not giving it much more thought. Well, in the end, it's just a few grains of rice for an emperor. The treasurer in charge of the transaction later returned to the emperor, informing them the reward would add up to more rice than they could ever have grown. What is going on? You know the chessboard is a 8 by 8, so we have 64 squares. Surely, adding 1 plus 2 plus 4 plus 8 all the way to 2 to the power 63 grains of rice, that can't be that much, can it? Now, if you want, you can go and find out how much do we produce in the world in rice in terms of grains, but I leave you to that, and I have another problem for you. The traveling maths presenter problem. I'm taking bookings for touring with my new show, and here's my schedule for the next summer, together with the travel costs. So initially I'm going to London, Manchester and Edinburgh, and I need to travel between all these cities. And yeah, London to Manchester, I'm seeing that there's £100 fare. London to Edinburgh, £150 fare. Manchester to London, yes, trains in Britain is a little bit more expensive. It's £120. And Manchester to Edinburgh, a bargain, 50 quid. Edinburgh to London, £130. Edinburgh to Manchester, £50. So this is what I'm expecting to spend so far. Now, I have to visit all these cities and come back to the starting point. Of course, in the cheapest way possible. But no cities are to be repeated apart from the start and end. I do want to end up at home. We can attack the problem by trying out all the possible trips in my tour. I could do London to Manchester to Edinburgh, of course back to London. London, Edinburgh, Manchester, back back to London, Manchester, London, Edinburgh, and so on. These 6 trips to check, and surely we can add up the totals and calculate the cheapest trip. Doesn't sound difficult. Oh, but it turns out I just got another booking coming in. I'm going to Cardiff. And here's my updated table with my costs. Now, with this extra city, the trips I'm to make, to travel, I could do Cardiff, London, Manchester, Edinburgh, back to Cardiff. Cardiff, London, Edinburgh, Manchester, back to Cardiff, and so on. So I could just put a Cardiff at the beginning of all the trips I've studied before. That gives me 6 of them. But I could go to Cardiff second, couldn't I? And here's the list. Or I could go to Cardiff in the 3rd place, on the 4th place, and so on. How many trips do I have now with this extra city? It turns out there's 24. So with 3 cities, 6 trips that I can consider. With 4 cities, we now have 24 trips. How many trips for n cities? I'm expecting a big tour. The trips to consider with 1 more city is the same as the trips I had with my old number of cities times the new number. So trips of n plus 1 cities is the same as n times the trips with n cities. So trips on 3 cities, 6. Trips on 4 cities is 4 times trips of 3, which is 4 times 6, 24. Trips with 5 cities is 5 times the trips of 4, which we've just done. It's 5 times 24, which is 120. So I can expand this as the trips for n cities as n times n minus 1 times n minus 2 times a smaller number times 3 times 2. We could analyze the costs of all these trips, couldn't we? But how long does it take to do that job? To cost and analyze all these possibilities as the number of cities increases? Yep. As I get more and more bookings, this approach to finding the cheapest tour becomes unmanageable. I hear you cry, surely we can use computers. The number of options to look at grows very fast as we increase the number of cities to visit. So fast that this brute force approach of checking every option is not okay, not even with computers. And in the case of the traveling maths presenter problem, also known in the literature as the traveling salesperson problem, there is no known algorithm to give the optimal solution. Yep, this is why in a computing degree you study problem solving, maths, algorithms, complexity, and get to learn why some algorithms just do not accomplish the task within our lifetime. Not even with all computers in the world linked up working on the same task. We touched on this before when we talked about factorizing large numbers and deciding of a number being prime. In this topic, we will be looking at some tools for understanding sequences of numbers, like the ones we saw earlier, their growth and summation. We will not cover all possibilities, but we will introduce key tools that will allow you to make sense of the behavior of sequences. What makes a sequence more than a bunch of numbers is the order the numbers feature. Think of it as a cloakroom, of a bowling club, school play, theatre, nightclub. There is a ticket with a number for each item. Well, the analogy breaks down as the items are all different, but, 2 people could have the same coat or bag. The point is, the items in a sequence are labelled, and so there is an order. In a different day, we have a different sequence of things. When we deal with sequences of numbers, we care about the variation of numbers as the labels big-ticket numbers increase. So a sequence is an ordered list of numbers. Here's some examples of sequences. Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday, ending there. 1 minus 1, 1 minus 1, 1 minus 1, and so on. 3, 3, 3, 3, 3, and carrying on like that. 1, 11, 111, 1,000, 111, and so on. Or 5, 4, 3, 2, 1, 0, ending there. As a computer scientist, one of the basic uses of sequences will be tapping into their patterns in order to be able to use them computationally. As I mentioned in the introduction, there are many other applications, but for this video, let's be pattern hunters. So take a moment to go through the sequences presented, make some notes on the patterns found, and your own way of describing each of these sequences in words. Let's gather our thoughts on this. The first is the sequence of weekdays starting on Monday. Note that it's a finite sequence. It only has 7 terms. The second sequence is infinite, as implied by the ... which says continuing in the same pattern. So the pattern is alternating between 1 and -1. Or you could say, beginning in 1, subtract 2, then add 2, and so on. Another way of saying it would be you start in 1 and alternate between subtracting 2 and adding 2. There is more than one way of describing it. The third sequence is a constant sequence of 3s and is also infinite. The fourth could be described as begin with 1, then write another 1 next to it and carry on like this. Or we could say instead, on each position, write that many 1s. So 1 1 in the first position, 2 1s in the second position, 3 1s in the third position, and so on. Or you may be thinking of place value. Add up consecutive powers of 10. So start in 1 and add 10 for the next term, then add 100, and so on. Or you could even be thinking of binary. Anyway, I'll let you think of how to express this pattern. The fifth is a finite sequence, a countdown from 5. Or start in 5 and subtract 1 to get next term. Stop at 0. Let's have another look at sequences. I want you to write down the patterns you find so that you can describe them to another person. Here are the sequences. We're going to discuss them after the pause. Now the first is a sequence of consecutive square numbers, starting from the square of 1. The second is a sequence of consecutive cube numbers, starting from the cube of 1. The third is a sequence of fractions of ratios of consecutive numbers. The first term is 1 over 2. The second term is the second number over the third, so 2 over 3, and so on. So the nth term is n divided by n plus 1. We start needing formal mathematical language to define these sequences precisely. Now the fourth is 0 point as many 9s as the order of the term. Does that sound complicated? The fifth could be the sequence of prime numbers. There is no formula for this. The sixth sequence seems to be a power of 2 and the number that comes next. Then the next power of 2 and the number 1 over it, and so on and so on and so on. you're probably with me, we need a better way of formalizing these patterns. Join me in the next video after the quiz. In the previous video, we looked at patterns in sequences, and I think you and I came to the conclusion that our way of describing them was a little bit ambiguous and sometimes hard to define precisely with words. Now we're going to define them more precisely here. To start with, sequences have a name, which is usually a letter. Now each number in the sequence is labeled according to the order it appears. So for example, in the sequence A, that has terms A1, A2, A3, and so on. And that little number appears as a subscript. If there is an expression to compute the terms of the sequence, we then have a variable for the order. For example, n. And we write an, with the n in subscript, as the general term of the sequence. And an example of such expression could be an equals n. This means that the sequence A will be term A1 is 1, A2 equals 2, A3 equals 3, and so on. Let's see the examples from the last video. The sequence of weekdays, we would have B1 equals Monday, B2 is Tuesday, B3 Wednesday, B4 is Thursday, B5 equals Friday, B6 equals Saturday, and B7 equals Sunday. The general term could be written as Bn equals the nth day of the week, with n ranging between 1 and 7, which we write 1 less or equal to n, less or equal to 7. For C, the other sequence, C1 is 1, C2 equals minus 1, C3 equals 1, C4 equals minus 1, and so on and so on and so on. The general term could be Cn is 1 when n is odd, and Cn equals minus 1 if n is even. That is a good enough mathematical description of that sequence. But if you want an even more computational one, we could write Cn equals minus 1 times minus 1 to the power of n. Check this out. The next sequence with constant 3's, d1 equals 3, d2 equals 3, d3 equals 3, d4 equals 3, d5 equals 3, and so on, the general term would be dn equals 3 for all n. Next, we had e1 equals 1, e2 equals 11, e3 equals 111, e4 equals 1111, and so on. Or you may have read it as e1 equals 1, e2 equals 1, 1, e3 equals 1, 1, 1, e4 equals 1, 1, 1, 1. So the general term could be written as en equals the string with n consecutive ones. Or more computationally, en equals 1 plus 10 plus ... the sum all the way to 10 to the power of n minus 1. So we gave an expression to calculate the nth term. That means we define the sequence by saying what is the general term, the formula if you want. There is another way. We can define the sequence by referring to other terms. For example, start with 1, then 1. Then generate the new term by adding the two previous terms, so 1 plus 1, which is 2. And so on. So this would be, I would have 1, 1, then 1 plus 1 is 2, then 1 plus the 2 is 3, then the 2 plus the 3 is 5, the 3 plus the 5 is 8, 5 plus the 8 is 13, and so on. So this is a different way. This is called giving the recurrence relation. It is self-referential. It refers to terms of the sequence to generate a new term. This means I'm not referring to the label value. I'm not referring to the n value. So more formally, this sequence I just defined can be written as f1 equals 1, f2 equals 1, those are the first two terms, and then from n greater or equal to 3, we have that f of n equals f of n minus 1 plus f of n minus 2. Those were the previous terms, the numbers before the fn. Have another look at this n minus 1 and n minus 2 appearing in the labels of the terms. Do you find it confusing? If you do, I suggest you get n running from n equals 3 onwards and replace the value of n in the expressions. So I mean, when n equals 1, we already have that f1 is 1. That's stated explicitly. N equals 2, we have f2 that is also said to us it's 1. But then when n is 3, we enter that part that says f of n is f of n minus 1 plus f of n minus 2. We need to say, okay, when n is 3, in my expression, I replace the n by 3, so f of 3 equals, and then on this part that it's f of n minus 1, when n is 3, n minus 1 is 3 minus 1, that's 2. So f of 2 plus f of, well, I've got n minus 2. When n is 3, I got 3 minus 2, that's 1. So that's what I need to do. I need to do f2 plus f1. Well, f2 is there, f1 is there, add them up. 1 plus 1, that is 2. So I've got my f3. And then for n equals 4, f of 4 equals, let's look at my recurrence relation over there. When n is 4, I've got f4 equals f of n minus 1. When n is 4, I'm looking at 4 minus 1, which is 3, so f of 3 plus, over there, f of n minus 2. So that's f of 4 take away 2, that is f of 2. And that means the f of 3, which I got here, which is a 2, add the f of 2, which is there, and I've got value 3. So I've got 1, 1, 2, 3, and then for the next term, I will just carry on doing the same. So if you find that a little bit complicated, just continue running the example and replace the values of n in the expression, in the recurrence relation. Let's look at another one. Sequence G. We have g of n given us twice g of n minus 1 and then take away 1. And that is for n greater or equal to 2, and we are told that g of 1 equals 3. Right, so we start with 3, so g1 is 3, that's when n equals 1. When n equals 2, we want g of 2. We'll replace n equals 2 on everything in that formula there. So g equals 2 is 2 times the g of n minus 1. So that's 2 minus 1, which is g of 1. And then take away 1 altogether. Now, g of 1 is 3, so we do 2 times 3 and then take away 1. Watch Bidmas. 2 times 3 is 6. 6 minus 1 is 5. Okay. For n equals 3, g of 3 is twice g of 2, take away 1. So that is 2 times the previous guy, 2 times 5, take away 1, so that's 10 minus 1, that's 9. And n equals 4, g of 4 equals 2g3 minus 1. So that's twice the 9, take away 1, so 18 minus 1, 17, and so on. So that sequence goes 3, 5, 9, 17, and so on. Now, if we look at the differences between consecutive terms, so the second from the third, so 5 minus 3 is 2, 9 minus 5 is 4, 17 minus 9 is 8. And the next term is actually 33, so 33 minus 17 is 16. Interesting pattern. We've got a powers of 2 in the differences. Let's see what happens with the second differences, meaning the differences between consecutive numbers in the differences sequence. 4 minus 2 is 2. 8 minus 4 is 4. 16 minus 8 is 8. Does it continue like this? Maybe. We've got the second differences being the same as the differences. What does that mean? Good question. Let's look at the ratio between consecutive numbers. 5 divided by 3, 9 divided by 5, 17 divided by 9. Is there a pattern? Let's take the sequence as it is and subtract 1 from all the terms. We get 2, then 4, then 8, then 16. The same pattern we had in the differences. That's curious. Now, looking at this new sequence, 2, 4, 8, 16, the ratios between consecutive numbers are always 2. 4 over 2 is 2. 8 over 4 is 2. 16 over 8 is 2. That's interesting. I'm exploring these as these are some of the things you may want to look at when you're trying to find numerical patterns in sequences. You might be looking at differences, second differences, ratios, and you might notice even other patterns like we did. We subtracted 1 from the sequence and then took ratios. Let's look at another sequence. So the sequence Hn given by the recurrence relation n times the previous term, Hn minus 1. And we're told that h of 1 equals 5. Let's calculate the first 5 terms. So h1 is there, is 5. h2, it says, is n times h of n minus 1. So n here is 2. So this is when n equals 2. So we have h of 1. That means it's twice the h1, so it's 2 times the 5, which is 10. When n is 3, we're doing the h3 equals 3 times h2. When n is 3, that n is 3, and here we have n minus 1, so we have 3 minus 1, which is 2. And that means 3 times the previous, so 3 times the 10, which is 30. When n is 4, we have h4, so 4 times the previous guy. So 4 times the 30, which is 120. And for h5, we got 5 times the h4, so 5 times 120, and that is 600. And it carries on in that fashion. Let's see how we can describe this one. D of n is d of n minus 1 plus 2 times n minus 1, add 1. And the starting value, d1, is 1. So how does this one go? Let's write it down. Okay, so that's for n greater or equal to 2. So we've got d1 is given, d2 is when n is 2, so we have d1 plus 2 times when n is 2, n minus 1 is 1, and then like this. So d1 is 1, so 1 plus 2 plus 1, and that's 4. d3 is n is 3, so n minus 1 is 2, so I have d2 plus 2 times the n minus 1, so 2 times 2, add 1. d2 was 4, so I got 4 plus 1, that is 9. d4, so n is 4, that means I got d3 plus 2 times 3 plus 1. So that's 9 plus 6 plus 1, which makes 16. And let's do one more. That's going to be d4 plus 2 times 4 plus 1. That is 16 plus 8 plus 1. And that makes 25, and so on. Now, is there a pattern you can see there? It is described as a recurrence relation, but the numbers go as 1, 4, 9, 16, 25. And you're probably thinking, this is a square number sequence. It is. We could write it as a square number sequence, so we could write it as dn equals n squared for every value of n, and at the same time, that is the recurrence relation. So you can have both. Can you always write a formula, like a general term, for a sequence that is given as a recurrence relation? That's a good question. We're not going to worry about that in this course, but I'll let you to investigate that for your own satisfaction. Now, one more. Sorry, I said that wrong. The one more is not. Now, still on this sequence, we can look at the differences between consecutive terms. 4 minus 1 is 3. 9 minus 4 is 5. 16 minus 9 is 7, and so on. Is it the prime number sequence? No, we need to look at more terms. The next difference would be 9. Actually, the odd numbers. Of course, there's a question, can we prove it? You can by looking at that sequence. I'm not asking you to do so, but I just want to get you to think about all these patterns. Now, still on that, on the sequence of differences, if we do second differences, we get 2 every time. Is it a coincidence? No, it is not. If we look at the expression for dn, yes, it is a sequence of squared numbers. No, dn is the sequence of square numbers. So being a sequence of square numbers, the second difference well, it's not really a coincidence. dn being a sequence of square numbers, that squaring actually means that the second differences should be constant. There's no reason why you should know that, but I'm going to plant that in your brain for now. Now, when you work with data and are looking to find patterns, you can also use a spreadsheet to automate your pattern search. Hello there, we're going to look at a special type of sequence called the arithmetic progression. Let's look at the sequence AN that starts with 4 and it goes with 6, 8, 10, 12 and so on in the same pattern. Probably notice what the pattern is. We're adding 2 every time to generate the next number. And I can check that by doing the subtraction of 2 consecutive terms. So 6 minus the 4 is 2, 8 minus the 6 is 2, and so on. So I'll write that using the terms. So A2 minus A1, it's 6 minus 4, that's 2. A3 minus A2 is 8 minus 6, which is 2. And I'll carry on doing consecutive subtractions and I will always get 2 because the law of generating the next term is always adding 2 to the previous term. That means we can write it as a recurrence relation, and that means that the A next is the A previous plus 2. Okay, we're almost there because it's not a very mathsy way of writing that expression. Let's write it properly with the variable in the label. So A of n plus 1 is the A of n add 2. So I'm adding 2 to the term an, just to make sure we're not adding 2 to the label. We're adding 2 to the value of the term. And as usual, we need to say what's the first term, and that is 4. So that completely defines the sequence above. But you may be asking, can we do better? Can we have a formula where we just plug in the value of n and gives me the value of the term of order n? In this case, yes, we do, but let's look at how we build that. So from looking at the sequence, which I'm going to write again here. So we got A1, 4, A2 is 6, A3 is 8, A4 is 10, and so on. We can rewrite this as A2 is 4 plus the 2. A3 is 4 plus the 2 and another 2. And A4 is the 4 plus the 2 plus the 2 plus another 2. I wrote all that detail because I wanted to see how the formula is going to appear. I start with 4 and then I add a certain number of 2's. How many 2's do I add every time? For the second term, I add 1 2. For the third term, I add 2 2's. For the fourth term, I add 3 2's. So for the nth term, I'll start with 4 and I add 2's, but just one s than the n. And that will be the expression for the sequence that is an arithmetic progression with common difference 2 and first term 4. Traditionally, we write D for common difference, and the first term is A1. So I'm going to rewrite this formula in that way. So AN is the first term for added the common difference D n minus 1 times. And any arithmetic progression will obey this law. Any arithmetic progression will have a common difference D and will have a first term A1, and the expression for the general term is given by this formula. Given any sequence, how do you check if the sequence is an arithmetic progression? We need to check if there is or not a common difference. For example, if we have 1, 3, 5, 7, 8, 10, 11, and so on, what do you think? Is this an arithmetic progression? Do the terms always increase by the same common difference? From 1 to 3, you add 2. From 3 to 5, you add 2. It's looking good. 5 to 7, you add 2. But 7 to 8, you just add 1. It's breaking the law of adding the same common difference every time. So this isn't an arithmetic progression. And you can prove it by just saying the common differences don't match. So you can say this is A1, A2, A3, A4, A5. You can say A5 minus A4 is 1, but A2 minus 1 is 2. These aren't the same. These are different. Therefore, there isn't a common difference. And if there isn't a common difference, then we don't have an arithmetic progression. Now, the first example we saw was an increasing arithmetic progression. We can have common differences that are negative. We can have common differences that are fractional. We can have any common difference as long it is the same difference over and over again. So 0, 1/2, 1, 1.5, 2, and so on. Common difference 1/2. That's an arithmetic progression. The expression would be AN is 0, add n minus 1 times 1/2, which I can just tidy up as n minus 1 over 2. That is an arithmetic progression. For example, 3, 2, 1, 0, minus 1, and so on. The common difference is minus 1. So D is minus 1 because it is A2 minus A1 is 2 take away 3, which is minus 1. A3 minus A2 is 1 minus 2, which is minus 1, and so on. And the first term is 3. So the general term is AN equals 3 plus minus 1 times n minus 1, the common difference times n minus 1. And this comes as 3 minus n plus 1, which is just 4 minus n. You can check, just replace n by 1, 2, 3, 4, 5 and so on and see the result. When n is 1 you got 4 minus 1, that's 3. When n is 2 you got 4 minus 2, that's 2, and so on. In summary, there's two ways we can define arithmetic progressions. By writing out its recurrence relation or by giving the general term. They both need the knowledge of the common difference. I'll write them here. As a recurrence relation, it would be that an plus 1, the next term, is an add the common difference, and we need to make explicit what the first term is. The general term is given as an being the first term adding the common difference, not quite n times, but n minus 1 times. So you can either use this one or the other one. And that's arithmetic progressions. We're going to look at another special type of sequence. Say we've got 3, 6, 12, 24, 48, and so on. I think that was enough to see the pattern. It is a doubling sequence, and I mean that any new term can be computed from the previous term by multiplying by 2, by doubling. That means that I can say that if my sequence is called A new term for A is twice the previous term, let's say the old term. Okay? Let's write that more mathematically. If the new term is the term of order n, the previous term is the term of order n minus 1, and so the new term is computed by doubling the previous. That expression isn't enough to totally define the sequence I've written. Any doubling sequence would be, so I need to define what's the first term. This is how we define sequences given by a recurrence relation, as we've seen earlier. So the first term, in this case, is 3, and so these two together define this special sequence. This is called a geometric progression, and it is so because any new term is computed by multiplying the previous by a common ratio. The common ratio for this one is 2. So I'll say the common ratio, usually denoted as R, is 2 for this sequence. Now, you might be wondering, can we do better than this? Can we write an explicit formula for the term an? Yes, we can. Let's look at it. So the first term of order 1 is 3. The second term, we said it is doubling the previous one. So it's 2 times the 3, which is 2 times the A2, right? And then the next one is twice the previous, which is twice the 2 times 3. And the next one will be twice the previous, so twice the 2 times 2 times 3, and it carries on like that. You're probably spotting the pattern. We have powers of 2 over and over again. So here on A4 I've got 3 2's multiplying together, so that's a 2 to the cube times 3. The previous one, A3, I've got 2 2's, so I've got 2 squared times 3. And A2 is just 2 to the 1 times 3. And if we want, we can write here that is 2 to the 0 times 3, because 2 to the 0 is 1. And this pattern can be extended to the general term. So I can say that term of order n is going to be a power of 2 times 3. How many powers of 2? Is it n or is it less? Let's look. For A4, I've got 2 to the 3, so 1 less than the number 4. And therefore, I have 2 to the n minus 1 times 3, which might be a bit more elegant to write in this way. Okay? So, and 3 is the first term of the sequence, and then I times it by 2 to the power of n minus 1. And that gives me the term of order n. For any ratio r, so that's the common ratio, the general term of the geometric progression will be a1, the first term, times r to a certain power, and remember it is 1 less than the n, so n minus 1. Just a little note to say, how do we check that the sequence we have in front of us, it is really a geometric progression? The key thing is that there is a common ratio, and that means that the ratio between consecutive terms of the sequence is the same number over and over again. So I look at a2 over a1, which was, a2 was 6 and a1 was 3, so that ratio is 2. I also need to look at the next pair, so a3 and a2. So a3 divided by a2, and that is 12 divided by 6, so that's 2, and so on. For this sequence, it is true that a to the n plus 1 over a to the n is always 2, which is the common ratio r. Let's look at another example. The sequence 1, 3, 9, 18, 27, and so on. Is this a geometric progression? We're going to check if there is a common ratio. We're going to look at ratios of consecutive terms. We do the second term over the first, so we do 3 over 1, that is 3. We now do the third over the second, so 9 over 3, that is 3. Then we look at 18 over 9, that is 2. This is not the same number, therefore it's not a geometric progression. So, not a geometric progression, because the common ratio needs to be common. Let's look at another one. We have 9, 3, 1, 1/3, 1/9, 1 over 27, and so on. What is the pattern here? From one term to the next, I'm multiplying by 1/3, or I'm dividing by 3, whatever you like to say. And so on, and that matches. Well, I wrote there that I multiply by 1/3 every time. You could check once again by doing the ratio I explained earlier. So we would do 3 over 9 is the same as 1 over 3. It's the same as 1/3 over 1 is the same as 1 over 9 over 1/3, and so on. It's always 1/3, and that's our common ratio. If you found the fraction over fraction a little bit confusing, I'll just do a quick recap on that. 1 over 9 over 1/3 is 1 over 9 divided by 1/3, which, to divide fractions, we turn that into a multiplication of the reversed fraction. And so you do 3 over 9, which is 1/3. Okay. Now, we have a common ratio of 1/3. Let's write the expression for this geometric progression. So let's call that sequence B. So Bn will be the first term, which was 9, times the common ratio, which is 1/3, to the power of n minus 1. Now, we can tidy this up a bit, because 9 is also a power of 3. So this can be as 3 squared from the 9 over 3 to the n minus 1, and that comes from the fact that 1/3 to the power of n minus 1 is 1 to the power of n minus 1 over 3 to the power n minus 1, and 1 to any power is just 1. So this is 1 over 3 to the n minus 1. Okay, so just a little side comment for you if you needed that. And now rules of powers just say that I will do 3 to the n minus 1, take away the 2 on the top, so n minus 3. Okay, and if I want I can write in this way as well. But I'll be really happy with a result written as that. I've got a question for you. Say we have a geometric progression with common ratio 4 and first term 1. Is 1000 a term in this geometric progression? Let's check it. So I've got a geometric progression with ratio 4 and first term, so let me call it A1, 1. And I want to know if 1000 is a term in this sequence. Is there any n such that 1000 equals it? Is it possible? Let's solve the equation. The equation that involves the general term of the geometric progression. So from here I know that an should be 1 times 4 to the power of n minus 1. Okay. So is there an n such that 4 to this power is 1000? In other words, is 1000 a power of 4? It is not. You can check through the calculator, you can run all the first powers of 4 and 1000 isn't one of them. If we run through the powers of 4, get 1, 4, 16, 64, 128, and you carry on multiplying by 4, you will never get to 1000. So there is no such n, and therefore (1000) is not in this sequence. Is not in the sequence an. The ratio of a geometric progression can also be negative. For example, the sequence 1 minus 2, 4 minus 8, 16 minus 32, and so on. The common ratio is negative 2. So the terms alternate between a positive and a negative number. A negative common ratio can also be a fraction. For example, the sequence 1/3 minus 1 over 9, 1 over 27 minus 1 over 8, and so on, is a geometric progression of common ratio minus 1/3. I leave you with a question. How do you imagine geometric progressions behaving as n grows larger and larger? I'll give you a hint. It depends on the type of common ratio. Modular arithmetic is a tool used in one of the most popular methods for generating sequences of numbers that appear random. Here's the setup. We're going to use modular arithmetic, and we're going to choose a modulus, a multiplier, an increment, and a seed value. I'll show you. So we're going to use a recurrence relation. So I'm going to write that my next random number, Rn plus 1, is congruent with m times Rn, which is the previous number, plus an increment I, mod c, the modulus for this particular method. Now c needs to be a positive number. That's the modulus. M is going to be the multiplier. I will be the increment. And our seed value R0 has to be between 0 and the modulus, but less than the modulus. So this will be my formula for generating random numbers, but let's see how random they really are. In this example, I'm going to choose the modulus to be 5, the multiplier will be 1, the increment will be 1, and we'll have a seed value of 1 as well. And so my expression boils down to the next random number, Rn plus 1, will be congruent with Rn add 1 mod 5. So I'm going to add 1 to the previous value mod 5. What do I get? Well, if I start with 1, the next number will be 2, then 3, then 4, and then, not 5, 0, then 1, and 2, and 3, and 4, and 0, and so on. Yeah, it's not very random looking. Let's look at another instance. We keep the modulus 5. We're going to up the multiplier to 2 and the increment to 2 as well. And let's have 1 as the seed value. So we're going to get my expression. So next random number will be twice the previous, add 2, mod 5. And let's see what do we get. We start with 1. And then we get 4, 0, 2, then 1, 4, 0, 2 again, and 1, and we'll be repeating. It's a little bit better, but it's still not very random. What should we do? How do we make these sequences more random? Well, let's try another example. You will play with it, but let's try with a different modulus. Let's go for modulus 13. Yeah, let's do doubling. Let's have a multiplier of 2, an increment of 0, and start with a seed of 1. Now, do this one. Do this one yourself. I'm going to write the expression. It will boil down to doubling mod 13, and we start with seed 1. What do we get? Take your time, do a few calculations, write it down. Okay, let's have a look at the results. It takes a bit longer to repeat the pattern, doesn't it? Does it look a little bit more random to you? We still go 1, 2, 4, 8, clearly a doubling, and then 3, 6, 12, 11. I would like to know your comments, and do share your ideas in the discussion forum. Now, the task you will work on next is self-assessed, but the summative assessment will refer to things you can only understand if you have performed the task to a satisfactory level. So what will happen is we will look at the examples we've done before, and I wanted to explain why the numbers repeat, why they are periodic, and I would like you to use as much of mathematical statements as you can. I also wanted to make it explicit what is the period of repetition, so the length in terms of the parameters. So I wanted to relate that to the values of the modulus, the multiplier, the increment, and do that as much as you can. Now, using the same formula we've given you before, I'd like you to write sequences of numbers by changing the parameters. But I'll be a bit more specific. I would like you to try at least 10 different sets of parameters. So do also work with the ones I've given you before, but those will not be included in this count of 10, okay? And then in terms of how long should you go for in calculating the terms of a sequence, it will be at least 2 times c terms. So for c equals 13, I wanted to do at least 26 terms of that sequence. But if you need to write more to make the pattern explicit, do, okay? And here's a suggestion of the sets of numbers that I would like you to use. So I'll suggest these 3, but you will need to come up with 7 more that aren't the ones in the examples. And then once you've done all these calculations, I'd like you to group parameters in families according to the properties you're finding relevant to decide how good these sequences are at appearing random. Now, everything you say in your work, I would really want you to justify your observations and illustrate that with calculations. And any predictions you make, I would like you to back it up, not just with the examples of the calculation, but the best mathematical explanation you can write. Just try your best. If you decide to use a spreadsheet to help with any of the calculations, then the patterns you find need to be explained in terms of how you would do those calculations by hand. It's also a very good idea to double check that what you do in the spreadsheet is actually correct by doing it by hand. Now, if you calculate by hand, I want to see you working for at least 3 examples that involve calculating something like A mod B when A is larger than B. So not just the simple mods. I want you to go over the modulus at least 3 times and show it explicitly. We looked at how to formally define sequences of numbers by either giving an expression for the general term or by giving a recurrence relation between terms. We looked in detail at 2 special types of sequences, one with a constant increment, the arithmetic progression, and another with a constant scaling factor, the geometric progression. We are interested in the behavior of a sequence as more and more terms are computed. We sometimes need to add up a certain number of terms. You wonder, are there any shortcuts to this? We will see in the next lesson. We're going to talk about series, and series is all about adding up terms of sequences. Now, back to us humans, most cultures have cumulative songs, songs that have a structure that is changed using progressive addition, resulting on each verse being longer than the previous. Do share such examples with us in the discussion forum. An example of a cumulative song is the British song, The 12 Days of Christmas. You may have heard it in the middle of shopping for presents. On the first day of Christmas, my true love sent to me a partridge in a pear tree. Let's read the verse. And it goes like this. On the second day of Christmas, my true love sent to me 2 turtle doves and a partridge in a pear tree. On the third day of Christmas, my true love sent to me 3 French hens, 2 turtle doves, and a partridge in a pear tree. And he carries on like this with more gifts in this pattern until there are 12 drummers drumming on the last one. That's a lot of noise for sure. Well. How many gifts are there all the way to Christmas? Okay, so in the quiz, you've written day 1, you've got 1 gift. Day 2 is 1 plus 2 gifts, so there's 3 gifts. Day 3, 1 plus 2 plus 3, so there's 6 gifts on day 3, and it carries on like that. So by day 12, we have 1 plus 2 plus 3 plus 4, all the way to 12 which is 13 times 6 gifts. So 78 gifts on day 12. So what we want to know, the total sum of gifts all the way to Christmas, is the addition of that 1 plus the 3 plus the 6 added with 78. The way we write the pattern of presents in one specific day is related to an arithmetic progression. On day n, we have the sum of the first n terms of the arithmetic progression with first term 1 and common difference 1. So 1 plus 2 plus 3 all the way to n. So we write this using a summation symbol, which is the Greek letter sigma, and it looks like this. Sum from k from 1 to n of k. We're adding k as k ranges from 1 to n. That's what that means. The symbol sigma means the sum, and then the k equals 1 means that the index of summation, so the variable of the sequence, is k, and we start with value 1, that's we say k equals 1, and the n on top is the last limit, is the last value that we replace k by. So let's look at what happens as I replace n by different values. So when n is 1, we get the sum from 1 to 1 of k, which is just 1. When n is 2, I'm adding two terms. I'm adding the term when k is 1 and when k is 2. So 1 plus 2, which is 3. When n is 3, I write the sum from k equals 1 to 3, which is 1 plus 2 plus 3, which is 6, and so on. So this is what the summation symbol, the series notation, looks like and how we use it. So when n equals 12, I've got the sum from k equals 1 to 12 of the term k, and so as I replace k by all those values, I get 1 plus 2 plus 3 all the way to plus 12. So that's the extended form of this summation, and that totals 78. Now, in total, it turns out that there are 364 presents in the whole of the 12 days of Christmas song. And actually, I'm here adding the sums. So it's another use of sums. But just for us to complete the exercise for Christmas, I translate this as the sum from k equals 1 to 12 of the total presents on day n. So I'm adding 1 plus 3 plus 6 all the way to plus 78, which I've done the calculations, have you? Is 364. Now, it is a long sum to do, 12 numbers to add up, plus you have to work out all of these in between. You and I probably wondering, is there a shortcut to work this out? I mean, if the song went on and on for another few days instead of just 12 in the same fashion, and in the terms of wanting to budget for this expense, you know, is there a way of working out this result? Yes, there is. You will find out as we go along with this lesson. Now, back to the sequences we saw in the introduction to this topic. Let's rewrite the rice reward as sequences and series. The amount of grains of rice for square of the chessboard, for square n, is given by the sequence an equals 2 to the power n minus 1, with n ranging from 1 to 64. The total reward, it's the sum of all these terms. So the total reward is the sum of the series, the sum of an. Now we need to work out what's the first and last value for the index of summation. We want to have 1 plus 2 plus 4 plus 8 plus 16 all the way to adding 2 to the 63, not 64. There's 64 squares, but we start in 1. So we write 1 plus 2 plus 4 plus 8 plus 16 dot, 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 all the way to the 64, and that is written as the sum of from n equals 1 to 64 of 2 to the power of n minus 1. So this is how we transform this sum into a summation symbol. Now, notice that we could change the limits in the sum and have it written as the sum from n equals 0 to 63 of 2 to the power of n. It's just a cosmetic change. They're exactly the same sums, but they're presented slightly different. All I've done is that because I've got an n minus 1 in the other series, and I've got the range from 1 to 64, if instead of n minus 1 I have n, then I'm starting at 0 and ending at 63. So the idea here is that when we add up sequences incrementally, we are creating a new sequence, the sequence of partial sums. But because this sequence is specifically generated by adding a consecutive number of terms of a sequence, we call it a series. So that's what a series is the sum of consecutive terms of a sequence. And in some cases, we have shortcuts to find this sum. At the start of this topic, we talked about a job offer with 2 payment plans. We wrote the sequences for those and we did the sums in our spreadsheet. Option 1 was we had £100 in the first day and then £50 extra done the day before in any new day. And option 2 was £1 to start with and then the pay was doubled every day. So we saw option 1 is an arithmetic progression of common difference 50 and first term 100. And option 2 is a geometric progression with first term 1 and common ratio 2. Now, in terms of the arithmetic progression, the general term is an is 50 times n plus 1. You can work it out from the formulae we worked. And the sum up to day n is the sum from k equals 1 to n of 50 times n plus 1, which is in the expanded form 100 plus 150 plus 200 plus all the way to 50 times n plus 1. For the geometric progression on payment plan 2, the general term is bn equals 2 to the power of n minus 1, or just 2 to the n divided by 2. So the sum up to day n is the sum from k equals 1 to n of 2 to the power of n minus 1. So when we looked at the spreadsheet, which I actually show you, we had results for the sums. So we can actually write that the sum on the 13th day, which I calculated and highlighted last time, the sum of k from 1 to 13 of AK from our spreadsheet was 5,200, and the sum for the second payment plan from 1 to 13 was 8,191. So we can say the sum of the first payment plan over 13 days is less than the sum of the second. So that means that we would choose payment plan 2 if we were planning to work for 13 days or more. Now, when we were calculating the presents on a particular day in the Christmas song, we have a special type of number coming up, and I really need to talk to you about that. So we had numbers, we had the sum 1 plus 2 plus 3 all the way, if it was day 7, it would be all the way there. And this sum, which is the sum of a very particular arithmetic progression when the common difference is 1, the result of these sums is called a triangular number. What I mean is we have number 1, that's a triangular number. Number 1 number 1 plus 2 being 3 is also a triangular number. The 1 plus 2 plus 3, which is 6, is also a triangular number, and so on. All the numbers written in this fashion, and that's because that many dots can be arranged in a triangular pattern. So 1 is just a very simple triangle. 3 can be written as 1 and then 2 underneath. That's a triangular pattern. 6, it's like the one before, but with a new row. Triangles, how beautiful. And it carries on. The next triangular number will have 4 rows. So you have a 1 with a 2, with a 3, with a 4. So that's 6 plus the 4, that's 10. So all of these are triangular numbers, and they will come up again and again in your mathematical and computing life. So when we look at the sum of the arithmetic series, you will get a formula for triangular numbers. So let's expand the following series. We have the sum from n equals 3 to 7 of the expression n plus 1 over n. Let's write this in the expanded form. That means we're going to replace n by the first value and then carry on until I get to the last value. So when n is 3, I have 3 plus 1, which is 4 over 3, plus when n is 4, I have 4 plus 1 on top, so it's 5 over 4. When n is 5, I get 6 over 5. When n is 6, I get 7 over 6. When n is 7, which is the last one, I get 8 over 7. So this is the expanded form, and to find the result, you just add up those values. And this equals 6.09285714 recurring. I mean, it's going to be a fraction, so it should be either finite or recurring. So this is the value. So let's look at another one. So we've had a sum from k equals 2 to 5 of k cubed. It's important that the index of summation, which in this case is k, because that's what k equals to, is the same as the variable used in the sequence. So I've got k cubed. So I've got 2 cubed plus 3 cubed plus 4 cubed plus 5 cubed, and you can work out what that is. Another one, sum from I equals 1 to 4 of the number 10. Now, I is the index of summation. The number you're adding every time does not change with I. So you're adding 10 to itself as many times as I goes from 1 to 4. So 10 when I is 1, 10 when I is 2, 10 when I is 3, 10 when I is 4. 4 times. 4 times 10, just 40. So in general, if you have a constant number added between I equals 1 to 4, I equals 1 to 20, it's that many times the constant number. And the sum from n equals 2 to 6 of 2 to the power of 6 minus n in the power. When n is 2, I've got 2 to the 4. When n is 3, I got 2 cubed. When n is 4, I've got 2 squared. When n is 5, I've got 2 to the 1. And when n is 6, I got 2 to the 0, which is 1. And then you can work that out as well. Let's now do the other way around. Let's start with sums and write it with a summation symbol. So if we're adding the odd numbers from 1 to 13, 1 plus 3 plus 5 plus 7 plus 9 plus 11 plus 13, this can be written as the sum. And now I need an expression that is going to generate all these odd numbers. Well, we start in 1 and then add 2 every time. So that's an arithmetic progression with first term and common difference 2. It will be 2n minus 1, will do the trick. From n equals 1, and now how many terms? 1, 2, 3, 4, 5, 6, 7. 7. Let's check that when n is 1 we get the first term. When n is 1 we get 2n minus 1 is 2 times 1, which is 2, take away 1, that's 1. And when n is 7 we have 2n minus 1 is 2 times 7, which is 14, minus 1, which is 13. So yes, those are correct. And I'll put brackets to make sure that the 2n minus 1 is all being added up in the series. So let's now do a half added with a quarter, added with an eighth, and so on, all the way to 1 over 64. So this is a geometric progression with common ratio 1/2, with first term 1/2. So this will be the sum. Let's have a variable n, and we need a half to a certain power. Now we can simplify things by choosing a value of n that will give us a half on the first instance. So when n is 1 we get a half, and then got how many terms? Well, we need to do a half to the power of n equals 1 over 64. So we just need to work out when 2 to the n, what n makes 2 to the n being 64. So 64, we got 2, 4, 8, 16, 32, 64, that's power 6. So 2 to the 6 is 64, so n is 6. There we are. So we wrote that sum of a geometric sequence, so a geometric series with a summation symbol. Let's do another one with alternating terms, as in positive, negative, and so on. Okay, we got this one. That looks like a geometric progression. We're doubling every time, but not quite. We're multiplying by -2 every time. So we will have -2 to some power. Let's put it n, and then let's work out what will be the value of n to give us 1 to start with, and then -2 next. So if n is 0, -2 to the 0, it's 1, so that works. And then when n is 1, -2 to the 1 is -2, so that's fine. So n equals 0 will give that guy, then n equals 1, and all the way to 64. But we can just count the numbers, so 0, 1, 2, 3, 4, 5, 6. Okay, or we could use the same technique we use in the other one to work out the power of 2. Another one. 1/2 plus 1/3 plus 1/4 plus 1/5 plus 1 over 6. That one, it's actually called harmonic series. We're having 1 over a number that is increasing, that denominator is increasing. So we have 1 over n, and n begins in 2 and ends in 6. Now, be very careful of division by 0. Don't make n equal 0 in that one. And one more. Say we're adding 4 plus 9 plus 16 plus 25 plus 36. Those you'll probably recognize that are square numbers. 4 is the square of 2, 9 is the square of 3, 16 is the square of 4, 25 is the square of 5, 36 is the square of 6. So we're doing squares of numbers, and the first square is the square of 2, and the last square is the square of 6. Because the summation symbol has behind it a sum, we can add and subtract and multiply by a constant these sums. So we can do things like, if I have the sum of n plus 2 to the n, and my n is ranging from 1 to 4, I can, because I'm adding the n and the 2 to the n inside the bracket, I can separate the sums. I can say, I can add the n's and I can add the 2 to the ends, but I need to be careful with the variable. It's from 1 to 4, and it's from 1 to 4 on both. So basically what I'm saying is that if I'm adding 1 plus 2, which is when n is 1, and then 2 plus 2 squared plus 3 plus 2 cubed plus 4 plus 2 to the 4, I can choose to add the 1 with the 2, with the 3, with the 4 in one summation, and the 2, 2 squared, 2 cubed, 2 to the 4 in another summation. And that's why I did one summation for the 1, 2, 3, 4, and another summation for the powers of 2. We can do that, and we can also do the subtraction of 2 summations. We can also do 5 times a sum. Say we have n plus 2 to the power of n, and my n could be ranging from 2 to 4. If I multiply everything by 5, that is the same as saying I have the sum of multiplying the number inside, the expression inside, by 5. Okay, so that is saying if I got 5 times the sum that it's 2 plus 2 squared, which is the first, for when n is 2, plus 3 plus 2 cubed, plus 4 plus 2 to the 4, well, with these little brackets here, is the same as doing the sum of every single term multiplied by 5. I'm just saying I can do 5, 2 plus 2 squared, plus 5, 3 plus 2 cubed, plus 5, 4 plus 2 to the 4. So that's what that means, putting the constant inside the summation or outside the summation. Now, what's really important is that when we multiply 2 sequences inside the summation symbol, that is not the same as multiplying the summations. It is not. So what I'm saying is that if you have n times 2 to the n, and you're doing this sum, this is not the sum of n times the sum of 2 to the n. It is not the same, okay? And the way you can look at that, expand this sum, and then multiply the results together, and you'll see it is not the same. You may find 1 or 2 examples where they are, but in general they are not. So now join me in exploring all these concepts in more detail and answers to some of the questions raised in the next videos. We looked at series. Let's now look at some examples where we can calculate the results without having to add the terms one by one. I mean, using a shortcut, using a formula. The first of such examples is the arithmetic series. So let's look at a simple one. So we have 1, 2, 3, 4, 5, and so on. It is an arithmetic progression with common difference 1 and first term 1. The series will be the sum of all of these terms. And say we're going to add them all the way to 100, just because I really like the story of the mathematician Gauss that worked out the formula for this when he was a primary school boy. I'll leave you to find out more. So we want to add all these numbers, 1 all the way to 100. The clever thing that Gauss did was that to note that the first and the last term, 1 and 100, add up to the same amount as 2 and the term before 100, so 99. They all add up to 101. And the same goes on to all the other pairs of numbers in the middle. So 1 plus 100 is 101. The other pair, 2 plus 99, is 101, and 3 with 98 is 101, and so on. All we need to find out is how many pairs are there. So the last pair to add up will be the middle one, with 50 plus 51. So there are 50 pairs altogether, which means that the sum above there is calculated with 101 added to itself 50 times. So 101 times 50, which is 5,050. Large number. Let's take a rule out of this example. So what we did was we added the first and the last term. We took that sum, in this case it was 101, and we multiplied that by the number of pairs. How could we calculate the number of pairs? Well, we've got 100 numbers, so is 100 divided by 2, it's 50, is the number of pairs. So we can generalize the pattern here to any arithmetic progression. So we did the first term added with the last term, and then times the number of terms, all divided by 2. So in the example we just saw, A1 was 1, AN was 100, and we had 100 terms, and we divided this by 2. So we had 101 times 50. The 50 came from there. Okay. The sum of an arithmetic progression. In the example we saw, we had an even number of numbers to add up, which meant we had a number of pairs. What if we had an odd number of numbers to add in the series? This formula would still work if we're adding an odd number of terms of an arithmetic progression. Let's look at 2 examples of this formula in action. We want to calculate the sum of odd numbers from 1 to 100. So we want to add 1 plus 3 plus 5 and so on, all the way to 99. Okay, all the odd numbers. We can use the arithmetic series formula if this is actually an arithmetic series, and it is. It is an arithmetic progression with first term 1 and the common difference 2. Therefore, the general term will be 1 plus n minus 1 times 2. So the sum of this sequence, when we run through all the odd numbers, is going to be the sum when n is 1 all the way to n equals 50. Let's check. When n is 50, we got 49 times 2 plus 1, and that gets us 99. Okay, so this is given by the first term plus the last times 50, which is the number of terms, divided by 2. So that means I do 1 plus 99, which is 100, times 50, divided by 2. That's 50 times 50, which is 2,500. Pretty neat. If I wanted the sum of even numbers from 1 to 100, I'm looking at adding 2 plus 4 and so on all the way to 100. I want to write it as a sum of an arithmetic progression. And let's write what's Bn. And Bn is going to be 2 plus n minus 1 times the common difference, which is still 2 in this case. And the last term is 100, and I achieve that when n is 50. because I start with 2 and I add 49 2's to it to get 100. So it's also the sum to 50, and therefore this result is the first term plus the last, that's 102, times 50, divided by 2, and that turns out to be 51 times 50, which is 2,550. Let's now look at the sum of a geometric series. Say we have 1 plus 2 plus 4 plus 8 and so on, all the way to 1024 to add up. The sequence we are adding in this series, it is a geometric progression. It begins in 1 and the common ratio is 2. It is a doubling sequence. The general term is Bn, which is 2 to the power of n minus 1. And we want to add all the terms all the way to 1024. We need to work out how many terms that is to start with. So 1024 is 2 to the power of 10. We are adding 2 to the 0, 2 to the 1, all the way to the power of 10. That's 11 terms. So we want to add Bn from n being 1 all the way to n being 11. So it's 11 terms. So let's say for now we're going to call this sum big S. And I'm going to write it on top as well. So that is our sum. It's quite a clever little trick to work out this sum. We're going to multiply the sum itself by the common ratio, by 2, because this is a doubling geometric progression. So we're going to multiply that sum by 2, and that's going to help us. Let's see. So 2s, and for us to appreciate the pattern, let's use the sum at the very top. Twice the sum is going to be twice every term. So I'm going to add 2, which is twice of 1. I'm going to add 4, which is twice of 2. Twice of 4, twice of 8, all the way to twice of 1024. Okay. And now let's compare the two. Let's compare the sum and twice the sum. Most numbers are the same. As in, I've got numbers from 1 to 4 all the way to 1024. And 2s goes from 2 to 4 and so on. And here, there's a 1024 as well, which is the term that comes before the 2048. I'm going to rewrite it there. Now the clever bit is to subtract the two sums. So 2s goes from 2 plus 4 plus 8 all the way to 2048. S is 1 plus 2 plus 4 and so on, all the way to 1024. And now if I subtract s from 2s, I'm going to subtract 1024 from that 1024. I'm going to subtract all these numbers here in the middle, and these two, and these two, and these two. So those are all going to cancel out, and I'm going to end up with 2048 minus the 1. So 2s minus the s is going to end up being 2048, take away 1. But all we did was to start with twice the sum and subtract the sum. That means I just got one sum here. So this is the value of the sum, and that is going to be 2047 from here. And it's done. We didn't have to add up all those numbers. This is the shortcut. The good news is that this also applies to any geometric progression, not just to the one we saw. And the same method is done. I'm going to write down the general case. So if we are doing the sum of a geometric progression that starts in 1 and then this ratio r, these are going to be the terms, and I'm going to add n terms of this series, so the last term is r to the n minus 1. The trick I did was to multiply the sum by the common ratio, so I'm going to do r times s. And as I do that, I have the 1 on the sum times r, so I'm going to have r. The r of the sum times r is going to be r squared, and so on. Every term above is going to be multiplied by r. But I have as many terms in one and the other. So the last one is r to the power of n. And now I'm going to subtract. I'm going to do rs take away s. And that means these here will cancel out, so they will subtract to 0. The same with everything in the middle. And I'm left with r to the n take away the 1. Now let's look at the left-hand side. This is r times s minus s, so that is r take away 1 multiplied by the sum. On the right-hand side, I've got r to the n minus 1. I can divide both sides of the equation by r minus 1. And so I have that s is r to the n minus 1 divided by r minus 1. Of course, if r isn't 1. If r was 1, we didn't need this formula to add it up. It wouldn't be an interesting geometric progression. So this is the sum of n terms of a geometric progression. I'm going to write s with a little n underneath. Of course, we are using the series notation. So the series notation will have the big sigma. So I'm going to rewrite that as the sum of the powers of r all the way from 0 to n minus 1. Remember, we were doing 1 plus r plus all the way to r to the n minus 1. So those are the limits of my sum. This is given by the formula we just wrote, which is r to the power of n take away 1 over r take away 1, provided r isn't 1. So that is the sum of a geometric series. Let's just see that formula applied to the sequence we just added up. When r was 2, the sum of 2 to the k running from 0 to 10, I know we wrote k going from 1 to 11 on the other example, but we're using the expression of 2 to the k here, so this is the same value. This is using the formula 2 to the n here is 11, minus 1, 2 minus 1, and that is 2 to the 11, take away 1, because the denominator is 1, and that is 2048, take away 1, as we had calculated before. Okay. Let's look at another couple of examples. Say we've got the sequence 0.3, 0.06, 0.012, and so on. It is a geometric progression. The common ratio is 0.2. And you would verify that by doing 0.06 divided by 0.3. And that is 0.2. And it's the same as 0.012 divided by 0.06. Okay? So it is a geometric progression with ratio 0.2. Let's add the first 5 terms of that series. So we want to add an when n goes from 1 to 5. And here what we do is we note that this series is not exactly powers of the ratio, but the ratio is 0.2. The general term of the sequence, we're going to write it up here, the general term for the sequence is an equals 0.3 times 0.2 to some power. Well, when n is 1, I'm not multiplying by 0.2, it's only when n is 2, so I'm going to do n minus 1. And so the sum I've got here, the series I've got here is 0.3 times the sum of 0.2 to the n minus 1. So that is 0.3 times 0.2 to the power of 5, take away 1, over 0.2, take away 1, which equals to 0.37488. So that is the sum of the first 5 terms of that geometric progression. One more example. Let's do 0.1 minus 0.05 plus 0.025 and so on. This is the series we want to add up. Now I want to add up the first 5 terms of that geometric progression. Let's check that it is a geometric progression. So the terms are 0.1 minus 0.05, 0.025, so let's do the ratios. Minus 0.05, this is minus a half, and that is the same as 0.025 divided by minus 0.05, okay? So we want r to be minus 1/2, and so the sum we're calculating is 0.1 times the sum of powers of minus a half. And we're running this from 0 to 4, that's 5 terms. And now this is going to be 0.1 times the formula for the sum, which is minus 1/2 to the power of 5, that's 5 terms, take away 1, divide by minus 1/2, take away 1. And that is 0.06875. We looked at 2 formulae for finite series. We saw the sum of an arithmetic progression and the sum of a geometric progression. Let's look at 3 more formulae for series. The sum of I between 1 and n, that means just adding up 1 plus 2 plus 3 all the way to number n. The formula for this one comes from the sum of an arithmetic progression of common difference 1 and beginning in 1. And this is written as n times n plus 1 divided by 2. Check for yourself that this formula matches the formula we've learned for the arithmetic series. Now, more interestingly, the sum of squares, the sum of consecutive squares from 1 to n, that is doing 1 squared plus 2 squared plus 3 squared all the way to the square of n. That boils down to n times n plus 1 times 2n plus 1 divided by 6. And finally, the sum of cubes. The sum of I cubed between 1 and n. This means 1 cubed plus 2 cubed plus 3 cubed plus all the way to the cube of n. This one, surprisingly, or not, it is the square of the first formula we have there. It is a square of n times n plus 1 over 2. So it's n squared, n plus 1 squared over 4. Let's just look at a couple of examples of these formulae in action. The sum of I, when I goes from 1 to 10, that is, we're going to use the formula we've learned before when n equals 10. So that it's n times n plus 1 over 2. We replace n equals 10 in here. And so we've got 10 times 11 over 2, which is 5 times 11, which is 55. The sum of squares, let's do that. Let's do the sum of the first 7 squares. So I from 1 to 7. The formula for this one was n times n plus 1 times 2n plus 1 divided by 6. And so we need to make n equals 7 in this one. And so it's 7 times 8 times 15 divided by 6 equals 140. Let's do the sum of cubes. Let's do the first 5 cubes. So that is the square of the first formula. So n squared, n plus 1 squared over 4. We're going to make n equals 5 in there. So we got 5 squared, which is 25, times 6 squared, which is 36, divided by 4, 225. In this lesson, we looked at adding up terms of sequences. We call these sums series, and we use the summation symbol sigma to write them. We added sums and multiplied a sum by a constant. We also use formulae for the sums of consecutive numbers and the sums of consecutive squares. We even saw the special cases of sums of arithmetic and geometric progressions. We saw formulae for these. Next, we will look at the behavior of sequences and series as n grows unbounded. In other words, as n tends to infinity. To get ready for the next lesson, I invite you to observe what happens to arithmetic and geometric sequences and series as n tends to infinity. Do the terms stay bounded? Do the sums stay bounded? Do the terms grow unbounded? What about the sums? Bring your thoughts with you to the next lesson. Hello and welcome back. We worked with several sequences and series, and by now you're fully familiar with computing terms of sequences and their sums. We are now going to look at the behavior of sequences. That means that we want to analyze the long-term pattern as more and more terms are computed without having to compute all of them. We're going to look at a few examples of sequences. I wanted to join me in trying to predict what happens as n grows unbounded. So I'm going to list a few sequences here. You can get thinking of them. So 1 over n, 0.1 to the power of n, 10 to the power of n, minus 0.1 to the power of n, minus 10 to the power of n, and then n over n plus 1 and n plus 1 over n. So all these sequences here. And we're going to run Rn from 1 onwards. So we've got n is 1, 1/2, 1/3, 1/4, and so on. 0.1 to the power of n is 0.1. Then squared is 0.01. Cubed 0.001. To the power of 4, there's 4 decimal places, and so on. 10 to the power of n, start with 10 to the 1, 10 squared, 10 cubed, 10 to the power of 4, and so on. Now, minus 0.1 to the power of n sounds very similar to the other one, but remember, we've got the brackets. We're going to have to do the powers of the negative 0.1. So the first one is minus 0.1. The second is a square, so it's going to be positive 0.01. The third is going to be negative. So it looks very similar to the 0.1 to the n, but it alternates in sign. The odd powers being negative and the even powers being positive. Next, similar stuff. So negative 10, positive 100, negative 1,000, positive 10,000. And again, odd powers negative and even powers positive. Now for n over n plus 1, starting with n equals 1, we've got 1 on top, 2 below. So 1 over 2, and then 2 over 3, and so on. So it's a number over the next one. So 3 over 4, 4 over 5, and so on. And the very last sequence is the other way around. On when n is 1, we got 2 on top, 1 underneath, so just 2. Then we have 3 over 2, 4 over 3, 5 over 4, and so on. Now, I know that it's very tempting sometimes to write all these numbers as digital expansions rather than fractions. I would like you to do that as well, and I wanted to see how useful is one or the other. It's good to bear in mind that in some cases one expansion might be more useful than the fraction or the other way around. Now, what I want us to focus on is what happens to these sequences as I compute more and more terms. As n is growing, as n goes to infinity. Saying as n goes to infinity is a way of saying as n grows unbounded, larger and larger. So I want to capture that behavior to infinity. So what do you think happens? How do you explain what happens with the 1 over n? What will be the behavior expected after a quarter, a fifth, and sixth, and so on? You'll probably join me in saying that that number gets smaller and smaller and smaller in magnitude. I'm dividing 1 by 4, 1 by 5, 1 by 6, 1 by 1,000, a million. It's getting really, really small in magnitude. So I say that the limit, and I put this arrow here, it's 0. Meaning what I expect these values to converge to 0, to get smaller and smaller and closer to 0. It doesn't matter whether or not 0 is attained, it's not attained, but the values are going to be closer and closer. If I say, can I get to 0 with a certain error bound within, say, 0.001? Yes, there will be a number after which all the numbers in this sequence are going to be within 0.001 of the limit 0. But I can make that error bound smaller and smaller and smaller, and there will always be a certain order after which all the numbers in the sequence are within that error bound from the limit. That's what it means to converge to a limit, to 0. Now, what about the next one? So we got 0.1, 0.01, 0.001 is getting really small, and that is also converging to 0, has a limit of 0. Now, when we have 10 to the power of n, that is growing rapidly. Look, the number of zeros is increasing. So I got numbers larger and larger and larger. And that, there are many ways of saying that, but in this particular case, the numbers are growing unboundedly and they're getting larger and larger and positive. So it's pretty clear that it's just blowing up as a positive number. We can say that it has an infinite limit, but it's also correct to say that it's divergent. But I will tell you more about divergent sequences. So this one here, I'll say limit plus infinity, because it's getting larger and larger and larger, is growing unbounded. Now, what does that mean? It means that I say, let me see if I can contain these numbers within this size. You know, I've got a bound. Say, let's see if I can contain these numbers up to 1,000,000. Will this sequence ever grow beyond 1,000,000? Yes, it will, because 1,000,000 has 6 zeros. It's only a matter of time. 10 to the power of 7 has 7 zeros. So after 7 terms, the sequence is beyond my bound. So every time I attempt to put a boundary on the size of the terms, there's always a number that goes over the boundary. So that is infinite limit in this case. Yes, so for the next one, minus 0.1 to the power of n is very similar to the one we had before, but this one alternates between being positive and negative, but they're still in magnitude really small and approximate to the value of 0, sometimes above, sometimes below. This one still converges with limit 0. The next one, minus 10 to the power of n, the numbers keep blowing up, but in both directions. They get infinitely negative and infinitely positive. So this one, I would say no limit. So divergent. Now, down to our fractions. You may have written down the values of these terms as a decimal, as a digital expansion. That would have been 0.5 for a half, 0.6 recurring for 2/3, 0.75, 0.8, and so on. The pattern isn't so clear when I write it as a digital expansion, but with a fraction, it's a lot clearer to me. That what we get a fraction when the numerator and the denominator are close. And the larger they are, just a difference of 1 between top and bottom isn't going to make much of a difference in terms of the magnitude of the number. It seems to me that they're approximating to 1. Their numbers are getting larger and larger, approximating to 1. Now you may wonder, can we prove that? I'll show you in a second. So that will be a limit of 1. The bottom one, 2, 3/2, 4/3, 5/4, and so on. There's just a tiny bit, the numerator is a tiny bit larger than the denominator. So the numbers are larger than 1, but just a little bit larger than 1. And you can write the decimal expansion yourself. The limit of this one is 1 as well. And I've used a notation there. I've used the arrow. I'm just going to formalize that. The way I would write this without this long diagram would be 1 over n converges, that's the arrow, to 0 as n goes to plus infinity. That is one way of writing it. The other way of writing it is with lim, from limit. The limit, and underneath I say the variable is n, as increases to plus infinity. The limit of what? And I'll write the of what is here. The limit of 1 over n as n tends to plus infinity. That limit is 0, and is the equals. Okay, so that's another way of writing it. And so applying it to the other examples, we have that n over n plus 1 converges to 1 as n tends to plus infinity. We can say the limit as n tends to plus infinity of n over n plus 1 is 1. And similar to the other examples. Now, can I show you that this limit is really 1? Here's a little trick. N over n plus 1. Well, we can do fractions, and so here I can say, well, the denominator and the numerator are very close. So I'm going to write the numerator as n plus 1 and then take away 1. You'll agree that that totals up. It's still n, I just artificially added and subtracted a 1 to make it look a little bit more like the denominator. And now I'm going to split the fraction into this bit minus this bit. So it's going to be n plus 1 over n plus 1 minus 1 over n plus 1. And now, this is the cool bit, this is 1, because top and bottom are the same. So I've got 1 minus 1 over n plus 1. Now, this bit here, 1 over n plus 1, it's very much like that sequence there, 1 over n. So that one has a limit of 0. That means I have terms that look like 1 minus something that tends to 0. So the limit is going to be 1. So n over n plus 1 is the same as 1 minus 1 over n plus 1. And in the limit is going to be 1 from this one and take away 0 from this bit. So the limit is just 1. And you can do the same to prove that n plus 1 over n has a limit of 1 as well. Just how we write the other limits. So we had a limit of 10 to the n when n tends to plus infinity. We saw that that was infinite. It's a divergent sequence, but it's a special type. We can still say the limit here is plus infinity. Whereas minus 10 to the power of n, because it alternates between positive and negative, this one has no limit. So they're both divergent, but the first one has an infinite limit and the second one does not have a limit at all. We're going to look at a couple of examples. Say we've got an is 2 to the n, bn is 5 plus 2 over n squared, cn equals a half to the power of n, and dn equals 2 plus n. What are the limits of these sequences? So let's have a look at the other terms. The first one, we got 2, 4, 8, 16, and it keeps doubling. What do you think it happens? Well, it's going to grow unbounded. So the limit here is going to be plus infinity. This one here starts with, when n is 1, I've got 5 plus 2, that's 7. When n is 2, I've got, let's do the calculation, 5 plus 2 over 4, so 5 plus half, so 5 and a half. Then for n equals 3, I got 5 plus 2 over 3 squared, that's over 9, so 5 and 2 nines. What do you think is going to happen here as we increase the n? Let's try a couple more examples. So 5 plus 2 over 4 squared, 16, so 5, 2 over 16 is 1/8, 5 and 1/8. What's happening here? It seems very close to 5. It seems that I've got 5 and a little bit, and that little bit, it's smaller and smaller and smaller. So is it limit 5? Can we prove? Yes, we can prove. So let's have a look. What we can do, we can argue that it's 5 plus 2 over n squared. Now, this 2 over n squared is very much like 1 over n. 1 over n has limit 0. So if I square it, I'm going to square that limit, it's going to be 0 as well. And now if I double it, multiply by 2, I'm going to multiply the sequence and the limit by 2. Well, 0 times 2 is just 0. And this is the same as 2 over n squared. So what I'm saying is that that sequence there that I circled has limit 0. Therefore, the limit of 5 plus it has a limit of 5. Okay, so how would you write this down? It will say the reasoning I explained there in steps of starting with 1 over n has limit 0, then square it has limit 0 squared, which is 0, then double it has limit twice 0, which is still 0, and then add 5, the limit will be 5 plus 0, the limit is 5. Okay, so that's the argument you'd use for that. So yes, we proved that that limit is 5. This one here, we have a half, a quarter, 1/8, and so on. Smaller and smaller, the limit is 0. And this one here, I have 2 plus 1, which is 3, 2 plus 2, which is 4. I just add one more every time. It's an arithmetic progression with common difference 1 and first term 3. That is going to grow unbounded, slowly but unbounded. So from here, I just want us to recognize a few examples. So Bn, it's similar to the 1 over n sequence we saw earlier. So we can do operations with the limits to get to the limit of that one. The top one, an, and this one, cn, are geometric progressions. An has a common ratio of 2. Cn has a common ratio of half. And look what happens. With a common difference of 2, which is large, it's making the number grow, the geometric progression will have a limit of plus infinity or no limit. With Cn, where the common ratio is a half, it makes the number shrink. The limit will be 0. The fourth one, being an arithmetic progression, I'm adding a constant number every time. Even if I subtract the constant number every time, the sequence is either going to go to plus infinity or to minus infinity. So the only that is convergent to a finite limit is the geometric progression where the common ratio is small. And we're going to make precise what I mean by small. If it's a shrinking ratio, that means it has to be a number between -1 and 1. If it's negative, it will alternate sign, but it's still going to shrink the sequence value, the terms of the sequence in magnitude. So let's summarize that. For arithmetic progressions, they are all divergent, and the limit will be plus infinity or minus infinity, depending on whether you're adding a positive common difference, that you get a plus infinity limit. If you're adding a negative common difference, you get a minus infinity limit. For geometric progressions, if the common ratio, if it's greater than 1, I will have a limit that it's plus infinity or minus infinity, depending on what your starting value is. If you start with a positive number like 2 and you multiply by 3 every time, you're going to get a positive infinity limit. It's divergent, but with plus infinity limit. If you start with a negative number and keep multiplying, say -2, and keep multiplying by 3, you're going to make it more and more negative and really large. So negative infinity in the limit. When the ratio is less than -1, If you start with a positive value, say you start with 2 and then keep multiplying by -3, you're going to have sometimes negative, sometimes positive values, but it's still going to be large in magnitude. So it's going to be divergent, but the limit will not be plus infinity or minus infinity. There will be no limit, okay? So no limit. And if you started with a negative value and keep multiplying by a negative number, you'll still have the same situation. The sweet spot of convergence is between -1 and 1. If the ratio is between -1 and 1, you are shrinking the numbers in magnitude, sometimes alternating if the ratio is negative, but it will shrink down to a value. So we'll have convergent. Okay. Now it's up to you to go and practice these skills on the quiz, but I want you to think of how you can use these ideas for limits of series, meaning what happens when we add the infinite number of terms of a sequence. Can we ever have a finite limit? We'll find out next. Can the sum of an infinite number of numbers ever be finite? This is what this video is about. The answer is sometimes yes. It goes without saying that the numbers we are adding up cannot be very large. In fact, the starting point is the sequence we are adding up has to be convergent to 0 if we are even going to consider the infinite sum. But not all sequences with 0 limit will have a finite sum. Let's get this in writing. So I'm looking to adding a sequence an, and adding the sequence an, we've seen earlier, we will have a summation symbol. We're adding the sequence. I'm going to change the variable as for k, and I'll say I'm going to start from the first term. I'm going to add it all the way to n. So this is the sum of the first n terms, and the expanded form is a1 plus a2 plus all the way to an. I'm adding that sequence, that's the series, the first n terms. What I'm asking here about an infinite sum is, as n goes to infinity, what is the limit of this sum? So I'm actually asking you to consider this sum as the sequence itself. So for each value of n, I've got a sum up to value n, and as n tends to infinity, is there a limit? So in other words, I'm still adding up the same sequence. My label runs from 1 to n as n tends to infinity, so I'm going to write all the way to infinity there at the top. This is the sum of all the terms of that sequence. Okay, so this is the series we're interested in this video. Right, so I said that the starting point is don't even bother trying to add up sequences that are too large. Meaning, if the sequence I have here doesn't converge to 0, then there's no point looking at the series, because the series will have an infinite value or it will be divergent. Okay, so I'm going to write that down as saying a series, an infinite series like this, can only converge if the sequence itself is convergent to 0. Okay, so this means this is a necessary condition for the series to converge. It's a necessary condition it's not a sufficient condition. The sequence converging to 0 does not guarantee that the sum does. So I'm going to show you both situations. So to start with, I'm going to show you a series, an infinite series that converges. So I'm going to draw a picture. Just follow me in this. So I'm going to start with drawing a rectangle here. So there's a rectangle, and now I'm looking at the area of rectangle. So I'm considering that area, and then I'm going to add half the rectangle to it. So same width, but half the height. So I've got the first rectangle, then half of it, and now I'm going to half that again. And half that again, roughly, and so on and so on. And thinner and thinner. So the question is, this area added with this area, and that area, and so on, and so on, and so on. What is the total if we keep adding? Well, say we're adding an area of one rectangle plus half of that area plus a quarter of the initial area plus an eighth. It's halving every time. And we keep adding all the way to infinity. Is this a finite area? The answer is yes. Now, I can convince you of this by showing you the detail on the diagram. So what I'm going to do is I'm going to shift this rectangle here over there. Because that's a quarter of the total, it's half of the half, it fits there. So I'm going to remove that one. And now this one here is going to fit over there. So I can remove it. So this part is going to fit there, is actually half that space. So I'm going to put it in there. And I just carry on in this fashion. All these next halves are going to fit in the space. So in total, if I add all the way to infinity, what do I get? I'm going to fill in the rest of the space. Well, theoretically, if I could physically add up all these infinite quantities, I would get the whole space filled in. So, if this part is 1 as well, and that's another 1, this sum should be 2. So I'm adding an infinite number of numbers, and I'm getting as a result 2. Now, if this is a little bit hard to stomach, I'm with you. We can't actually physically add up an infinite number of numbers, but it's the concept of limit, like we used earlier in limits of sequences. So what we're getting is that as I add more and more terms of this sequence, so partial sum, so the finite series, and as I increase the number of terms in the limit, I approximate 2. I can get as close as I want to 2. So I'm going to write this down. We looked at the series 1 plus 1/2 plus 1/4 plus 1/8 and so on, all the way to infinity. That is written as the sum of the sequence 1 over 2 to the power of n when n runs from 0 all the way to infinity. Let's check. When n is 0, I have 1/2 to the power of 0, and that is 1. When n is 1, I have 1/2 to the 1, which is also 1/2, and so on, okay? So because I want all the terms, I am adding them up from 0 to infinity. So this is the sum I want. And what I'm saying is I consider partial sums, so finite series. I can do k from 0 to some value n. Actually, I'm going to put a large n there so there's no confusion. So for n, that could be 1, 2, 3, any number. And then let's see what that means. That means that when n is 1, I'm doing the sum from k equals 0 to 1 of 1/2 to the k, and that's the sum of 1 plus 1/2. When n is 2, I'm doing the sum from 0 to 2, and that's going to be 1 plus 1/2 plus 1/4. The sequence is the sequence of these partial sums. This series has a limit because the sum on k from 0 to n of 1/2 to the power of k has limit 2 when n tends to infinity. We have looked at that geometrically, and I gave you a nice argument for why that is 2. You may want an analytical or an algebraic method of proof that is a bit more reliable than my drawing. I'm with you. We are doing maths and computer science, so we need a bit more rigor. I'll go into that. So what's going on here? So I've showed you this example to give you an example of a series that has a finite sum. So in short, the sum of 1/2 to the power of k on k from 0 to infinity, that sum is 2. Now, I said that the sequence itself converging to 0 was not sufficient for the series to converge. I'm going to show an example of that. So if I have the sequence 1 over n, and I'm going to add the sequence, so I'm going to do the series when n goes from 1 to infinity. Now the sequence itself, so the 1 over n part, that converges to 0 as we saw earlier in another video. That converges to 0, so it satisfies the necessary condition, but this sum is not finite. So meaning that when we add 1 plus 1/2 plus 1/3 plus 1/4 and so on, this sum is going to blow up. Even though the terms you're adding are smaller and smaller, they're not small enough. They will still compound to a really large number, so this is going to be divergent. I am not going to prove it to you. There are plenty of proofs you can find in references. I do encourage you to go and find that out because it's quite intriguing. This is not slow enough, it's not small enough to add up to a finite number. Now this is called the harmonic series. If you want to look it up, that's the harmonic series. And the example we saw earlier, you've probably spotted that it was a geometric series. And it's a geometric series as we saw earlier. So in this module, we're going to look at convergent series. We're going to look at geometric series. And there's one type that converges. We saw earlier in the course that the finite sum of a geometric progression of common ratio r, that finite sum has a formula, and that formula is r to the n minus 1 over r minus 1, okay? And that we need that r isn't 1, okay? And that is a finite sum. Now, if we look at that, looking for the infinite series, we're looking at n going to infinity. Now, as n goes to infinity, we need to look at what happens there. We've got a geometric sequence there with r to the n. Yeah, I know, it's subtracting 1, dividing by r minus 1, but it's essentially, that is comparable to r to the n or r to the n minus 1. It's comparable to that. So this kind of sequence only converges when r is small, when r is between minus 1 and 1. And when r is between minus 1 and 1 is exactly when the geometric series with infinite items, with infinite terms, will converge. So r to n minus 1 over r minus 1 has a finite limit when n tends to infinity if and only if r is between minus 1 and 1. Okay? And that limit is, well, if r is between minus 1 and 1, r to the n converges to 0. So r to the n converges to 0, and it converges really fast, exponentially fast. And that means that guy goes to 0. That means this limit is minus 1 over r minus 1, which if we rearrange would be 1 over 1 minus r. Okay. Right, so what I just said is that the infinite sum is 1 over 1 minus r if and only if r is between minus 1 and 1. So that is the series with the finite infinite sum that we will use in this module. Okay, so let's look back at our example. We had 1 plus a half plus a quarter plus an eighth and so on. We had this one with the rectangles. Does it add up? Bad pun, I know. We have r is 1/2. It is between minus 1 and 1. Cool, let's carry on. The sum of a half to, okay, from 1 to infinity, that's going to be 1 over 1 minus r. R is a half, okay? And that means I got 1 over 1/2, which is 2. Okay, so that one is convergent, and that type of geometric series is convergent. We have a formula for the sum. Brilliant. I'm just going to recap that all the others we've seen aren't convergent. So things like sum of 2 to the k, when k goes from 1 to infinity, this is divergent. It has an infinite sum. Okay? And in fact, if you've got that sum of a geometric series when r is greater than 1, then the sum is also divergent. It's also true that if r is less than -1, that sum is also divergent. Now, when the common ratio is less than -1, one might think, well, some terms will be positive and other terms will be negative. So maybe the sum of the positives and the sum of the negatives kind of cancels out and we have something with a finite sum. It's a good idea, but let's see what happens. Say the example is I got ratio -2 and I'm adding powers of that. I would have -2 at 4, -8 at 16, -32 at 64, and so on. Okay, the next term being negative, the other one positive, and so on. Now, if we pair up numbers like this, the sum is 2 here, it's 8 there, and it's 32 there. So we're still adding up a sequence that doesn't converge to 0. So let's look at another example of using the sum of a geometric series. Let's do the infinite sum of 3 times 0.1 to the power of k. Infinite sum. How do we use our series formula for this. So I'm multiplying the geometric series here by a factor of 3. So I can take that 3 out and multiply by the whole sum. That's still possible with infinite series. Okay, so that's all I'm doing. And now I've got pure geometric series to add up, and the common ratio is 0.1. So I replace the series by the formula. So 1 over 1 minus the ratio. Okay, so I have 3 over 0.9. That's 27 over 0.1, so that's 270. Okay, so the sum of 3 times 0.1 to the k totals 270. Okay, so this is another example. Now, why would you care about this as a computer scientist? Surely you're not going around adding areas of crazy rectangles that go all the way to infinity. Yes, true, you are not going to do that. But as a computer scientist, you will compute loops. You will compute sums of consecutive terms on a loop. So you'll have something like 4k from 1 to 1,000. Add this term to this existing sum. You've got to be careful about sums that will overflow, sums that will become really large, so large that you run out of memory to do the computation, or you will lack precision. So you need to be aware of how far you can add up such things. Also, any numerical analysis of sequences and series that may come across in terms of performance or complexity, this is part of your numeracy and your literacy in mathematics. I leave you as an exercise to apply the sum of the geometric series to the place values in binary or the place values in any base. One connection with the real world, and I do love paper, I use the A format paper a lot. A4 is my favorite printing format, and the format A for paper has a very specific property. When you half a page, the smaller page has the same proportions as the bigger sheet of paper. So as you fold, you keep the same format, but the sizes shrink down. And is a particularly nice paper format to explore geometric sequences, and if you want to add up the area of the sizes of paper, you'll be looking at the geometric series too. So go ahead and practice. Wow, you have a great deal of information now about limits of sequences. You saw the convergent sequences, 1 over n, geometric progressions with ratio between -1 and 1. We intuitively used the following idea. If two sequences are convergent, then adding them up gives a new sequence that is convergent to, and the limit is the sum of the limits of the two sequences. I can write that as the limit of a sum of sequences is the sum of one limit with the other limit. Of course, if an and bn are both convergent. Meaning that an plus bn is also convergent. I mean, we're not only saying that the sum is convergent, we actually tell you exactly what the limit is. Now, here's another case. We also used intuitively the fact that multiplying a convergent series by a constant still results in a convergent sequence. And we can write that in this way. If an is our convergent sequence and c is a constant, then I'm saying that multiplying the sequence by a constant, we take the limit of the sequence itself, and whatever that is, we multiply by that constant. So that means, because we know that 1 over n is convergent, 3 over n is convergent, is 1 over n multiplied by 3, and 1 over 4n is also convergent because the constant there is a quarter, and so on. But what about all the other sequences? You know, the ones that we can't just use these two rules. Convergence is all about being bounded and narrowing down the variation of terms as n increases. That's my mental picture of convergence. Say we're looking at 1 over n squared. That is a bit similar to 1 over n, and 1 over n is convergent. Now you're probably thinking 1 over n squared is smaller than 1 over n. So surely that should guarantee that 1 over n squared is convergent. And you're right. If we're talking about magnitudes of the numbers, if we're comparing the magnitude of the numbers in the sequence, and the sequence you're working with is sandwiched between two sequences that converge, then the one in the middle is also convergent. So what I write there is, if we have a sequence Bn that is convergent, and Cn that is convergent, and I'm wondering about the convergence of An, wondering about that, but I realize that actually An is sandwiched between the other two, because the other two have limits, these have limits, then that one in the middle is going to have a limit too, and the limit is going to be in between. So that means that if this happens for all n, in fact for all n after a certain number, but let's say for all n, then the limit of An exists and the limit of An is in between the limits of the others. And now just notice that I used strict inequalities for the sequences. I used Bn less than An, less than Cn, but when I came to the limit, I wrote less or equal to, because in the limit, you can actually have those numbers being equal. In the same way that 1 over n is never 0, but the limit is 0. So if this exists, so what we take home is that if Bn is convergent and Cn is convergent, and An is a sequence in between those two, then An is also convergent and the limit is in between the limits of the other two. Now, this does not give the limit. This is a rule that doesn't give you the value of the limit, but it guarantees it exists and gives you bounds for the limit of An. This is of use as you analyze sequences and functions in practical life. You want to have a sense of convergence and have bounds for limits, but you don't necessarily need the precise value of the limit. So back to my example of 1 over n squared, that is between 0 and 1 over n. So 1 over n squared is between 0 and 1 over n. In fact, if you make that n is greater or equal to 2, because we only need it to happen after a certain number, and if your sequences in the beginning are very different and the pattern only happens after a while, just take that number for your analysis. Okay, so in this case, for n greater or equal to 2, this works. Therefore, the limit of 1 over n squared is going to be in between the limit of 1 over n and the limit of 0. Now, this is quite a nice one because the limit of 1 over n is 0 and the limit of 0 is 0, so therefore the limit of 1 over n squared has to be 0 as well. So that part is 0, that part is 0, and therefore the limit of 1 over n squared is 0 as well. Again, we cannot guarantee strict inequalities in the limit, since a limit can be smaller than all the terms of a sequence, or larger than all the terms of a sequence. Now, for series, we can use comparison too. But let's recap what we said about the sequences we're adding up in a series. If we're looking at a series that is a summation of an, we said that if an is not convergent, or the limit is not 0, then the series cannot converge. This gives a necessary condition for convergence, but is not a sufficient condition. So what I said was that when we're looking at the series an, and this is implied that the limit is from a number 1 to infinity. In fact, I can put here any finite number. The necessary condition for convergence is that an converges and the limit exists, and it is 0. So this limit existing is a necessary condition for the sum to converge, but is not sufficient. Now, that means it will be handy to have some sufficient conditions. It will be handy to have some tests that could guarantee convergence. Now, there's some good news. If the sequence is almost a geometric progression with ratio r, that is between -1 and 1, then the series converges. Unfortunately, I don't have a formula for you, because we saw a formula for the sum of the geometric progression with ratio r between -1 and 1. We saw that formula, but if the sequence is almost like that, we still guarantee convergence. Okay, so the series I'm wondering about is the sum of an. If we take the magnitude of an plus 1 divided by an, and the absolute value of this ratio in the limit gives a value r, then if r is between 0 and 1, then the sum converges. So basically we're saying if this looks very much like a geometric progression, then the sum converges if the ratio is a contracting ratio. So that means I write an plus 1 over an, and it's the magnitude of this number that I want. So I want the absolute value, which is usually denoted with 2 bars around it. That means the positive value of it. So if it's -5, you write 5. If it's minus 0.2, you write 0.2. If it's 2, it's still 2. So the absolute value, if this in the limit is an r, and that value is going to have to be 0 or more. If that limit is r, and r is between 0 and 1, but not 1, then the series converges. We don't know the value, but we know it converges. Now, if r is greater than 1, it will diverge. So we have a clear answer. So if we're just growing immensely, the series is going to diverge. Now, if r is exactly 1, this test will be inconclusive and we'll have to do other investigations. So if r is greater than 1, the series diverges. And if r is 1, it's inconclusive. Now, we can compare terms of the sequence directly with another sequence to assess how the series behaves. Let's work with positive sequences only for now. If we have two series, the sum of A and the sum of B, that converge, and we want to decide on a sum of Cn, where Cn is in between the two sequences after a certain order, then the sum of Cn converges and it's in between the values of the other sums. I'll write that down. So we know that this converges and this one converges too. And let's put the values here. And if we have that the terms of the sequence Cn are sandwiched between the terms of the other sequences, then the sum of the series is also going to be convergent. Then the sum of Cn converges. And we have bounds for that value. And again, I use less or equal to in the limit, even if I have a strict inequality between the sequence terms. There are more criteria that have been studied and proved, and you will be able to use them in your professional life. I encourage you to go and learn about those, but be aware that any other criteria not stated here is outside the scope of this module. In this lesson, we looked at the behavior of infinite sequences and infinite series. We introduced the concept of limit, calculated limits of sequences and series. In particular, we saw formulae for limits of geometric sequences and series for when the ratio is a shrinking ratio, meaning that it's between -1 and 1. We formalized our intuition and gave criteria to decide if a sequence or a series are convergent by inspecting the general term or comparing it to others. In this topic, you've been on a journey through ordered lists of numbers and their sums. These are called sequences and series, respectively. Our emphasis is on you using critical thinking when dealing with sequences and series in your professional life. So we got you to make sense of patterns and then see the need to formalize such patterns in a precise definition, such as the general term of the sequence, basically an expression or formula, or a recurrence relation. The main difference between these two ways of defining a sequence is that the recurrence relation requires you to calculate all terms before the term you are interested in, whereas the general term allows you to just replace the index variable by the value you want to get the term you need. We looked at two special families of sequences, arithmetic progressions and geometric progressions. The first consists of sequences where any two consecutive terms differ of the same value. The second, the ratio between two consecutive values is the same. We also looked at limits and said when a sequence converges. We saw that arithmetic progressions do not converge, but geometric can. If it's a scaling down progression, meaning that the common ratio is between -1 and 1. We then looked at adding up consecutive terms of a sequence. These terms are called series. We have formulae for such sums for arithmetic and geometric progressions for a finite number of terms. Now, taking series to the limit, these sums do not often converge. We saw criteria for convergence, and in the case of geometric progressions of ratio r between -1 and 1, we have an explicit formula for the sum of all terms. To understand where this all fits with computing, have a go at adding up numbers in a loop. And looking at numbers of comparisons an algorithm requires to perform, and the performance of different algorithms that solve the same problem. Or design computer graphics where you need to access resolution limits of how much of your design shows up when we zoom in and out of the image. This is outside of the scope of the module, but part of the professional development of a computer scientist. I love maths. Look, I love maths. How is this done? The sound waves were plotted as a graph. We have sound as a function of time. In this topic, we will look at tools required to represent information as images, from designing a computer game to creating digital art or simply understanding how images fit on screens. We use the basic knowledge of coordinates to represent functions as a graph. The picture that encodes the variation and behavior of that function. We will illustrate one application in modeling motion in the kinematic equations for simple straight line motion with constant acceleration, also known as SUVAT equations. Handy if you want to design a simple video game throwing balls in the air or simple race cars colliding. Here are some examples. We have volumes of containers plotted against height as you fill them up. Which graph corresponds to which container? You can answer in the in-video quiz. Now then, how hard was it for you to match them up? It probably varies on how familiar you are with analyzing these things. But some containers are harder to figure out and need closer study. Experiments run, data collected, and graphs plotted rigorously. Of course, computers and some calculators can plot graphs for you. In this module, we are focusing on the thinking skills of deciding how to plot a graph, how to represent it, how to interpret it. We will use a digital graph plotting tool to gain intuition on how functions work and to get to know types of graphs without having to plot everything by hand. But you will be asked to submit hand-drawn graphs, so get your graph paper and geometry set ready. Where are you? The answer being 2 numbers, your coordinates. Whatever system you want to use, latitude, longitude, 2 numbers that describe your position on the planet. Well, 3 if you want to tell me how far up you are. We're going to look at functions and graphs, and for that we need to be able to represent points in the plane. We're going to use Cartesian coordinates. And that just means we're going to have 2 numbers to give me the precise location of a point in a plane, say an infinite piece of paper. To make those instructions precise, we need a reference. We need a reference point, it's going to be our origin, and we need two axes, there are two lines that are going to be our frame of work. That means we're going to have a horizontal axis, and notice that I'm label it X as our tradition and our convention, and a vertical axis that we're labeling Y. And notice that it is important to put the arrow at the end of that line in both of the axes and the letter that it refers to. We're using handwritten lowercase letters X and Y. The other important thing is these axes have to be orthogonal, meaning perpendicular, meaning that the angle is 90 degrees. And the point where they cross is called the origin, and it's where everything starts. Now, our convention is going to be, we are assigning two numbers that tells you in which direction you're walking to get to that point. You start at the origin, and if you go 2 and then 3, we are using 2 in the X direction, and we're using 1, 2, and 3 in the Y direction, and our point is there. The way I write that point, you can label it, say that is point A, and A has coordinates 2, 3. I did use a dot on that point, but it's important that when you locate a point, you use the cross, and then you can embellish it with a point if you want. Now, let's see what happens with other points. Let's make 3 more points here. And we'll do, say point B has coordinates -1, 2. That means I will use -1 steps in the X direction from the origin. So from the origin I go -1 there. And then I do 2 in the Y direction. That means 2 upwards from where I was. So 2 upwards from here, 1 and 2. So here's my point B. There we are. So I've got C with coordinates -2, -1. I start at the origin, I go 2 steps on the negative direction of X, so -2, and down -1 on the Y, so 1 down. 1 down from here, so I've got point C. And for point D, you're probably guessing I'm going to use a positive X and a negative Y, yes. I'll have 1 and -2. That means 1 in the X direction here, and then 2 down. That's -2. And so it's my point D. Okay, so I've got 4 points there, 1 in each quadrant, and the quadrants are the 4 parts of the plane that were split by the axis. So we have the A is in the first quadrant, the point B is on the second quadrant, point C is on the third quadrant, and point D is on the fourth quadrant. Coordinates of points can be added and subtracted, and you can scale up a picture by multiplying the coordinates of a point by a number. So on a new graph, my X, my Y, I have points P with coordinates 1, 2, and Q with coordinates -2, 3. I'm going to use a different scale this time. I'm going to represent 1 and then 2. So my point P is there. Then Q is on -1, -2, and then 3, 1, 2, 3 there. That's where Q is. Let's use a little color. So I've got P and Q. Okay. We can write what P plus Q makes sense to do. What we do is just add the coordinates. 1 plus -2 is -1, 2 plus 3 is 5, and geometrically speaking, P plus Q has also a meaning. Let's just plot the coordinates. -1, it's there, and then 5, 4, 5, there we are, here's the point. That is P plus Q. Let's put that a little green. That's P plus Q. And if you've done vectors, you may have seen this before. If not, I'll just look at that. If I look at the arrow that goes from the origin to P and the arrow that goes from the origin to Q, that adding of P plus Q is the vertex of the parallelogram made by those two lines. What I mean is I take the arrow for P and I put it there, and I take the arrow for Q and put it here, and that P plus Q is the other corner of that parallelogram. Just the sides are all parallel here. You can subtract as well the coordinates one by one. So for example, if we do Q minus P, that would be the coordinates of Q take away the coordinates of P. So that would be -2 take away 1, which is -3. And then 3 take away 2, which is 1. And so the subtraction of that will be -3 and 1, which is here. Q minus P. And I will leave you to work out what that might mean geometrically. Just telling you that we can do those sums. So the arrow is there. Now, just to clarify, we are not talking about the arrows just now. In Cartesian coordinates, in points, we are looking at the dot where the point is. I'm talking about the arrows, so you can build on any knowledge you might have had from before. As to scaling up, let's just see what 2p might mean. 2p would be doubling every coordinate in P. So P is 1, 2, so we double the 1, which is 2, we double the 2, which is 4, and so 2p will be 2 and 4 there. So 2p is there. And in terms of arrows, will be the double arrow. An arrow that goes from the origin, goes through P, and goes over there. Okay. Right, so we can add, we can subtract coordinates, we can also multiply coordinates by one number. We do not multiply coordinates of 2 points. We are not going to do that. We're using coordinates to describe parts of the plane, but we are also going to need language to describe, language and notation, language and symbols, to describe points within a line. So we're going to look at interval notation and simply say I want the point values of x between 1 and 5. That was a long sentence to write. We can summarize that in mathematical notation in the following way. X is greater than 1 and is less than 5. But some of you may be thinking, could we have 1 less or equal to x? Or could have x less or equal to 5 instead of just strictly less? My written language wasn't clear enough, was ambiguous. So in mathematics, we're going to make it absolutely clear whether we want to include the 1 and the 5 or not. So I want to script that 1 less than x less than 5 means in a line, I have the x line there, I've got the origin there with a 0, got a 1 and 2, 3, 4, 5. I mean all these points here, but not the 1, not the 5. So I'm excluding that. And when we're drawing points and graphs, if we want to exclude a point, we draw a circle that is left empty inside. If we want to include the point, we fill in that little circle. So if we wanted to include the 5, we would write it with that symbol. And in terms of representing it on the line, we would make the ball open in 1, the ball closed and filled in 5. And we are thickening that line in between. So that will be our representation. Now, this notation is still long, so there is a shorter way of writing it. That is the interval notation. I'm going to make some space here for it. I'll write the first condition as 1, 5, and that is in an interval. And here 1, 5 with a rectangular bracket. That means closed, that means include the 5. And if I want to include both, I would write 1, 5, and the condition that goes with it is 1 less or equal to x less or equal to 5. We can also have closed on 1, that's the one that is missing, and open on 5, so that will be that condition. Okay. There are times when we want to include infinity, but just saying, you know, I want all the points after 2. All the points after 2, excluding 2, will be x is greater than 2. That on the line means here's 2. At the end that I haven't plotted is the known infinity. And I want all of those guys, and I don't want 2, so open ball. Or I could have x greater or equal to 2, and therefore I would include the ball. And the interval notation would be 2 to plus infinity, and it's always open on the infinity, and this one will be closed on 2 to infinity. And what's missing now is just doing the minus infinity intervals, so x less than 3 will be minus infinity to 3, open. X less or equal to 3 will be minus infinity to 3, closed. And that means the points on the number line, those ones closed with minus infinity, and those open with minus infinity there. How do we use this? We want a condition in a plane that we're going to use coordinates to describe, and we might need to use these conditions or these intervals. So say I have got 2 there, so this is x, that's y, that's the origin, and I want all these points. How do we describe them? Well, looking at them, I can see that it is everything that is to the right of 2. Everything to the right of 2, including 2. That means that the points will have coordinates x and y. There will be coordinates. And the x itself is going to be greater or equal to 2. That's it. Y can be anything. Those curly brackets around it just mean it's a set. It's a set of all the points that have coordinates x and y, and x is greater or equal to 2. Another example could be that I wanted this is 1 and that is 3. I want that region there. So this is x, this is y, and I'll say I want the points with coordinates x and y, and x has to be less or equal to 1, and at the same time y has to be less or equal to 3. Okay, just an idea. Now, you might not write this formally like this when you're in computing, but you will need to be able to make sense of regions, and these are some of the ideas you need to do that. The idea for graphs of functions will be that as x changes, we will have a value of y that may or may not change, but it will be written as a function, will be dependent on the x. So the x, the horizontal, is the independent value, the independent factor, the independent variable, and the y, the vertical, will be the dependable one, the one that is written as a function of the other. So a line like that is a line of a function. That's because each point on the graph has, of course, it has coordinates x and y, but you will never find one x value with two y's. Never. If you draw a vertical line, it will only cross the graph in one point. Only in one point. And that's the y value corresponding to the x. The opposite isn't true. You may have one y value that is the result of different x's. So in this case of this graph I've sketched here, I will say that each value of y is a function of x, and usually written as f brackets x. In this lesson, we use coordinates to represent the behavior of functions graphically. A picture is worth 1,000 words, someone said. Once again, why do it by hand when machines can do it for you? You will need to make choices to request a machine to highlight the features of the function that are of interest for a specific purpose. Within the module, we will focus on you demonstrating that you know what to expect from a given function in terms of growth of a function, if it has repeating pattern, symmetry, if there are gaps in the graph, points of interest, and choose how to plot the graph to show such features. Traditionally, the horizontal axis marks values of the variable, usually x, that is independent, and the vertical axis the value y of the function for each value of x. For example, this graph shows a function of x, meaning that the y values are dependent on the value of x. There is only one y value for each x value, and that means that if we draw any vertical line, the line only cuts the graph once at most. Now, to show you this graph, I've already started making choices on how to highlight the interesting behavior. Now, I'm going to make some more choices here to see what is happening near x equals 0. That's better already. Near 0, we now can see that actually in the window between -1 and 4, there's quite a lot of interesting behavior. There's a lot of variation in the graph. We now can tell that the values of y increase for x up to about -0.4, where y reaches about 30. See over there. Round about -0.4, y is 30. Now, between x equals -0.4 to 1.4, the values of y decrease, and they decrease to a minimum of about -2.5. So they come from 30 to around -2.5. Then between x equals 1.4 and about 2.5, y increases again to a maximum of about 2. Just need to make sure that we're reading the scale right. Yeah, about 2. And again, y decreases when x goes from 2.5 to about 3.65, give or take. From that point, from x equals 3.65 onwards, y increases rapidly. And we can see that, zooming out again. We can also see that the graph cuts the x-axis several times. Let's look at the point x equals -1. Is it precisely -1? Good question. At 1, at 2, at 3, and at 4. We can check whether or not that is precise. We can check algebraically. We can do calculations. We're going to find those precise values where the line crosses the axis. Those are called the zeros. But can we always find that out? Sometimes we can, sometimes we can't. We will look into these questions so we know how much is possible to do with precision. We will get some of the tools needed in this topic. We will learn more tools with limits and calculus later on in this module. You're going to plot and sketch graphs by hand, and you wonder, but I'm a computer scientist, why do I have to do this by hand? We want you to understand functions so that you are able to implement functions in your programming appropriately. So in this module, I want to prepare you to do all the work to do a really good graph that captures the essence of the behavior of the function. And that's what we're looking for. We're not looking for you to replace a plotting machine. We wanted to give the impression of that behavior, the impression of change, and all the points that are noteworthy in that function. So the first thing we need is to have a table of values. I mean, you need a table of values before you start drawing. And the table of values is not something you just do blindly. We're going to think about what points, what values are good to represent in this table. Say we've got the function y equals x squared minus 2. We're going to prepare a table of values for this. If you know nothing about the function, you just start with a few values to help you. So we do values of x are going to run over there, and the corresponding value of y. Now, I write y there, but I really want you to think that instead of just y, what you need to calculate in that line is x squared minus 2 for each value of x that appears on the top row. So really what we have here is x squared minus 2. Let's put it in a few values. Let's try what happens if we put value of 0. 0 squared is 0, take away 2 is minus 2. Let's do 1. 1 squared is 1. 1 minus 2 is minus 1. So minus 1. Let's try the value of 2. 2 squared is 4. 4 take away 2 is 2. Are 3 points enough? Well, if you know nothing about the function, then I suggest you start drawing the graph from the points you have. If you know something about the function, you will know that this is not a good choice of values. But let's do it. So our x-axis, not y-axis. We're going to have our origin there. We need to choose a scale for now. Let's see, 1 there and 2. And for the y direction, we don't have to use the same scale for y as we use for x, but we just have to have a scale on each and have consistent representation. Now, for now, 0 will have a value of y minus 2, so 1, 2, so minus 1, minus 2. So I've got that point there. In 1, I've got negative 1, so I'm there. And on 2, I'm on 2. Wow. 1 and 2. What happened there, you wonder? Right, so I've got 3 points, which I'm going to mark with a different color. I've got that point, and that point. Okay, tempted to just draw the line there. Now, if you know nothing about it, you could be tempted to do this. That is terrible. What I wanted to do is you go through a few of these functions on a plotting software like who I've shown you in the previous video. So you build an intuition of what the graph should look like. That is awful. This graph is not going to be straight lines. This is a quadratic function. And if this is new to you, just go and plot a few until you get a sense for what they look like. It has to look like a parabola. And a parabola looks like this or like this. It's smooth, it's round, and it's got a vertex, it's got a minimal point there, or it's got a top point, a maximum point. That's the vertex. And although my sketch in green isn't that great, the idea I wanted to give there is that they are symmetrical. The two sides, the two arcs on each side of the vertex look pretty much the same as a mirror image of each other. So the drawing I have there, it's really not good when you take that into account. To start with, we need a little bit more points. And now that we see what it looks like, we know we should expect something on this side. So let's give our table of values a few more points. So -1. -1 squared is 1, take away 2 is still -1. And -2 for the x, minus 2 squared is 4, take away 2 is still 2. So marking these points on the graph, so on -1 I got -1, and on -2 I've got 2. And so to sketch this, I got a line that goes through all the points, and I can adjust to give the impression of symmetry. Okay, and that is a sketch. It is a plot of the graphs. What's the difference between plot and sketch? I've actually calculated points, and the line goes through those points, so that's a plot. A sketch would just give an impression of it, like I did the earlier drawing of the two parabolae in green. Let's look at another one. Y equals 2x cubed minus x. Let's have a table of values. Let's try x to be -2, -1, 0, 1, and 2. The y value will be calculated using the formula. So let's do 2 times -2 cubed, take away -2. That is, -2 cubed is -8, times 2 is -16. -2 is +2, so I've got -14, -14 there. -1, 2 minus 1 cubed minus -1, I've got -2 plus 1, that's -1. For 0, I got 0 cubed, which is 0, twice that is 0, minus 0, that's just 0, and the value of 1 cubed is 1 times 2 is 2, 2 minus 1 is going to be 1, and for 2 I have 2 cubed, which is 8, double that is 16, 16 take away 2, that's going to be 14. Okay, and this graph, it's going to look different from a quadratic. This is a cubic, and we can plot it here roughly. It is, I need to pay attention to this scale, because look, I've got values from -14 to 14 on the y. So I'm going to do, that's going to be my -14, that's going to be my 14, the same distance, and I've got points 1 and 2 on the x, and -1 and -2 on the x. On -2 I got -14, on -1 I got -1. Divide that vertical space into 14 parts, roughly, is going to be a tiny amount. That's a very mathematical way of saying it, isn't it? I know. And then that's going to be another tiny amount, and it's going to be a 0 there, tiny amount, and huge amount there. And our cubic like that. Okay, so that is the curve y equals 2x cubed minus x. A couple more examples. So y equals -2 over x. We'll do a similar job as we did before. We're going to have a table of values, and we could start by using, say, you have -2, -1. Are you tempted to put a 0 there? Why is that a problem? We cannot do 2 over 0, so we cannot. I'm going to put the 0 there, but I'm going to say it's not possible. It's not defined, okay? It's not defined. And then 1 and 2. And the values for that, the y, -2 over -2, that is 1. -2 over -1, that is 2. And here, -2, and here, -1. And undefined. Now, that doesn't give me enough information to do a decent plot. I'll show you why. We've got -2, -1. I've got the value of 1 there, and the value of 2 there. So 1, 2, and then that's minus, so that is 1 and 2. And I've got this value, We've got only those 2 points. What's going on? What happens near 0? Near 0, because it's undefined, we need to have more values between the -1 and the 0 and between the 0 and the 1. So we actually need to have a decent approach there. Between -1 and 0, let's say we do -3/4, a half, and -1/4. -3/4, -1/2, -1/4. If we do -2 over that, let's do the sums here on the side. -2 over -3/4 is positive 4/6, which is just 2/3. So that's 2/3. -2 over -1/2 is going to be 4. And -2 over -1/4 is going to be 8. So the smaller I make that number in magnitude, the bigger the result of y. I'm going to have these numbers here just going off my graph. This is the problem. If we don't prepare our work, we're going to go off the page. This is happening. So we'll have a function, we'll have a graph that looks pretty much like that. And it's going to try to approach the vertical axis. So the table of values, it's really important because it helps you plan what the graph should look like. So you can now fill in the gaps and put more values between -1 and 1, and you'll see the behavior. I'll just sketch it on the other page. What you should expect is to have a curve like this that looks like, this curve is called a hyperbola. You don't have to know this, but this is a hyperbola. And the x-axis goes over there, and the y-axis goes over there. And this bit here isn't looking very good because you shouldn't really ever cross the x-axis. Shouldn't even touch. So the graph should look like that with nothing happening on the vertical line through the origin. Okay? Now that brings us to another concept that we need to cover, which is the domain of a function. This function, y equals -2 over x, this function cannot be calculated when x is 0. So x equals 0 cannot be part of the values we use. The domain of the function are all the values of x that we can actually use, and x isn't one of them. So I'll say the domain is going to be everything except for number 0. So that's going to be -∞ to 0, union with 0 to infinity. Or you can call it R, as in all the real numbers, except for the point 0. Okay, so that's the domain of this function. How do we calculate it? Well, we look at the expression and we think, what values can I not put in x? And you take those out of your domain. Say we've got y equals square root of x, which I will introduce it to the function notation as well. I can write it instead of that saying f of x equals root of x, and I say that y is a function of x. Say y equals that function of x. So this, over here I'm telling you what the expression is. Here's another way of doing the expression, and here I'm just saying y is going to be calculated as a function of x. Now, so with y equals root of x, where are the values of x that cause a problem? Well, what values of x can you calculate the square root of? Any value that is positive and 0. So negative values of x cannot be in the domain. So the domain is going to be just the positive numbers and 0. You can write it that way, or you can write it as the real numbers, the positives, and 0. So positive and 0, real numbers. That's the domain. And this function, that means your table of values would incorporate positive values and 0, and I'll give you a sketch. that way. And the value for 1 is 1. Okay, and nothing on the left-hand side because there's no negative numbers in the domain. I want to go back to the function we saw earlier, this one here. That line that I said that the vertical line through the origin where there's no graph, that is called an asymptote. Not because there's no graph, but because the curves of the graph really want to touch that line. So this line here is the vertical asymptote for this graph, because the two branches want to approximate it, one on the left and one on the right. This graph has even another asymptote. It has a horizontal asymptote where the axis is, because again, as you make values of x larger and larger, or larger and larger but negative, the values of y are going to approximate to 0. And so they're trying to lie down on the axis, but they're just not getting there ever. So that's an asymptote. We're going to look at a series of examples of plotting graphs by hand. Let's bear in mind a few key principles. We need to have correct labeling of the axis. We need to have correct labeling of any points we want to highlight. The scale needs to be consistent. You can have a different scale for the x-axis and for the y-axis, that is fine, but the scale you use in one axis needs to be consistent across the whole drawing. If the function has symmetry, you are to highlight that symmetry. Even if your values aren't absolutely accurate, it's important that you highlight, that you understand that the function has that symmetric behavior, or that it has an increasing or decreasing or a flat behavior. Any other key features you can be aware of a function are to be highlighted in all these plots and sketches you do by hand. I would like you to plot graphs by hand once you've looked at a few examples of them plotted in a plotting software. Further to that, do build tables of values to make accurate plots of graphs by hand, and then you'll build intuition and experience to choose values for your table in a much more efficient way and sketch graphs with very little information. Bear in mind that not all functions have one expression. Some functions have expressions that are broken into branches. Those are piecewise functions. We'll look into those as well. But in the end, all these pieces are going to be built from types of graphs that you're going to study individually. In computing, you may have other special functions like absolute value and step functions like ceiling or floor functions. I invite you to explore those as well. The skills you need for those are the same skills we're going to study with all the other functions we'll look at now. To plot straight lines, we can start with the expression. We can look at what the slope might be and the intercept. Say we have y equals minus a half of x plus 3. We will write a table of values, but before we go into table of values, from the numbers in front of us, we have the slope, this minus a half, and we have the y-intercept, which is 3. That means we know a little bit more about our function. We know that the graph cuts the y-axis in that point, and we also know that the slope is negative 1/2. I move 1 in the x direction, I move minus a half down in the y direction. Easier if we think of If I move 2 in the x direction, I move 1 down in the y. So from that point of coordinates 0, 3, the intercept, if I move 3 down, I move 6 across. So I should expect that point to be a point in the straight line. Let's check if that is true. Table of values. When x is 0, we've got 3, which is the y-intercept. For x equals 6, I got minus a half of 6 plus 3. Minus half of 6 is minus 3. Minus 3 plus 3, it is 0. Okay? So our geometric thinking paid off. And the straight line will be just a straight line that joins those points. We have y equals minus a half x plus 3. So here's an example where you can use the geometrical information to speed up your plotting and choosing your values for the table. Now we had a special number, a special value there. We had on that graph a point where the straight line crossed the x-axis. That is called a 0. A 0 is a value of x that gives 0y. That's why we call it a 0. So it's a point where we cross the x-axis. Now, what if the geometric information didn't allow us to calculate that point? It's not a problem. We have algebra. So in this example, to calculate that x equals 6, I could have just said, I want to know when y is 0. When y is 0 in that expression. That means that I want minus 1/2 of x plus 3 to be 0. That means I'm just going to run a bit of algebra in here to solve the equation for x. So I add 3 to both sides. I get minus 1/2 of x equals minus 3. I now multiply both sides by minus 2. And I get x on this side and 6 on the other. Done. That was the value of the 0, the value of that point there in the graph. So, in summary, you can use geometrical information to help you draw the graph and speed up the choice of values for the table and what the graph is going to look like. But you can also use algebraic tools like solving an equation, and to find the zeros, or in this case the 1, 0, you solve the expression of the function equal to 0 and solve it for x. Now we have the y-intercept, we have the 3 on the y-axis. Could we have solved that one algebraically? Of course. In that case, we're not looking at y equals 0, we are looking at x being 0. So that point there has coordinates 0, 3. The x is 0. So we want to know in that expression, when is x equals 0? Well, we substitute x equals 0 into the expression, so minus 1/2 times 0 plus 3, and it gives us the value 3, as we knew already there on that table of values. So both those points are obtainable by algebraic methods. We're going to plot quadratics. Here's one. We have f of x equals x squared plus 3x. That just means that y is going to be x squared plus 3x. Okay, we're going to plot the graph of y as a function of x given by that expression. Now, it is a quadratic because the highest power of x is x squared. So that's power 2, that's a quadratic. Inspecting the function, things we can look for straight away. What's the y-intercept? What is the individual number? This function has a plus 0 there. The independent term is 0. So that means the intercept is 0. That means it crosses the y-axis at value y equals 0. That means you're not on the graph, which I'm going to draw here. I'm going to draw my axis. That's my x and my y. That means that it's going to go through the origin. When x is 0, y is going to be 0. So that's the intercept that we got from the fact that there is no independent term here, so there is a plus 0. Okay, so we got that. Now, what else can we take from there? Well, we need to understand what the shape is, and we know from experience that it's going to be a graph like that or like that. Now, the happy parabola or the sad parabola is all to do with the sign of the coefficient of x squared. That means the sign of the number multiplying by x squared. In this case, we got x squared is the leading term, and x squared has a 1, an invisible 1 multiplying there. That's a positive number. So this is the type of parabola we expect to have. That parabola has a vertex, the lowest point. So we'll be looking to finding that point. And this graph may or may not cross the x-axis, may or may not have zeros. Let's start with the zeros. Looking at that expression, to find the zeros, we'll be looking at solving y equals 0. That means we need to do x squared plus 3x, which is the expression for y, equals 0. Can we solve this? Yes, we can. There's many ways you can do that. One can be by factorizing if it's possible, or you can use the quadratic formula. The quadratic formula applies when you have a quadratic with coefficients, as I'm writing here. So a, the coefficient of x squared, b, the coefficient of x, and c, the independent term. And solving that to 0 means we use this formula minus b plus or minus the square root of b squared minus 4ac, all inside the root, divided by 2a. In this case, a is 1, b is 3, and c is 0. The independent term is 0. That's why we had a y-intercept of 0. Now, we can do that and apply it to the formula. So we could do x equals minus b, which is minus 3, plus or minus root of b squared, so 3 squared, minus 4 times a, which is 1, times c, which is 0. So this bit disappears as 0. Over 2a, which is just 2. And we could solve and simplify that. Now, we can do that, but I'm going to show you another way that works for this particular example. So I'm going to rub all of this off and leave the quadratic formula for a more complicated example. In this particular case, I can factorize because there's no independent term, so there's a common factor of x. So I do x times x plus 3 all equals 0, and I have to do the equivalence. And that is equivalent to say, well, two numbers multiplied, this and this, multiply out to 0. The only way we can have that if one of the numbers is 0. So I say x is 0 or x plus 3 is 0, which means that x is 0 or x is negative 3. So the zeros of my function, the points where it crosses the x-axis, are minus 3 and 0. So on my graph, I'm going to choose a scale, and I'm going to say this is going to be the scale 1, 2, and 3. Okay. Minus 3 and 0 are the points where the graph crosses the x-axis. So I've got those there. Now, what else other than the zeros? I mentioned the vertex. Where is the vertex? It's on that point there, but because we have two zeros, the x-axis is somewhat above the vertex. So we know we've got a minus 3 there and we got a 0 there. The vertex is always in the middle of the two zeros. So we should expect the vertex to have coordinate x minus 3/2. It's bang in the middle, but we don't know what the y value is yet. Because what we do is we replace x equals minus 3/2 in the expression and we get the value of y. So y is x squared plus 3x. We're going to do x equals minus 3 halves, because we said it's in between the zeros. And that means that y equals minus 3 halves all squared plus 3 times minus 3 halves. And that gives us, when you boil down all the numbers, to minus 9 quarters. So in our graph, we can do minus 9 quarters. That is minus 2 minus a quarter. On that scale, if that's minus 1, minus 2, a quarter is around there. So minus 9 quarters is there. And that is the value of y for the point minus 3 halves, which is here, minus 3 halves. And so this is the other point I've got. That's the vertex. I'm going to call it V for vertex, that point there. Okay, so far I've got 3 points for my parabola. We could add a few more to do a nice plot. So we could complete our table of values. Let's say I've got minus 4, which is before the 0, minus 3, that is the 0, minus 3 halves, which is on the vertex, the 0, and then let's do another value of 1. So we've got zeros here. We've got minus 9 quarters here. And now let's calculate the others. Minus 4 squared is 16. 16 plus 3 times minus 4 is minus 12. So I've got 4. And then I've got 1 plus 3, which is 4. Okay, and then on the table we see the symmetry. The values are the same distance from the vertex, have the same values of y. So on my graph I've got 4, so 1, 2, 3, 4 at the very top of the page. So for minus 4 and 4, 1, I've got those points there. And now the sketch. Let's have a look. Really trying to capture the symmetry of my drawing, and you can always readjust. It's best to use a thicker line to make sure I cross the points I need. Now, if you're submitting hand-drawn work, it doesn't hurt to make a comment saying it is supposed to be symmetrical, and you explain more about that if you haven't achieved that with your drawing. Now, questions you may be asking: what if we hadn't worked out the zeros of the graph? Could we still work out the vertex? Yes, we could. To do that, we can complete the square. To complete the square, I start with my y equals x squared plus 3x, that's my function, and this part here I'm going to write as a x plus something all squared. So the way we do that, I need to put a number here, so I do the half of the 3, so 3 halves, and then I have to take away the square of that 3 halves. And this gives me, I want expand, because if I expand I get what I started with, and I just work out what this is. 3 squared is 9 and 2 squared is 4. So that is the expression, which is the same, it's same function as they're equivalent, but this one, the bottom one, reveals the vertex. These are the coordinates of the vertex. So the vertex has coordinates. There's a 3 halves there, so we do minus that, and then minus. So in other words, if you have x minus a number, must be the vertex is AB, okay? Which is our lovely graph there. So y equals x squared plus 3x sketched. We're looking at cubics now. Say we have y equals minus x cubed plus 2x. Looking at the expression, the independent term is 0. That means we have a y-intercept of 0. So we can already put 1 point on the graph. So let's draw our graph. And we already have the intercept is at the origin. What else can we know? It's a cubic, so we have less tools than with quadratics, but in this particular case, we can look for the zeros. We can solve it y equals 0. So we can solve minus x cubed plus 2x equals 0. We can do that not only because we have no independent term, we also have no term in x. So it will be possible to factorize and solve this equation. So that means I've got an x factor, minus x squared plus 2, that equals 0. Again, a product that gives 0. That means each of the numbers could be 0. Okay. And now we solve these. So we've got x is 0, or x squared minus x squared equals minus 2. So x squared equals 2. And that means that x is root of 2, or x can be the minus root of 2. So in this case, we can find the zeros of the function, but note that in general, with a cubic, it will be beyond the scope of this course and many undergraduate courses to find the zeros of a cubic. Now we got the zeros here. There's 3 of them, so we're going to mark it on the graph. So root 2 is around 1.4. So we've got a scale. If that's our scale, 1, 2, 3. Is that a good scale? We could be a bit more generous. Let's do -1 and this -2, and this 1 and this 2. Okay. So our zeros, minus root 2 or 0. Root 2 is about 1.4. So we have minus root 2 over there as 0, and root 2 around there. And we have 0 that is a 0. Okay, we've got those 3 points. Now, what does the graph look like? It's a cubic. So a cubic, it's either like this or like that. Or you don't have the wiggly bit in the middle. It could be just like that or like that. Now, this is the coefficient of x cubed is -1. So it is a descending cubic. So it's one of these, either the top one or the bottom one. Finding the middle bit will depend on the zeros. But look, we've got 3 zeros, so it has to be the wiggly type. We're going to delete all the others. So we expect the graph to look like that one. Let's find a few more values. So what values to choose for our table? Now, we calculated vertices on quadratics. We don't have tools at this stage to calculate anymore. Those kinky points on the graph, we don't have the tools now to find them, okay? So we're going to estimate them. We're just going to find a value in between the zeros, values in between the zeros, to make the best judgment we can about this graph. So our table of values, the values we want, -2, we've got the minus root 2, which is about -1.4, -1, the 0, the 1, the root 2, and the 2. So we got the zeros, we got values in the middle, and we got a little bit outside the zeros. So values of y, and we've got, just remind ourselves what the expression is, minus x cubed plus 2x. So minus 2 cubed plus 2 times -2. That is -8 times minus, so it's 8 minus 4. That gives us 4. Okay, got that value. We should have the same value on the 2. Let's check. Minus 2 cubed plus 2 times 2. That's going to be -8 plus 4. That is -4. On -1, we have minus 1 cubed plus 2 times -1. That gives us 1 minus 2, so that's -1. And on 1 minus 1 cubed plus 2 times 1, we have -1 plus 2, which is 1. And on all the other values, we had 0. Let's see if that makes sense in our graph. Got 4 and -1. So I need an appropriate scale. That's -2, that's -4. That's 2, that's 4. And let's have a look. On -2, I've got 4. On 2, I've got -4. On -1, I've got -1, which is here. And then on 1, I've got 1. It's around there. And I've got 0. Okay, let's see how this works. Let's try and draw that graph. Not bad. Y equals -x cubed plus 2x. Looking at that graph, I know there's one part there that isn't really accurate. The behavior between the zeros. I don't know if it's as shallow as that or not. What to do? What I mean is, I've drawn that green line, but going through the points, here's another alternative. This orange line is a totally plausible line and it fits the data. We need to add more values to the table. So you're going to do that. You're going to find more values of x in between here so that you can figure out how the graph looks like, if it looks more like my orange or my green curve. So you're going to go away and calculate more values of x and the respective values of y in those regions to clarify exactly what the behavior of the curve is like. So far we plotted graphs of quadratics and cubics. Quadratics and cubics are special types of polynomials. Polynomials of degree 2 for quadratics and degree 3 for cubics. Any power larger than 3 on a polynomial, we're going to call them higher order polynomials. And there is a very limited amount of mathematics you can do with them at this stage. So what can you expect? If I give you a function that looks like this, y equals a really large number of multiplications, x minus 4 times x minus 3 times x minus 2 times x minus 1 times x plus 1, if you were to multiply out all these brackets, the largest power of x you'll get will be 1, 2, 3, 4, 5, x to the power of 5. And then you have some terms in x to the 4, x to the cube, and so on. That'll be a larger, higher order polynomial, will be a polynomial of degree 5. Now, there's no advantage in multiplying out these brackets because we have a little bit of information in this polynomial as it is. The fact that it's written as x minus a number times x minus a number and so on, that gives you the information of the zeros. So this polynomial we know has to cross the x-axis when x is 4, because when you make x equals 4, that term becomes 0. When x is 3, when x is 2, when x is 1, and here, when x is -1, if you replace x by -1 everywhere, you'll get numbers, and this last term will be 0. So each of the numbers I wrote there, 4, 3, 2, 1, and -1, are zeros of this function. So we're going to draw that on the graph. Okay, we got our y-axis and our x-axis, and the zeros go from -1 to 4, -1, 1, 2, 3, and 4. So those are the points where the graph crosses the axis, the x-axis. This graph, what it looks like, is a degree 5 polynomial. It's going to look like this with the x-axis crossing that way. So 1, 2, 3, 4, 5 zeros. And I know there's an ascending one because when I multiply out all the x's, it will have a positive coefficient. So it is an ascending graph in the sense that it goes from a lower value here to a higher value there. To complete the graph, all you need to do is make a table of values that incorporate all the zeros and puts numbers in between. So it would be a nice thing to do: -2, -1, 0, 1, then a half, 1.5, then 2, 2.5, and 3, 3.5, and 4, and 5. And you can complete that table of values with corresponding values of y plotted in the graph, and you'll get a curve roughly like this. You can then check your answer by plotting the graph against graphing software and see how well and how accurate your own graph was. Let's look now at plotting reciprocal functions. One example of that is y equals 1 over x minus 5, meaning that the function of x is 1 over x minus 5. It is a reciprocal because we have 1 over an expression in x. In this case, 1 over x minus 5. With reciprocals, the main thing to watch out for is the domain, or in fact, the points that aren't in the domain. So in this case, the problematic value, the value that will give you a division by 0 in computing, you don't want that, is when x equals 5. So x equals 5 is not in the domain, so the domain of this function is the whole of R except for the value of 5. And that's 5 because if x equals 5, then x minus 5 is 0, and we cannot perform division by 0. Why do we care about the domain at this stage? It's because it will be a very sensitive part of this graph. When x approaches 5 by lower or upper values, the function is going to behave in a highly sensitive manner. The values of y are going to get huge. So we're going to prepare our table of values, taking this into account. So 5 is our sensitive value that the function isn't defined on, so it's not defined. We're going to have lots of values of x around 5. So we're going to do 5 and a quarter. We'll do 5 and a half, 5 and 3/4, and 6, and so on. We'll see what if we need more. And on the other side, we're going to take a quarter away from 5, so 4 and 3/4, 4 and a half, 4 and a quarter, value of 4, and then we'll see what else we need. We're going to calculate those, so let's remind ourselves that it's 1 over x minus 5. So for 4, we have 4 minus 5, which is minus 1, so 1 over minus 1 is minus 1. For 6, we have the value of 1. And then for 4 and a quarter, we're looking at 1 over 4.25 minus 5. That is, the denominator we have 0.75. That is, it's 3/4 at the bottom, so that makes 4/3. That's the value, and that's 1.3 recurring, or you can just write 4/3. 4 and a quarter, we have 4/3 as the answer. I missed the sign here. It should be minus, 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 minus. And in 5 3/4, it's going to be 4/3. You can check that by yourself. On 4 1/2, 1 over 4.5 minus 5, that's going to be 1 over 0.5. So 1 over negative 0.5, that's going to be minus 2. And on the other side, on 5 1/2, it will be a similar calculation that will get you 2. And on 4 3/4 is 1 over 4.75 minus 5. This will give us minus 1 over 0.25. 0.25 is a quarter, so this is negative 4. So the values are increasing. And if we wanted to have more and more detail, we could find more values between 4 3/4 and a value of 5 to have finer detail. And on the other side, it will get you a value of 4. You can check that. Now, this should be enough for us to have a good picture. As on our graph, we need a range, a vertical range from -4 to 4. And we need x values from 4 to 6 with quarters showing. Okay, let's do that. Okay. 4, 5, 6. 5 is where we have the vertical asymptote because we don't have a function defined there. We're going to have values for 4 1/4, 4 1/2, 4 3/4, and the respective values on the other side. On the vertical axis, we need range from 1 to 4. So let's do, say this is 4. This is going to be, what values do we need? 4 and 2. 2 will be here, and 1 will be here. And let's work with it. So with 4 we got -1. Let's do it again. -4, -2, -1. So I've got, and 4 -1. On 4 1/4 I got -4/3. 4 1/4 is there, -4/3. Let's do a third of that. That's going to be around here. And then -2 on 4 1/2. -2 is here. And -4 on the other one. Okay. And on the other side, I'll have a similar behavior. So I've got 4 around here. I've got 2 in the middle. So that's one there. And then I've got the 4/3, which is 1 1/3. That is going to be the value for that one. Now, what graph do we expect? We expect a graph like that, with axes going that way. Is that what we have? Almost. So what happens as values of x increase? Let's try a big one. Let's try in our calculator. So if we do what's big, so we try, let's try 20. If x is 20, we have 1 over 15, so 20 minus 5 will be 15. 1 over 15, 1 divided by 15, that is 0.6 recurring, 0.06 recurring, beg your pardon. And then if I try the value of -15 on the other side, or let's try -10 on the other side. -10 on the other side, that should be the equivalent value. -10 minus 5 is -15, so it should be -0.06 recurring. So under 0.01. So very, very close to the x-axis. So on -10 and on 20. So really large. So we expect the graph to behave like this. This sort of behavior. And I'm implying that we're not touching the x-axis and we are not touching the asymptote, but we are approximating it. What to highlight? This line here is asymptote. It's a vertical line through 5. So is the line of x equals 5, that's the If your graph doesn't look quite symmetrical, and it should be, then you can always leave a note saying that the two branches of the graph should be symmetrical. We just looked at reciprocal functions. There's another type that also has a ratio, and is a rational function. For example, the function with expression y equals x over x squared minus 1. The denominator of this function, when calculated in x equals 1 and x equals minus 1, will be 0. Again, division by 0, which we can't have. So the domain will be r except the values that make the denominator be 0, which is -1 and 1. That's because minus 1 squared minus 1 is 0 and 1 squared minus 1 is 0. Now, so we expect to have two vertical asymptotes, one in -1 and the other one on 1. But what will the graph look like, and how do we prepare for this? Well, the method is similar to what we've done for reciprocals, so I'm going to show you the graph plotted in graphing software. So this is the graph, and we have, I'm just going to zoom in here, and on -1 and 1 we have vertical asymptotes, as in we have no graph there, and the function, the rest of the graph, is approximate to that line. We grab the graph, we have it here, so let's just make some notes on top of it. So the asymptotes that with the equation x equals -1, and the other asymptote over there equation x equals 1. And in terms of table of values, we're going to choose values close to these asymptotes and enough detail in the middle to account for this really nice wiggly behavior around 0. So I would suggest that we will use a number that's far away from the asymptote, and then as we get close, we want detail. So in between -2 and -1, I suggest at least 4 points. The closer to -1, the better. So I'll recommend that we'll use values of x of -6, -3, -2, and then between -2 and -1, at least -1 3/4, -1 1/2, -1 1/4, and if needed, a little bit of finer detail. And then we skip the -1 because it's not defined there. And then we'll do -3/4, -1/2, -1/4, the value in 0, and then the symmetrical values of these values of x. So that's why I recommend you start with. How would you know that without the graph? Well, we based it all around the asymptotes. So we chose a value far away from the asymptote, and then as we get close to the asymptote, finer and finer detail, at least quarters of interval between the values. That then between the asymptotes, between -1 and 1, again, fine detail, and repeat the same pattern symmetrically. If you choose the values of x symmetrically, taking into account where the asymptotes are, then the symmetry of the graph will be sorted out automatically by that choice of values. As before, this function also has a horizontal asymptote. That's highlighted here in green. And it is the x-axis once again. And you might wonder, can we have horizontal asymptotes that are not the x-axis? Yes, we can. We'll look at that in transformations. And that's pretty much all you need to know to get going with plotting rational functions. The last type of function I want us to look at is the piecewise function. That means that the function is made of different branches that have different expressions. So let's look at this example. Y equals x if x is less or equal to 5, and 2x minus 4 if x is greater than 5. Basically, we have two expressions. We have y equals x, and that's whenever x is less or equal to 5. And we also have y equals 2x minus 4 for values of x greater than 5. We're basically plotting two graphs. Y equals x is a straight line with gradient 1 going through the origin, and y equals 2x minus 4 is a line with gradient 2 with minus 4 as the y-intercept. So we could sketch those to start with, and then make sense of the branches later on. So let's plot the lines. Y equals x. Y equals x. We need a scale here. We had 1 to 1. But I'm going to choose this value here to be 5, 10, and so on. Okay, and so on. And on the vertical axis, the same scale. We already commit to it because we already drew y equals x in 1 to 1. Okay, and now y equals 2x minus 4. Minus 4 and a slope of 2. So that point and that point and that point, that point. So let's get a line through all of this. So that is y equals 2x minus 4. Now, how do I know how to draw this graph? So let's look at the expression again. It's y equals x for x up to 5, including 5. So up to x equals 5, we have the first graph. So I'm going to use the green pen. So we have this graph in green, up to 5, including 5. And then we have the other one. So I want to include this point, and I want to exclude that point. The branch of y equals x includes the point 5, 5, and the branch y equals 2x minus 4 has an open dot on the point of coordinates 0, 6, and then is full line from then onwards. So that's the graph of a piecewise function. The functions we're going to have in the branches are going to be of the type we saw earlier. Straight lines, quadratics, cubics, reciprocals, rational functions. When you played with graphs of functions earlier, you may have noticed that some graphs looked pretty much alike, but their expressions were different. We're going to look at these cases and what is the mathematical reason for that. We're going to look at transformations of graphs such as scaling, translations, and reflections. Now, to make the most of this section, I wanted to bear in mind the key identifiers of a function. What I mean is that when you look at a graph or you study a function, and if you notice details about the domain, whether there is a gap or a discontinuity, or there is a vertical asymptote, or maybe more than one vertical asymptote, I wanted to bear in mind those bits of information about the domain and the behavior on the x direction of the function. Other things like zeros, meaning where the graph cuts the x-axis, or even intercept, where the graph cuts the y-axis. Also, if they are horizontal asymptotes and where they are located. other features like extreme points, so where we have a maximum or a minimum of a function, where the function changes growth or decelerates growth. All these elements will be important to help you make sense of which transformations are happening to a graph. In some cases, like the quadratic function, we can even attend to details such as the vertex or the opening of the parabola. With straight line graphs, we'll be paying attention to the slope and whether it is ascending or descending and what happens to transformations of that function. So join me in looking at these graphs. I'm going to picture here the graph of 1 over x, and I want us to think of the graph of y equals x cubed minus x squared. So we're looking at those two, and we're going to look at transformations of each of them. So let's focus first on the reciprocal, y equals 1 over x. Now, in this function, one of the key features is that it has an interrupted domain. The 0 does not belong to the domain, and it has a vertical asymptote at x equals 0. It also has a horizontal asymptote at y equals 0, the horizontal axis. What would a transformation of this graph look like? Well, it will be this graph shifted somewhere else, either by a horizontal translation or a vertical translation or a combination of both. We can reflect the graph on the y-axis or in the x-axis, and we can also scale it up or shrink it, either in this direction or in the other direction. I don't mean by that to change the window, like doing what I'm doing here. The scale there has changed, but the proportions of the graph are still the same with respect to the scale. What I mean is absolutely having a different graph that stems from this one. So let's look at this one. Let's look at what the brown graph looks like compared to the grey one. So I started with the grey graph, which was the reciprocal, and the brown one, okay, yes, you can see the expression on my sidebar, but let's focus on the drawing at the moment. How would you describe, how do you get the brown graph from the grey one? If we look at the discontinuity in the domain, the grey graph has an asymptote at x equals 0, whereas the brown one will have the same asymptote but at x equals minus 3. So I shifted the graph 3 units to the left, so minus 3 units in the x direction. So that is a translation that brings the grey graph to the brown graph. In the same way, the other example I had was the cubic. So now we're looking at a brown graph as our base graph. If I apply the same transformation of translating, meaning shifting this graph 3 units to the left, so minus 3 units in the x direction, I get that blue one. And again, look that the point at the origin of the brown graph, it's now at a point when x equals minus 3. The other 0 of the graph, of the brown graph, which was at 1, is now shifted to negative 2. Again, 3 units to the left, so 1 minus 3, giving minus 2. So this is what I mean by focusing on these key features of the graph to identify the transformation. Now, how does the expression of the function change when I do the translation? Well, let's focus then now on my toolbar here, on my sidebar. The brown graph has expression y equals x cubed minus x squared. That's highlighted as my function p in this graph. The blue one, q, is x plus 3 cubed minus x plus 3 squared. Just take a moment to think of what is happening between the two. The cube bit and the square bit look pretty much the same on both functions, p and q, but the q function is like the p with the x replaced by x plus 3. So I'll write that down, making sure we see that. So p is y equals x cubed minus x squared, and then q is y equals x plus 3 cubed minus x plus 3 squared. And I'm just going to take a moment to clarify the notation. When I say p such that y equals x cubed minus x squared, I mean that y is a function of x and the function is called p. And that means I could also write that p of x equals x cubed minus x squared. So these are ways of writing the same thing. So in the same fashion, q of x is x plus 3 cubed minus x plus 3 squared. So notation out of the way. The similarity between the two functions is that I'm doing a cube minus a square, and I'm using the same thing cubed minus the same thing squared, whereas in p I have an x, but in q I have an x plus 3. And obviously I need to put brackets when I'm cubing and squaring, but I did have got the same. So that x plus 3 is responsible for translating the graph minus 3 units in the x direction. So how do I write this down? I'll say that the graph of q of x is a translation of the graph of p of x minus 3 units in the x direction. Now, some of you may be wondering, why minus 3 when I have x plus 3? Good question. It can be confusing. This is where I think it's important to focus on the key identifiers of the graph. So let's look again at the graph we had. And the brown function is p. If I use as key identifiers the point when x is 0 and when x is 1, what did I have to do to the x values to end up in the same important points of the blue graph? This point here at 0 became the point here at minus 3. So from 0 to minus 3, I had to do minus 3. And the same works from that point 1 on the brown function. What do I have to do to have minus 2? Well, I do minus 3 again. So that tells me it is minus 3 units on the x direction. Let's see if that makes sense with the other function. We had the reciprocal, and the other function is there. In terms of the expression, I had y equals 1 over x, and the translated by minus 3 units in the x direction is 1 over x plus 3. I'll just write that down. So 1 on y equals 1 over x, when we translate in the x direction by minus 3, we get y equals 1 over x plus 3. You can think of it as we're doing 1 over x minus the translation part. Because the translation is minus 3, is 1 over x minus minus 3, which is plus 3. We can also translate vertically, and that means we're going to move the graph up or down. That means we are changing the values of y by adding or subtracting a constant value. So if we start with y equals 1 over x, if we want to translate it upwards by 5 units, all I have to do is add 5 to the expression. So as simple as y equals 1 over x, when I translate by 5 units in the y direction, that means I'm adding 5 to everything. So I'm doing y is what I had before as y, which was 1 over x, and now add 5 to it. If I wanted to translate down 3 units, I would do y equals 1 over x minus 3. So this function has a graph that is the translation of the graph y equals 1 over x minus 3 units in the y direction. We're also looking at scaling, and we're going to scale graphs in the x direction. We can scale them up or down. We're always going to take it from the point of view of scaling up. So if we scale up by a factor of 2, we are doubling. If we're scaling up by a factor of a half, we're going to shrink it. And we can do that in the y direction as well. So back to our cubic function, p, this y equals x cubed minus x squared. Let's do some scaling. So I'm going to create another function. I'm going to multiply everything by 2. So I'm going to multiply, I'm going to do 2, and I had x cubed, so I'm going to do 2x cubed minus 2x squared. Now I've got a purple graph that is a scaling of the brown graph by a factor of 2 in the y direction. I multiplied everything by 2. I'm doubling all the y values. Now, does it look like I've doubled it? Let's look into detail at what those two graphs look like. So the brown one is our base function, is the function we started with, and then we doubled everything. So when x equals 0, we have a y value of 0, so doubling that is just going to be 0, and the same happens in 1. And then look at the other values. On the same vertical line, so if we look at around x equals 0.6, the brown line is just below the minus 0.2, and then the purple looks like the double of that downwards. And looking at a positive side here, it's harder to tell. If you focus on looking on a vertical line, say the line that goes through x equals 1.5, we have the brown graph with a y value around 1.1 and the purple of about 2.2. It's the double. So this is what is happening. Notice that there was no shift in the x direction on what happens to the graph. So it's purely a scaling of factor of 2 vertically on the y direction. Now, what would a scaling of factor of 2 look like in the x direction? Some of you might be thinking, should we just double the x? We're going to double the x and going to see what happens. We're going to double the x, see what happens. You can take bets. Well, you don't, because you're mathematicians, computer scientists, you know that betting isn't a good idea unless you know how the odds work. But let's move on from there. So x, I'm going to double the x, so I'm going to 2x inside the bracket. I need to cube it and then do minus the bracket, and instead of x squared I'm going to do the 2x and now square it. And that is a grey graph. We're going to remove our purple one. So now the grey graph is what happens if you double inside the x. Does that look like we dilated by a factor 2 in the x direction? It doesn't look to me. It looks like we've done the opposite. It looks like we shrunk it by a factor of 2. In other words, that we dilated it, we scaled it by a factor of a half. So it looks like, again, things that happen in the x direction work in the opposite way of the numbers we put in there. So we multiply the x by 2, we get a shrinking. So if we want to dilate the graph in the x direction by a factor of 2, we need to divide the x by 2. So let's do that one here. So y equals, so the bracket, and do x divided by 2, and then cube it, and then do minus bracket x divide by 2, and square it. And that in black, just let's look at black against the brown. I think I forgot, oh yes, I forgot something here. No problem, we're going to put some brackets there. It's good to have this mistake so we know what could go wrong. So we put a bracket, x divide by 2, and then cube it. Ha! Black function against the brown function. That is more like it. That it is, the brown one is scaled by a factor 2 in the x direction, as the key points, the markers, the zeros at 0 and 1 are now at 0 and 2. So let's write this down, make sense of it as a pattern. So when we work with y equals x cubed minus x squared, the expression where we double inside the bracket, we do this. This results in a scaling by a factor of 1/2 in the x direction. Whereas when we divide inside the x, we have a scaling of the initial graph by a factor of 2 in the x direction. And we also looked at the scale is in the y direction, so I'll write that information down. So y equals, if we do 5x cubed, multiply everything, is a scaling of y equals x cubed minus x squared by a factor of 5 in the y direction. To shrink, we can do y equals, say, 1/3 of x cubed minus x squared is a scaling of y equals x cubed minus x squared by a factor of 1/3 in the y direction. That's the sort of answer we would like to see from you that summarizes this sort of transformation. Finally, but not least importantly, we have reflections. Reflections are all about mirror images. So we're going to look at mirroring the graph in a vertical mirror, the y-axis, or a horizontal mirror, the x-axis. All we need to do is to change a sign. Mirroring in the y-axis means I'm going to change the signs of x. I'm going to swap positive x's with negative x's. Mirroring on a horizontal axis means I'm going to change the sign of the y's. I'm going to swap positive y's and negative y's. If I have the function y equals x cubed minus x squared, our beloved cubic, if I multiply everything by -1, meaning I do y equals minus the whole business, which does simplify into this, I obtain a function that has a graph that is a reflection on the x-axis of the initial one. So I have a reflection on the x-axis. So a reflection on the x-axis doesn't change the x, it changes the y's. Okay, so reflection to change the y's needs to be a reflection on the x-axis, and I'm just changing the sign of the y's. Okay, you start with the brown function, and you can use your plotting software to check that the graph is going to look like a mirror image. Just multiply everything by -1 like we did on writing. For a reflection on the y-axis, we start with our function again. So for a reflection on the y-axis, I'm going to change the signs of the x's. So I'm going to replace x by negative x. So I get minus x then cubed and minus x inside the bracket and then squared. We can simplify that, and it is -1 cubed. It's still -1, so that minus there, and the x will be cubed. And then I have a minus, and then minus x squared, that is just x squared, with the other minus that was already there. And see for yourself, plot that graph next to the original one, and you'll see that it is a reflection on the y-axis, meaning that the left and the right side are swapped around. Of course, you can have fun mixing and matching all these transformations, so we just look at one example to give you a taste of that. Remember, you can always plot the functions in your graphing tool to investigate what is happening. So if I have 1 over x and I have another function that is 5 over x minus 1, what are the transformations applied? The x minus 1 bit tells me that it's a translation in the x direction by 1 unit. The 5 part, because it is the same as multiplying everything by 5, it's a scaling of factor of 5 in the y direction. So I can break it down into steps. So I do a translation from 1 over x to 1 over x minus 1, and then I'll multiply everything by 5, which is just the expression we have on top. The transformation is this, in this precise order. It is a translation of 1 unit in the x direction, followed by a scaling of a factor of 5 in the y direction. If we had y equals x cubed and we did the same transformations, let's see if reversing the order will make any difference. Say we do x cubed, do the translation by 1, and then multiply by 5. That's what I get. What if I change the order? What if I did the multiplication by 5 first? X cubed, multiply by 5, and then do a translation. We get the same in this case. Now, could we get a different result? Yes, if the transformations were happening in the same direction. So if I had still y equals x cubed and I do translation in the y-axis, and then I scale it by a factor of 5 in the y direction as well. Now if I do the other way around, I start still with the cubic and then do a scaling of factor of 5 in the y direction. I will have this. And now if I do a translation of 1 in the y direction, I need to add 1 to everything. And these two functions aren't the same. Don't take my word for it, check. You can check algebraically. You also can plot the graph with a graphing tool or by hand. This side here we can expand the brackets. And that is totally not the same as the other expression, okay? So the order of the transformations can matter, and I would like you to gain intuition on that by trying several examples and finding your own pattern. So now you're free to go and play with all these transformations, use your graphing tool, and also practice doing these transformations by hand and describing what the results are and also what the transformation is. We looked at representing locations, points, in 2 dimensions using 2 coordinates. We worked with several types of functions to build tables of values suitable to plot the graph. We focused on the suitability of these values, as the main idea of plotting by hand is to capture the key features of the behavior on that plot. We then looked at geometrical transformations of graphs and how they correspond to changes in the presentation of the expression of the function. We looked at translations in the x and y direction, reflections in both axes, and scaling in both directions. These skills are of use with any type of functions. I promised computer games. Well, sort of. You will learn the maths you need to design them. Let's get the ball rolling. We consider the motion of a particle moving in a straight line with constant acceleration as a function of time. The variables considered will be displacement, s, initial velocity, u, final velocity, v, acceleration, a, and time, t. These equations are often known as Suvat equations. This means that the motion is in a straight line, with acceleration being the same direction of motion. So all calculations show variation from the initial position. So we're going to consider that the initial position has displacement s equals 0. We're going to look at when the particle moves at constant speed, when the particle moves with constant acceleration. We studied the change of position. That means how far and in which direction it moved. And also the change of speed. We're going to look at some graphs. I know I haven't told you yet what the equations are, but we're going to look at some examples and we're going to make sense of them from there. So here I've got an equation for position. So I've got s of t is a function of t, s being 2t plus 10 squared divided by 2. In this case, I've got an acceleration of 10 and I've got an initial velocity of 2. And I can tell that the acceleration is helping moving. It's helping increasing the displacement and it's a positive acceleration, so it's a plus 10. Now, how do we read this graph? This graph is position measured in the vertical axis against time on the horizontal axis. And let's just focus here on the initial seconds of motion. So the units, by the way, time is measured in seconds, velocity in meters per second, and acceleration in meters per second squared. So we've got from t equals 0 to t equals around 6 seconds, we see we've got a reading of position about just below 200 meters. The corresponding expression for velocity, it's here as well. It's highlighted on green and the graph is showing as a green line as well. So that is showing the speed is increasing linearly with time. That's because my acceleration is constant. I'm just saying as every second elapses, we are adding 10 meters per second to the speed. So we can see on this graph that we start with a speed of 2. When t is 0, the green graph is having a reading of 2 because that's the initial velocity is 2. And then every second elapsed, because my acceleration is 10 meters per second squared, for each second the velocity is going to increase 10 meters per second. And look, after 1 second I have a reading of 12 meters per second on the green line. When t equals 1, I have a reading of velocity of 12 meters per second on my green line. I said that the acceleration is constant, so the graph for the acceleration in this case is a horizontal line going through 10 meters per second squared. It will always be a horizontal line because it will always be constant. Let's see what happens when I change the acceleration to be negative. Let's just put it to minus 10 meters per second squared. So I'm going to change all my equations of motion here. Put a minus on that one, and acceleration here being, okay, let's see the result. And there we are. Let's isolate them. Acceleration is constant at minus 10 meters per second squared. The velocity is going to be decreasing because I have an acceleration that is negative. That means this stopping motion is stopping, so it's decelerating. The velocity is going to decrease. It decreases from 2 meters per second at time equals 0 seconds, and at 0.2 of the second, the velocity is 0. And then it will be negative. So it's starting to move backwards with a negative velocity. Let's see what happens with the position. With the position, we start at the origin, so displacement 0. And as time increases, when I get to that point, when time is 0.2 seconds, is when the velocity hits 0, the position hits the maximum value. This is what happens when you got a ball going up in the air. You go up, it stops and it comes down. The position the distance has increased, and then it starts decreasing again. That's what is happening with our brown graph there. Feel free to play with these equations on a graphing tool to make sense of how the graphs behave as you change the initial conditions. Now, the equations. We're going to look at the equations similar to the ones we saw and a couple more. So we write, just bearing in mind that S is a position along time, U the initial velocity, V the final velocity, and acceleration is constant, and time elapsed. The equation for position is initial velocity times time plus a half of the acceleration times the square of time. Sometimes we write this equation without the t after the s. Sometimes we write it just like this. But I quite like to write with t to remind us that it's a function of time. As to velocity, it is the initial velocity plus the acceleration times the time elapsed. We can use these equations to derive others. So S can also be described as some sort of average of speed over time. The square of the velocity is also the square of the initial velocity plus 2 times the acceleration times the displacement. And one more. We'll start with the final velocity times t minus a half of a squared t squared. I'm going to remove the t's there, so we have a more traditional look of the Suvat equations. And let's look at a couple examples of how we use them. Say we have an example like we saw in the initial graphs. We had acceleration of 10 meters per second squared, so I'm going to do s to the minus 2. The initial velocity was 2 meters per second, so second to the minus 1. And I want to know how long it takes to move 600 meters. So we have S equals ut plus a half of at squared. We have the initial velocity, we have the acceleration, we have the final position. So the final position is 2 times t plus a half of 10t squared. So 600 is 2t plus 5t squared. And we basically solving a quadratic equation. And we can use the quadratic formula or factorize. Let's use quadratic formula. T equals minus b, so minus 2 plus or minus square root of b squared, which is 4, minus 4 times a, which is 5, times c, which is minus 600, over 2a, so 2 times 5. This gives us minus 2 plus or minus root of 1204 divide by 10. So minus 2 plus the root of 12004 over 10, or minus 2 minus root of 12004 over 10, and that gives us 10.8 seconds, or minus 11.2 seconds. Now, we're not going back in time, so the solution we want is time equals 10.8 seconds to 1 decimal place. So after 10.8 seconds, we achieve a position of 600 meters. Another question could be how long it takes to get a speed of 400 meters per second. So we have the same data. A is 10 meters second to the minus 2, U was 2 meters to the minus 1, and we want a speed of 400 meters per second. How long does that take? We have that V is U plus AT. We want 400 meters per second. We start at 2. It accelerates 10 per second. So let's just solve that. So we got 3. So 400 take away 2, 398 equals 10t. That means that t equals 39.8 seconds. It takes 39.8 seconds to achieve the desired speed. So we use the velocity equation here. On the previous example, we used the position equation. And then depending on the problem, depending on the quantities you have, you choose the right relationship to obtain the quantity you want. Just one more note on graphs. The position graph against time should be a parabola, either upwards or downwards, depending on the acceleration. If the acceleration is positive, we have an upwards parabola. If it's negative, you have it pointing downwards. The velocity is always a straight line, and is an ascending straight line if the acceleration is positive, and is a descending straight line if the acceleration is negative. The acceleration is always constant, therefore it will always be a horizontal graph. Kinematic equations model a very simple motion. It's so simple that we don't need to keep track of coordinates of the body that moves. We only need to track how far it moved from the starting point. This is because the movement is just on one straight line. That could be horizontal, inclined, or vertical. The trick is that the acceleration is constant. So the velocity changes linearly over time, so only appearing t and numbers in the expression, and the position varies quadratically over time. So it features t squared, t, and constants. This means that the graphs of these functions are quite simple too. Acceleration against time is a horizontal straight line. Velocity against time is a straight line, and position against time is a parabola or a straight line, depending on whether the acceleration is not 0 or 0, respectively. The kinematic equations are often presented as SUVAT equations because of the S, U, V, A, T variables for position, initial velocity, final velocity, acceleration, and time. And here you are, at the end of the module. We looked at some mathematical tools that are a foundation for the numerical needs of a computer scientist. We looked at number basis and modular arithmetic with applications in web page color codes, encryption, and generating seemingly random numbers. Looking at lists of numbers, we looked at sequences and series with special attention to super regular sequences called progressions and their sums. We also looked at how we tap into the knowledge of these sequences and series to study others that aren't so regular. Moving into 2 dimensions, we looked at coordinates and ways of defining regions in space, and we studied functions and their graphs. The key idea is to showcase the behavior and key features of the function with the choice of the window for the graph. We also understood the transformations of graphs actually group functions that have similar behavior but different expressions. If you wish to continue the journey with us, you can join the full degree and complete the Numerical Mathematics module to study trigonometric, exponential, and logarithmic functions. Study geometry of triangles and of 2D space, both using trigonometry, trigonometric functions and matrices. This also introduces us to linear algebra and solving systems of equations. The full module supports the numerical work necessary to learn tools for computer graphics, but also to explore algorithms that range from well-established to state-of-the-art. Of course, we will also look at calculus and probability. Actually, with probability 1. Whether or not you will join us for the full degree, enjoy your newly acquired numerical mathematical tools.